Mic check, mic check. Ladies and gentlemen, good morning. This is your moderator speaking. If you're not seated yet, please make yourself comfortable so we can start in a few moments. Thank you very much. Good morning once more, and a very warm welcome to the 6th General Assembly of the Copernicus Climate Change Service. Thank you for joining us here in Brno, Czechia, as well as online. Allow me to introduce myself. My name is Ali El Jabri. I'm a professional moderator and studio presenter. I'm a former TV correspondent with Associated Press and former lecturer of public policy at The Hague University. Nowadays, I dedicate most of my time to moderating events, including on the climate and climate change. It's a great pleasure to be with you, and I look forward to learning from your input. The program over the course of the next 3 days will consist of various sessions, including 9 thematic sessions on topics that are relevant to C3S, as well as C3S users and the C3S wider community. Today, we will have lunch at 1 o'clock. At 5:30, we will serve mocktails, and at 7 o'clock, we will have dinner. Please do join us on Twitter using hashtag C3SGA23, and please also note that recordings of the plenary room proceedings will be made available this week on the GA website. And now, without further ado, it is high time for the opening session of the day, which will consist of a number of welcome and keynotes. I'm delighted to first give the floor to the Director of Copernicus Services at ECMWF, Mr. Jean-Noël Thibault. Please give him a big applause.
Thank you very much, and welcome everyone to the 6th C3S General Assembly. Thank you for our host, Mr. Sushi, who is going to speak in a minute. I'm very glad to be here because last year I couldn't attend. I had to attend it online for some personal reasons. So I'm really happy to be back together with you. Of course, C3S is special to me because back in 2013-14, we thought about it at ECMWF, and with my colleague Dick D, who is somewhere in the room, not too far. We did a lot of brainstorming with also our point of contact at the European Commission, Bernard Panty, at that time. So we basically built it from zero. And at the time, I remember the discussions whether we should be a voice for climate, an authoritative voice for climate, or the authoritative voice for climate, a lot of things. And today, here we are. When you see the uptake by the media this summer or over the year, it's just phenomenal. So we made it, I would say. And talking with Bernard Panty actually last weekend, we were in Paris for a different reason. France beat New Zealand, by the way. He was telling me, you know, when it's becoming mundane to see Copernicus on the front page of Le Monde or El País or on the BBC TV and all other media, it means we have really succeeded. Because indeed, now it's becoming sort of business as usual to be on the front page. And this is thanks to all of you. So I think we should all collectively be proud of it. So that was my first point. So tap on the back to everyone. Now, there will be several significant things happening within the next months and years to come. First of all, there will be a midterm review of the Copernicus program and the Copernicus services. Perhaps Francesca will say a few words about it. And also trying to think forward, what will be Copernicus 3, for example. So these are the new challenges that we have to start thinking about. So we have to shine and to think for the future. There is also, as you know, disruptive science and technology. Machine learning is already being prominent in numerical weather prediction. So the question is, what about climate? What does it mean for the product, the value chain that we are producing as C3S? Reanalysis is one example, but it's not the only example. There are climate simulation, there are ECVs. What will the future be is also a nice challenge and a nice opportunity. Then we have new initiatives like Destination Earth and other programs, how to make sure that all programs benefit from each other and are not competing against each other. So that's also something which together we are going to contribute to. A good news, which probably some of you already know, but the UK is back. So after so many years and so many troubles, we had to remove the UK from our activities. Now, as of January 1st, 2024, they will be considered as a third party country like Norway, or participating country, sorry, like Norway or Iceland. So this is extremely good news because there was a lot of expertise in the UK which we couldn't take advantage of, and for the future procurements and future activities, we will be able to do this. This won't go without challenge again, but I think it's excellent for the program in its entirety. And the last thing I wanted to mention, because I only have 50 seconds left, is the National Collaboration Program, which is really ramping up for also the Atmosphere Service and now for the Climate Service, which, in my view, is really a nice way to engage with the member states and to increase the uptake of what we do even further. So last words, the climate crisis is not going away, that's for sure. So we'll still have a very heavy responsibility to respond to this crisis in terms of providing information for adaptation and mitigation and being even more policy relevant. So that's a very strong responsibility on Carlo and Sam. Yes, Sam is there as well. And on all of us, or all of you, to stand up to this challenge. But I'm sure that you will manage. Thank you very much.
Many thanks for your words of introduction, Jean-Noël, and thanks a lot for minding the time. We are hosted here in the beautiful city of Brno, and this is why we are honored that we are joined by the Deputy Mayor of this wonderful city, Mr. Jaroslav Suchy. Please come forward while you hear your applause.
Ladies and gentlemen, distinguished guests, it is my great pleasure to welcome you all to the 6th Copernicus Conference here in our beautiful city of Brno, Czech Republic. I'm glad that the discussion on climate change, which is very important these days, is taking place right here in our beautiful city. The location that we're in is also historically significant, as we're close to the Augustinian monastery, where Gregor Mendel made his extremely significant discoveries in genetics. However, it's worth noting that his intellectual pursuits extended beyond genetics. He also dabbled in methodology and statistics. In the monastery library, you can also discover the work of the mathematician, lawyer, and astronomer Nicholas Copernicus, 6 books on the revolutions of the heavenly spheres. This site serves as a testament to the intersection of science and discovery that we continue to explore today. Brno is a city actively engaged in both adaptation and mitigation efforts against climate change. We have a long-standing partnership with the Czech Globe, and we are one of the conference co-organizers, which I'm glad about. Collaboration is the key to addressing climate change, and we are committed to working together with our partners to find innovative solutions. The question we face is this: how can we ensure a pleasant and sustainable life in our city in the coming decades? In 2017, the city of Brno joined the Covenant of Mayors and pledged to significantly reduce greenhouse gas emissions. Our campaign called Prepare Brno is driving us towards our goal of reducing CO2 emissions in Brno by at least 40% by the year 2030 in comparison to 2000. It is clear that we cannot win this battle on our own, and thus we collaborate closely with the Brno community, organizations, businesses, institutions, and the wider public. In partnership with Czech Globe, Brno has been developing adaptation strategy to address climate change since 2016. In the spirit of cooperation and shared commitment, I look forward to discussions and insights that will emerge from this meeting. I think that together we can make a meaningful impact on addressing the challenges posed by climate change and securing a better future for our cities and our planet. Last but not least, I hope that you will have an opportunity not just to sit in this room, which is important, of course, but also I can tell you that Brno is a very beautiful city worth exploring, both the city and the surroundings. I hope you will do, and I hope that this is not your last time in Brno. You are heartily invited to join us here as tourists. Have a beautiful stay, and I wish you a fruitful meeting. Thank you very much for your attention.
Thank you very much, Mr. Jaroslav. We are hosted by the Czech Globe Institute, which is part of the Czech Academy. The director of the Czech Globe Institute will now address you. I'm happy to give the floor to Director Professor Michal Marek.
Thank you. Thank you. Hello to everybody. Do you know, I think that your meeting must be very nice, because when the moderator is starting the conference by announcement when the lunch will be served, I think that it will be perfect. I think that it will be very nice atmosphere here. But more seriously, my name is Michal Marek, and I am a very happy man, because I was really fulfill my old dreams. Because 70 years ago, we started together with my colleagues. The group was named the 7 Heroes. We started to prepare the special proposal, and we was establishing new institute, absolutely according our ideas. And because at this time we were successful in the competing for the European Union structural funds, we was winner. It means that it's a unique situation. You was in the situation where you was preparing the institute, and you received the money for this. Absolutely unique. It never will be repeated. It means that, for your imagine, we started, it was 7 heroes. Now the staff of Czech Globe is 400 people. It means that we started to be a really very big and active institute. Czech Globe, what it means? Czech contribution to global problem. Global Change Research Institute, and we are the part of the Czech Academy of Sciences. It's advantage, because you know the Institute of Czech Academy of Sciences are absolutely independent institutions. It means that really we are really responsible, only we are responsible for our activities. And of course, the Institute activities are based on the 3 pillars. Investigation of atmosphere, investigation of ecosystems, and investigation of society responses. It means that our institute is really dealing with interdisciplinary research, which is a very big advantage. Sometimes it's disadvantage, but in principle it's advantage. We are using the special infrastructure, and I am very proud about it. Basic system of our infrastructure, there are the networks of research site, of some observing points, etc. For example, we are dealing with the carbon cycle. At the present time, we have 8 sites where we are measuring by ecovariance, long-term uptake of CO2 from atmosphere to different types of ecosystems. And because we are Europeans, we are very happy that we established 2 stations in tropical areas. 1 station is working in Vietnam, and second is working in Ghana. It means that we are really starting to be active member of this FluxNet network. The second important network which we are using is the network of special stations for the monitoring of fires, fire risk. It means that we have a lot of stations which is covering the whole territory of our country. And third one is the special network of dendrometers, Dendronet. It means that we have stations where we are permanently measuring the growth of the trees for to obtain the information what happens. Regarding the composition of our institute, we are really very young. The majority of our staff is in the age interval 30-40. It means that it's very promising. The same, I think that we are really very focusing on the gender ratio. It means that we are very happy that we have a lot of colleagues which are women, which are which are heads of department, etc. Very important feature of our institute is that these different teams, at present time we have 17 research teams, are collaborating together. And of course, very important part of our activities is not only the investigation of atmosphere creation, the different scenario models, but we are using the remote sensing. We are very proud that we are owner of special aircraft, which is equipped for remote sensing application. We are doing a lot of the activities together with the European Space Agency. Our aircraft is operating over the whole Europe. It means that I must tell you that the really Czech Globe is very nice and friendly institution. And I am very happy that you are here, that our institution is contributing to this event, and I wish you spend nice time here. Have a nice time. Thank you.
Thank you very much, Michal. Our next speaker represents DG DEFIS of the European Commission, Francesca Somma.
Thank you, Ali. Deputy Major Succi, dear Professor Marek, dear Jean-Noël, dear Carlo, dear participants in the room and online, good morning. I'm Francesca Somma, as Ali said already. I come from the Directorate General for Defense, Industry and Space, which is in charge of managing the Copernicus program. I'm very glad to contribute to the opening of this event, of this General Assembly, and share with you a few considerations. Copernicus today is a world-leading environmental monitoring program based on Earth observation. This past June, Copernicus celebrated its 25th anniversary. The anniversary marks not just the achievements up to today, because as Jean-Noël said, we have achieved astounding success. We are on the news every day, but marks also the start of an even more bold journey, which sees Copernicus at the heart of empowering our climate agenda, which is the biggest challenge we're facing today, with our digital transition, which is one of the biggest opportunities we have, indeed. We're all aware of the climate records of 2023. Rebecca will testify to that. And the recent climate-related emergencies, which were all over the news. We have extreme urgency to act, and we have powerful, ever-evolving tools at our hands to bring this challenge and these opportunities together. We have achieved a lot with C3S and the Copernicus program in general, as I said, but we cannot stop, and we must continue to look to the future with new opportunities, new challenges, be those available from new sensors and new data coming in, or the use of, for example, artificial intelligence and machine learning. I wish to convey you some key elements now that are important to bring the challenges of climate change and the opportunities of the digital transition together, and how C3S can contribute to this. First of all, we intend to expand our space-based observation. that matter for climate change. The Commission is actively working in that direction. We have a concrete and ambitious roadmap for the modernization and the further evolution of Copernicus. We have the next generation of Sentinel satellites and the Copernicus expansion missions, which will empower the Copernicus contribution to the climate agenda. And this will be a step change. The first new mission to come on, as you know, will be the Copernicus CO2 monitoring and verification support capacity, one of our expansion missions. But this is just an example, which is also the most important for the climate agenda. But we also face challenges in this sense. For example, as you know, we have secured funding for 2 of the satellites wished for this mission, but not the third. And in this sense, UK joining the Copernicus program again might bring some good positive news. The Commission has also fully embraced the potential of commercial satellite missions from established players, but also from emerging European new space companies, and we just onboarded 9 of them. This includes data that are important for climate change, such as the monitoring of atmospheric data. We are now working with the Copernicus services, including C3S, on how to integrate this new information in our portfolio of trusted, high-quality information services and products. The second point I wanted to make is the embracing of new digital tools to exploit the data we have, the wealth of data we have. Copernicus is one of the biggest generators of data worldwide. And C3S is an excellent example of how we adopt and push forward the possibility that these new digital tools offer to us. And we are moving already there with the remaking of the Copernicus data store. We will hear about it later on. The highest performance computing center in Bologna, but also artificial intelligence and machine learning, which can improve our capabilities even further, as Jean-Noël mentioned. On the Commission side, we are, as part of fully exploiting our digital opportunities, we have also revamped our data access system by establishing the Copernicus data ecosystem space, which allows public authorities, private companies, and citizens to set up their own services on top of this new infrastructure. New traceability is important for climate change, where facts and evidence are constantly challenged. So this is really more important than ever to gain trust and have transparency. Last but not least, enable users to generate impact. To truly empower our climate agenda with Copernicus, we need to go again on this side also one step further and promote the use in various domains aside from the usual suspect, as, for example, the climate policy, which is already embracing Copernicus largely. And we need to increase the impact of the Copernicus program. For the climate agenda, we are working on the uptake of our CO2 data already. We have a lot to offer and to meet our international commitment. And likewise, we are trying to push the use of Copernicus data and information into all range of EU laws, not just environmental law. And we are doing a number of steps, including, for example, the recent establishment in 2021 of the Knowledge Center and Earth Observation. The Commission is now pushing the preparation and launch of thematic hubs, on which we'll rely to engage regions and themes in a different way. And we are feeding also a thriving downstream market of European business through the European Agency for EU Space, EUSPA. It's also, so I would like to thank all of you for your contribution to the success of C3S as part of the Copernicus service family. It's also thanks to such a strong community of providers of Earth observation data and users of Earth observation data, as we see here today, that the impact of Copernicus is stronger. And with this, I wish to all of you in this room and online an enjoyable and rich assembly. Thank you.
Thank you very much. We now have our final speaker for the opening session. He's Director of C3S. A warm welcome for Carlo Buontempo, please.
Thank you, Ali. Thank you for the hosting of our General Assembly here in Brno. It's a great pleasure to see you in person in a physical space once more. And if you want, what we have been through with this first few presentations has been a bit the preface. If you were a book, it was the preface to the book. And so what I'm going through now is the index. And the index is structured into two parts. The first one is looking back on what has happened over the last year. And the second one is looking forward on what will probably happen over the next few months. So basically, I looked at the highlight that we present on a quarterly basis to the Commission, try to remind myself of what has happened. And the first thing that's happened has been the move of the operation on our new supercomputer in Bologna. This was a major exercise where the production of ERA 5, our reanalysis, and the seasonal prediction moved from the UK to the new computing center in Bologna. And this was done without breaking at all the operational nature of these streams. So everything worked very nice and very smoothly. So major success. In November last year, we went to COP, and at COP27, C3S was extremely present. We took part in several meetings. And it was interesting that we were hosted by WMO, by the UN Pavilion, by the EU Pavilion, but also by the Union for the Mediterranean, and our presence was very much felt. Around the same time, actually in October, we launched the first joint report on the state of the climate with WMO for the European region. And this was the first that was followed then in June by the second edition. And now we are working much more closely with WMO in the production of the next year report. Right? How do I change slide? Okay, good. Looking at the beginning of the year, I guess the highlight was the fact that we sent out a look back on the analysis of 2022 for the first time. This was well before the state of the climate. And the second highlight was the fact that ERA 5, a single data set, reached the 100,000 user mark. Other highlight of Q1 was the production of ECVs in a joint effort with Mercator Océan. So the idea is really to leverage what is going on in other services in the production of our ECVs, and is a model we would like to follow for other ECVs in the future. And then, very importantly, and referring back to what Francesca was saying in her introduction, actually we have a first example where the data from C3S fed directly into an existing policy from DGN, where the information, not just information, but the data actually makes a difference in informing a policy. In the background, many things were happening. So on the one hand, we have the title page on the newspaper, and we'll say more about it. But on the other hand, this is really important. Work was going on in the building block of the service, and in particular in the reanalysis. So in the contribution agreement, we promised to bring back the reanalysis to 1950. And as a matter of fact, we pushed it back to 1940. So we have a very long stream of 83 years of reanalysis in reaching near real time. And this also happened for the ERA 5 land in near real time, which was another achievement. And there will be more information on the reanalysis in session 1, but also on the regional reanalysis. So there were major milestones being met by the regional reanalysis, both the Arctic reanalysis and the European reanalysis in terms of update. Those important building blocks. Going to Q2, we released the State of the Climate report. And again, it's interesting, I will say a bit more about the State of the Climate report, because if you look at the progression over time, has been extremely important. But it's not just the State of the Climate, it's the seasonal prediction that in Q2 already predicted the occurrence of El Niño. There was a lot of discussion internally on whether, on when to communicate on El Niño. But what we are seeing now really indicate not only that the Niño is very likely to be a moderate or strong El Niño, but also the fact that the entire world is a different place to what it has been, and so the teleconnection needs to be looked in that fashion. Finally, again, a lot of work on reanalysis, and in particular on the use of reprocess and rescued data, and I will say something more about it. This is what I meant when I was talking about the State of the Climate report. It comes every year in April and requires a big effort, not only within ECNWF, but from many of you who contributed to it. And if you look at the progression over time from 2019 to now, in terms of visibility, has been incredible. And this year was not exception. On the contrary, it had a major impact, maybe. Is there? Okay, good. Well, they meant to come one by one, but if you look at the titles of the newspaper, not just in one language, but in a variety of languages, you really can feel how important the state of the climate has become. June, we hosted in Bonn, in our new premise in Bonn, the GCOS meeting, the joint panel meeting, and it was a very good occasion to strengthen the existing relationship between the Global Climate Observing System and our program. And in particular, an element that we picked up from that is this joint action on C3S and GCOS on making the GNSS precipitable water archive available for further exploitation. And this is an important element among many. Looking at Q3, well, actually, Jean-Noël was mentioning Bernard Panty and the discussion about the visibility of C3S internationally. When the Secretary General of United Nations explicitly mentioned, as you can see in the arrow, the Copernicus Climate Change Service in his speech in July, well, that for me is a new benchmark in terms of impact. And I sent the photo to Bernard, who was very, very happy about it. Also important in June is the fact that the Climate Data Store reached the 200,000 users, which is a very noticeable mark. I remember where we were just a couple of thousand registered there. Even more staggering to me is the fact that we are now close to 250,000, just 3 months later. On the projection side, we made the first step in the operationalization of the IPCC Atlas. So the data underpinning the IPCC Atlas is now available on the Climate Data Store. The idea is to make the entire Atlas and the new setup of the Atlas available in the new year when the new climate data store will become available. Finally, I think a note of mention from the Library of Congress in the US, who identify C3S as an important website to preserve in perpetuity because of the impact C3S has on global communication. So that was an interesting benchmark in terms of our global visibility. One of the things we will do in the next year is to improve on the remote control of the presentation. But looking beyond this and in the specific, one of the elements that I really think is important to highlight is the role that applications have. So there have been a lot of development in the application within the SISs, the Sectoral Information System, on, for instance, the interface with EEA. EEA is playing a vital role in the EU climate risk assessment, but also in the mission on adaptation, and making at the service of EEA the infrastructure and the data that are available through the Climate Data Store is very important. There are a similar engagement is happening with the European Investment Bank, and is making very rapid progress thanks to Chiara. And there will be more information in session 1 and 6 about this. Two areas of development on agriculture and water, a different stage of development, but this is happening very, very soon. So if you look at the program as a whole, I think we are pretty much on track with our plan. We engage with the vast majority of European countries. We have very many contracts ongoing. And what is interesting to me is that if you look at the distribution of our contractors, the majority of our contractors are private entities. And among of these private entities, the SMEs play an overwhelming role. So that's a very important signal for the health of the service, in my opinion. So I promised to divide this index in two parts. So we touch about what has happened. Let me just briefly touch on what will happen next. Well, the first thing we heard already is the fact that we will happily welcome back our UK colleagues and friends that we had to part from due to Brexit. And this is really important, as both Francesca and Jean-Noël were mentioning in their introduction. If you look at specific in the ECVs, what we are planning to do in the ECVs, and we already started to do with the issuing of an RFI, a request for information, is to change the way in which ECVs are produced and organized. So the new setup for the ECVs, ITT, is being defined now. But the idea is to ensure that we can expand the list of ECVs available while also increase the efficiency in the use of the budget. So these are a major shift. The second one, and actually this is a slide from Paul Pauly, is about the preparation of ERA 6. And I guess one of the questions is, why do we bother? ERA 5 is a major success. Why should we bother in generating a new global reanalysis? And if you look at, well, these are standard metric to look at the performance of reanalysis, the anomaly correlation of the forecast at 500 millibart geopotential height. And if you see the evolution from ERA 15 to ERA 40, to ERA interim, and then to ERA 5, you see, maybe not ERA 5, but you see that the quality of the forecast keeps improving. Good. So by including more effort on all sides, so on the resolution side, on the level of coupling, on the data simulation, on the physics of the model, we actually improve the description of the climate system, and so we improve the utility of it for our user. And a lot of these things have been defined for ERA 6. Some details are still to be defined, and we are finalizing it so that we can start by July next year, most likely. But the other way in which we improve the reanalysis is by using observations that are not available, or they were not available at that time. And so the work on data rescue and reprocessing is very nice. And these are a slide from Bill looking at IRIS, which is a spectrometer flying in the early 70s. Single spectrometer, you can see the coverage in 12 hours on the top left. So very few data points. And still, this very few data points in a period that is so data scarce make the difference. And you see the improvement of the forecast, both in the bottom left and bottom right. And we'll need more time than I have to get into the details. But I found very interesting that even just a single mission can make such a difference in the quality of the forecast. But it's not just that. So I was approached last year by a consultancy company who said, oh, you do weather forecasts at ECNWF. Wouldn't it be nice to do weather forecast in the past so you have a reconstruction of all 3D fields for the last 40 years? Funny you talk about that. That's what we do. And this means to me that on one hand, we need to work on improving the reanalysis, but on the other hand, we need to keep working in ensuring that the people know about it and use it. And these two plots that Julien and the climate intelligence team put together have been seen by tens, hundreds of millions of people over the last summer, because they describe the climate crisis that Jean-Noël was referring to. So it's important that we work on the two sides, because having a great product that nobody knows is not of great use. One of the other priorities in the near future will be attribution. Attribution has been parked in Copernicus 2 for a number of reasons. Now we are in a situation where we can restart that process. We will start with a couple of ITTs coming out very soon, and possibly with other tools later on. And the idea is to build upon the pre-operational prototype that was put together in phase 1, but also incorporate new development, in particular in AI, that has made major step forward in the generation of counterfactual reality. So it's really an exciting area that we finally can touch and expand on. And this is likely to happen over the next quarter, at least the first steps. What is not going to happen in the next quarter is the good. The next big development on the EQC, in the program, is the EQC. So EQC, the evaluation quality control, has been, in a sense, a bit quiet over the last few months. We didn't talk too much about it, but a lot is happening in the background, and it's really a new approach to the way in which quality information is set up, displays, and integrated in the climate data store. So we do expect over the next few months for this to become visible, to be visible to everyone and accessible to the climate data store. And this is an important evolution, because we were discussing with Stefano this morning over breakfast. In a sense, quality assessment is probably one of the most important entry points if you look at the climate data. So a major development. The other development that has been mentioned by other speakers is the development in the user engagement. So on the one hand, on the user intelligence, but also on the National Collaboration Program. So National Collaboration Program, we went out to member state with a survey. The survey has been analyzed, the response to the survey has been analyzed, and we are now in a position to present some of the results. These also involve the expert for training, so that's another area of great expansion, and the thematic hub that will be pre-launched here and then launched at the Space Week in November in Seville. So major area of development, area to watch in the next few months. Probably I wouldn't do a good service to the presentation looking forward if I didn't mention the major revolution that is happening in the climate data store. So the fundamental approach to the way in which the data is cataloged and displayed is going to change and will make the interface even simpler and more accessible than it was today. Interestingly, this slide, which was put together a few months back, and I only partially address, put the 250,000 user mark at the far end of the spectrum, and we are already there, signaling a really speedy transition towards the new phase. So I close here, and I just thank you all very much for your attention. But I don't want to leave the stage quite yet, not because I got used and I don't need to use the remote anymore, but just because I want to express my personal gratitude to Jean-Noël and Dick for having set up the program, because we wouldn't be here today, we wouldn't celebrate these 250,000 users and all the successes that were highlighted in this slide had not been for the passion and the vision you had when this started. So I ask you to join me in thanking Jean-Noël and Dick for their effort.
Thank you very much, Mr. Bontempo, and thanks to the other opening speakers as well, including for being mindful of the time. It is now time for our first thematic session, which will consider reanalysis and observations. The format of the session is as follows. We'll first have 3 presentations, and to further delight Professor Marek, let me also announce now that after those 3 presentations, we have a coffee break. And subsequently, we have another speaker and a Q&A session with all of you. And we do look forward to your active participation in the Q&A session. This is essential for the quality of the discussion. To participate in the Q&A session, if you are in the room, you simply raise your hand the old-fashioned way, and you'll get a microphone. If you are a remote participant, please do join us on Slido. And to do so, you will require a QR code, which I think should be visible shortly, and if it is not visible now, then it will appear at some point. You send in your questions, and our Slido moderator will then ask the questions here in the room. We have quite a tight schedule, and so I'm very happy that the presenters have promised that they will remain within the time limit. Let me then give the floor to our first speaker, who will talk about the reanalysis user landscape, Chiara Cagnazzo of ECMWF. Here she is. Give her an applause.
Yes. Thank you. Can you hear me? Not sure I'm on. Yes, now I'm on. And let's hope this remote control will work. So thank you, everyone, and welcome to the session on reanalysis and observations that has been nicely set up by Hans and Polly, who is here. And I'm also, I'm also a very happy man to acknowledge the many contributors that are behind the slides. So, unfortunately, I'm not going now to talk about the evolution of reanalysis. For this, you have to wait for Hans. But I'm going mostly to focus on the use of the reanalysis. So here I will try to cover a few elements very quickly, who the users are, how reanalysis is used in the selected applications and examples, why they are fit for purpose, and which are the current and evolving requirements. So, of course, being the first speaker of the reanalysis and the observation session, I had to dedicate a couple of slides to the reanalysis, but you know very well what reanalysis are. Here, I would just like to mention a couple of numbers. The first one that was also mentioned by Carlo, there are more than 120,000 users for the reanalysis, and also reanalysis include over billions of observations used so far. And together with the ERA5, the global atmospheric reanalysis, also, the twin brother is the ERA5 land that starts to be quite used by the community, going to higher resolution and dedicated mostly to support land applications. Together with this global reanalysis, there are also regional reanalysis that are important to mention. So regional reanalysis give more finer resolution, so they start to be quite used also by the community. There is, let's say, the added value comes related to the fact that there is a downscaling exercise together with data assimilation of local observations. And during the Copernicus one, a set of European and Arctic reanalysis have been developed. And what to expect in the next phase is that those same reanalysis will be extended somehow, making available more in real time. But also there is in preparation the new generation of pan-Arctic reanalysis with a resolution of 3 kilometers over this larger area that you can see in blue into this slide. So, as said, this presentation mostly focuses on the users of the reanalysis, and there is this, let's say, complex exercise that through the user engagement, we try to, let's say, understand the categories of users. It's very difficult, and maybe there are many gray zones, but let's say we can say that there are categories of users mostly interested in doing science, so researchers, but also there are users like professional consultants. Those are experts in a specific domain, and they use the reanalysis because they know very well which are the challenges that their industry is facing, and they use the reanalysis for answering questions to put the data into their workflows. There are big data experts that are skilled in playing with the data, handling large volumes of data, visualizations. And I'd say that those three categories of users mostly are interested into the data as they are offered into the catalog, the CDS catalog, but also other categories of users such as journalists and policymakers who mostly use the reanalysis for, let's say, corroborating their stories or their decision-making, and the general public who mostly use post-processed information, not really data from the reanalysis in the climate data store. So there are many areas where that, reanalysis are used in many different areas, and again, those are grouped in big categories. So for example, they're used to obtain this three-dimensional synoptic scale situation, or as Hans says, the weather of the day. They are used to obtain statistics of climate-related extremes, to compare the current situation with a consistent 30-year climate of the past. They're used to estimate variability of the mean state and long-term changes, to provide also initialization to other model simulations, and more recently to train machine learning weather prediction models. I will try to give you just a few examples based on what is available at C3S in the climate data store. This first example, the figure is very small, I'm sorry, looks at a catalog of wind extremes based on the reanalysis. On the top left, you see the reanalysis. ERA 5 is used in this case to track storms at the mid-latitudes. And then this information is coupled together information about the wind gusts, so extremes in the wind. And they provide these orange maps that are footprints. So for each storms, there is an indication of the area affected by the storm in terms of the extremes in the wind. And in the middle panel, you can see this kind of orange area that gives, for a specific storm, this higher resolution information on the extremes in the wind, because the data are downscaled and bias corrected to go to higher resolution. And then downstream, this information is used, for example, by the insurance sector to make estimates like losses, estimated losses associated to those extremes in the wind. So in the climate data store, you find some information about that. So catalog of windstorms, specific indicators that are relevant also to the insurance sector, but also a catalog of synthetic events that in practice makes more robust statistics. So those are physically realistic set of plausible windstorms that didn't happen, but they could have happened, and those are based on the climate conditions. There is a current activities to extend this, and you will have more information if you go to the poster by Lorenzo. The second example, if I'm able to go there, oh no, sorry. First, just a summary of what are the requirements that come from this community of users. So, from this community, there is a need to have an accurate representation of the current weather of the last 50 years. So this is used to prepare this catalog of events. That is important not only for the insurance sector, but for many other applications that needs to estimate, for example, the risks on windstorm extreme events and the damages associated. So for example, forest sector, infrastructure, agriculture, and so on. And the other need from this community is to increase the sample size of the historical weather events to create more statistics. And this, in practice, means developing methods to have catalog of equally plausible versions for the past. And there are different methods that are developed so far using reanalysis and, for example, the seasonal forecast of the past. The second example looks at the energy sector and is looking at the climate reanalysis for the energy sector that is used for doing what? First is used for doing monitoring, and this comes from the last European State of the Climate 2022. Carlo mentioned it, you will know more in the next session. And this looks, of course, at specific meteorological conditions. In this case, the wind is used that is relevant for this community of users. And then these meteorological data are connected to specific energy indicators. And in this case, this is actually related, for example, to potential production from onshore wind, from offshore wind, for solar PV technologies, as well as electricity demand. And this is indeed used, to understand, for example, how the variability affects those energy-related indicators and how this is put in the context of the long-term climate. But such a climate information, climate reanalysis for the energy sector is also relevant for other typology of applications in the energy sector. And this is another example where reanalysis also are used to support the European network of transmission system operators to deliver these pan-European outlooks of the power system to the short and the long-term scale. So to understand if there are conditions by which you can have low production of energy, but at the same time from renewable sources, but at the same time you have high demand. I invite you to go to these other presentations to learn more. The next example, sorry. Here now I would like to collect and summarize which are the requirements from this community of users. So first of all, these users need a consistent representation of a temporal trends for the last 30 to 50 years. Think of the monitoring exercise. And this means a lot of challenges. So one of the challenges dealing with the changes in the observing system, that is within the reanalysis. Also the challenge of having the possibility to estimate an uncertainty that reflects those changes in time. Characterizing the mean state uncertainty. But also, these users will benefit a lot if we can go toward a consistent and updated temporal evolution of the boundary forcing as it is planned in the next generation of reanalysis, together, of course, with higher resolution and dealing with biases. The next example is about and focuses on the agriculture sector. Here's just quickly to advertise this Ag ERA 5 open data product based on the reanalysis. This is dedicated to the agriculture impact modeling running crop models. And the need from this specific community of users is really to have a global reanalysis because, for example, when applied to the food security problem, this problem is local and global at the same time. For food is produced locally, but then it is consumed globally. And then this group of users will benefit from improved, for example, land cover and vegetation from the next reanalysis. The next example, very quickly, is an example looking at the policy-driven needs. And this is, as Carlo also mentioned, the EU developed a directive on emission reduction commitments from member states. In practice, member states have to commit to reduce emissions, and they have to report regularly to the European Commission. And there is a specific article into this directive that implies some flexibility in this reporting. So if there is an exceptionally cold winter or dry summer, it is possible to trigger an action and to trigger this flexibility. So there is a need of data for doing this exercise. Of course, those data have to be reliable, have to be authoritative. Those are the database, for example, for our climate monitoring, and everything should be transparently documented. This is the snapshot of what was produced in this regard, but what I would like to highlight here is just that the need from a policy-driven kind of application is to have quality-controlled data and processes, authoritative information, but also continuous with respect to the policy cycles. The next example was looking instead on supporting, on the climate monitoring for the adaptation context. And here is to support the European Environment Agency in their EU mission on adaptation. And actually, I cannot go into the details of that because my time is almost gone. But please go to Sam Almond's presentation poster and maybe some elements in Julie Bergman's presentation tomorrow. And then again, the set of needs from this set of users is that often there is the need of a reanalysis that is consistent in the representation of different components because those indicators, cover different areas and domains. But also, reanalysis here are used to connect the historical climate informations to the climate predictions. And so there will be large benefit of, for example, tools close to the data to downscale and bias adjust. At the same time, benefit if we go toward improved forcings in the next generation of reanalysis. I think I need to skip this and go to my conclusions, but please follow the online, again, follow the presentation tomorrow. And the last slide, again, follow the presentation of Matthew that is happening later today. This is I'm looking at the new use of the reanalysis, and in this case, Matthew will show how ERA 5 is strong and powerful in training accurate weather forecasting models. We do not know yet which are the requirements from those community. So my key messages are that there have been significant advances in the evolution of the reanalysis, and this is why reanalysis are one of the key data sets used in different climate applications. There is a strong benefit with a continuous analysis of those user requirements. And finally, there are a lot of challenges, technical and scientific challenges in the production of new reanalysis. And lucky me, this is a problem for Hans, probably, and also on how they are served. And there are also a lot of opportunities behind that. Thank you very much.
Many thanks, Chiara. If you have questions and you're an online participant, please send those in using Slido. You can do so whenever you want, and we'll try to address as many of those as possible. Our next speaker will talk about ERA 5, the story so far, and plans for ERA 6. Hans Hersbach, ECMWF.
Good morning, everybody. Let me see. Yeah, that works. So I'm in charge of the reanalysis team at ECMWF. We are producing the ERA 5 reanalysis. We're preparing for the ERA 6 reanalysis. We are also do the technical contract management of part of the regional reanalysis, and in situ and satellite reprocessing data sets that we need for our next reanalysis. So there's many people involved, which would like to thank here. So my overview is ERA 5, the story so far. Then I will talk about ERA 6, what we are doing at the moment, the preparations, and I will give a summary. So my presentation is it's not too technical, not too many nuts and bolts will be shown. So, but if you are interested in those nuts and bolts, last week we had the annual seminar at ECMWF, and I was on Earth system reanalysis. There were many presentations, also on ERA 5 with much more details, scientifically as well. So they're all recorded, so if you're interested, you can have a look at them. Okay, so yes, I have the same problem. Oh, yeah, exactly. How do I go back? Yeah. So ERA 5, what is it? So that's where it sits in the climate data store. Reanalysis, we have observations, and we also have predictions, projections. So it's a full observing system reanalysis. So we use all the observations we can use for the atmosphere, the land surface, and the ocean waves. So these three components at the moment. So what happened in the last year? So we have about 128,000 users now, up to, and I checked last year's GA slides, then it was 88, so we gained 40,000 in 1 year, so it's 50% more about. We have more than 100 terabytes of downloads a day. I think this is already an old number, so it's more now. So we were able to complete a further back extension just before they unplugged the computer at Reading, which was quite challenging and hard work, but we managed. It was, because at some point all the tapes that we need that have the archive, they were on the back of a lorry to Bologna, and we were able to continue our production and things we couldn't do because they were on the tapes of the back of the lorry. We could do them once they were uploaded again in Bologna. So, but it all worked at the end. Then also, so now we have over 83 years of hourly data from 1940 until 5 days ago, because we have this ERA 5T service, which Carl already mentioned, was migrated without disruption to users, so they didn't notice anything. Also, the ERA5 LAN-T service was introduced in December. And also, last but not least, we are maintaining the ERA5T observing system. And we're following our NWP, TSMWF. Whenever there is a new satellite, a new type of instruments, of in-city data, we try to ingest that in ERA5 as well to keep the observing system up to date, because at the end of the day, the quality of your reanalysis is determined by the observations, because without the observations, you're nothing. So that's what we're doing. Then the ERA5 scientific journal paper has now topped 10,000 citations, what actually happened, the 10,000 mark was hit yesterday evening at our dinner. So it's 10,000. And we are nearing completion of a paper that describes the latest back extension, but also gives a whole overview of the full 83 years that we have so far. Okay, then quality. So Carl already showed that. So what we do, so ERA5, it's a reanalysis. We don't do it's not a forecast product, but we always make forecasts as well in our production, because that's what we do at ESMWF. Not so expensive to do. And they're very useful for verification. So that we've done here. So Carl already showed you that you have this older reanalysis like ERA15. So basically what you see here is that how many days are you able to produce an excellent forecast? In some sales score, which is 95%. A good forecast is 80%, or a reasonable forecast, which is 60%. And you see that Carl has showed already, we have this older reanalysis. Every time we have a new generation of reanalysis, we are increasing the number of days that we can forecast. And of course, that depends on the quality of your analysis. The better your analysis is, the longer your forecast will be valid. You also see that ERA5 is by far the longest reanalysis that we have produced with a full observing system. Okay, we had Centennial, but that only used a subset of observations. That incorporates all the other reanalysis. Of course, you see that when you really go back in 1940, that the scores go down, but still we're able to do, of the northern hemisphere at least, to do a good job for the synoptic accuracy. An example is this extreme storm in February 1941 that hit the Iberian Peninsula. Of course, but over the southern hemisphere, it's a completely different story. If you go before the satellite era, 1979, then the skills really drop down. It might be clear here that really we want to get the scores up. You do that by having a better model, using more proven R&D, but also we need more observations, especially in the early period. Okay, so preparations for ERA6. So all these pop, but that doesn't work. But it's good because I don't have to press 10 times. So we're working on that. So there's a what does it entail to set up a new reanalysis? So there's a number of elements. So of course there's configuration. What kind of resolution are you going to run it at? So we're testing both 18 kilometers and 14 kilometers. Basically, I'm doing most of my assessment on 14 kilometers. So that is about double the resolution of ERA5. And also the ocean waves, we will also have that resolution, because for ERA5, the ocean waves are at a lower resolution as ERA5 itself, and users have been complaining about that. And now in the research department for our next NWP system, that is an option, so we're going to do that. Uncertainty estimate will be at 28 kilometers, which is again double the resolution for ERA5. Of course, the configuration depends on how expensive this, can we afford it? Of course, the quality, and also very important, throughput. Because when we produce the reanalysis, we have typically 4 parallel streams. They have to do about 8 to 10 days a day each, and we have to be able to do that on the computer, so it's really important. Okay, then there is, of course, the products, and they are based on user requirements. So hourly data, we have an extended list of new parameters. Relative 2-meter humidity is something that people want. Then clear air turbulence, that is a user requirement that came from our NWP users, and in our NWP, they have now implemented that, so we have it. So we just tick the box, and we can also now use it for ERA6 as well. Then we want to have height levels for the lowest part of the atmosphere, because at the moment there's only pressure levels in the vertical, and that's not really easy to work with when you're a non-technical person. Daily pre-calculated statistics, people have been complaining that hourly and you have monthly means, but hourly is a lot of data. We want to have daily statistics as well. Then we want to ingest the best observations. So these are the satellite reprocessed data set and data rescue and in-situ data that we are working together with our contractors. And of course, we have to enhance quality control. Then there is also technical code management, suite optimization, make sure that we can run 8 days a day in each stream. And all products have to be in grip too. So that's a new format, and yeah, that's also a lot of work. Of course, then we also have to monitor the whole suite because that we do very actively in the production of ERA 5, so that we can catch things that go wrong in an early stage, so that we can still correct them before we make the products available to users. I think that's really important that you do that very carefully. And then finally, of course, should have put it at the top, latest mature science plus reanalysis specific developments. Okay, so going to this science, so just give you an idea of what we have been doing at ECMWF so far on reanalysis. We have a very long experience. ERA 5 is land, atmosphere, and ocean waves, but we have run reanalysis in many more domains, so like atmosphere composition as well. So where we go now next is ERA 6, and what ERA 6 will use, we also have this ocean reanalysis. There will be a next generation ocean reanalysis, ORA S6, Ocean 6, and that will be coupled with ERA 6. It will not be a full two-way coupling, it will be a one-way coupling, so ERA 6 doesn't feed back on ERA 6, on ORA S6, that's more for the future, but we will get a lot of benefits from coupling with the ocean. Okay, so just a little bit overview what kind of ERA 6 science and innovations we have. There are reanalysis dedicated innovations. So the first bullet point is also for NWP, but we will use this before it will be used in NWP, although we will go through a very rigid research to operations evaluation of this. So establish the level of coupling of this ORA 6 ocean reanalysis. I will not go into the details because I don't have time for that. In my presentation last week, I give some more details. Then systematic model errors is very important. Carlo already showed it a little bit, especially in the historical period. So basically we have a systematic model error, and when you have reanalysis, when you go very far back much in time, when you don't have many observations, your reanalysis, the mean state of your reanalysis is more governed by the state of the model, and when you have a lot of observations, is more governed by the state of the observations. And when they're not really well calibrated, you get that can affect climate trends. So, and we're doing already a good job at ERA 5, but we can do better, and that we want to do in ERA 6. So that's what that is about. Then we want to improve also the uncertainty estimate, because people tell us that our ensemble spread is too low, which I think is correct. And also resolve a number of ERA 5 known issues where possible. So some of the known issues we don't have an answer to, but a number of them we have an answer to, so we need to address that and make sure that it's sorted in ERA 6. Then we, of course, at ECMWF, a lot has happened in the last 8 years, so our NWP model has improved a lot, and we can benefit from that. So we get an additional 8 years of R&D, and there's many things. So just a little selection here. So we can reduce biases in snow and improve assimilation of snow observations, because snow, we get complaints that we have too much snows in mountains, so we know that, so that should be improved. Extreme ocean waves, because at the moment the relation between, we are not able to create the extreme waves, I think in ERA 5 as we should do, which we can improve when we have this improved drag. A new ozone model, we have a revision of the moist physics that should have a positive impact on, for instance, radiation budgets, for energy sector, that should be beneficial. Then vegetation cover and type, that will be, we will use a new data set Potentially, but that's more a bit unlikely. We might also be able to evolve them over time. But if we would like to do that, then we would need more time to implement that. Okay, so my final slide. We have hourly snapshots. Some of the quality evolves over time. When more observations become available, there are boosts, and they follow the boost and observing system. The mean state for climate trends, I think for temperature from the lower stratosphere downwards up to the troposphere and the surface, we're doing a very good job, I think. But there are like other quantities like humidity where it's still more challenging, but we're working on that. Yeah, we're preparing for era 6. Then when we go one step further, we're also already thinking about era 7, next generation. And actually, we're making use of a lot of funding also as well from ESA, European Union project, really to go to a more fully coupled system. Okay, well, thank you very much.
Thank you very much, Hans, and congratulations one more on hitting your landmark objective. Thanks a lot. One more applause for Hans. Our next speaker works at Maynooth University, and he'll speak about the contributions of C3S to the global climate observing system. Peter Thorne.
Thank you, and I'm here not in my Maynooth University capacity, but because I'm the chair of the GCOS Atmospheric Observations Panel for Climate. And we'll see whether I have more luck with the slider than Carlo did. Firstly, to orientate you, the big thing that really Copernicus and any other program should be responding to is the implementation plan. And I must first thank Carlo for being an active participant in the drafting of that plan. It was enormously beneficial to GCOS to have the expertise of Carlo in the room. So these are produced every 5 to 6 years. They're submitted to the UNFCCC and the GCOS sponsors, and they provide the recommendations for a sustained and fit-for-purpose observing system, global observing system. They cover climate monitoring needs over the entire Earth system, from the atmosphere to the oceans, from the cryosphere to the biosphere, and they encompass the major cycles in the climate system. And we have listened. In the past, our implementation plans have been huge. They have been 300 plus actions. And funders have quite rightly gone, well, which of your 300 actions actually matters, folks, please? Tell us which one matters. We tried to get much more integrative, much more selective this time. There are clearer means of assessment, so we will know whether funders, governments, international organizations have stepped up to the plate or not. There's a clearer identification of stakeholders. And we hived off the ECV requirements because it was then larger than the implementation plan itself. So this thing should not be an onerous read. You should be able to read and comprehend this within an hour or two, certainly within a morning. It is not that doorstep that we have produced in the past. I'm not having any more luck with this than anyone else. There you go. So we have a cycle of monitoring the climate observing system, which has at its heartbeat a status report, which looks back and says, have we done everything we said in the last implementation plan, and then the forward-looking implementation plan. There is extensive consultation. It's drafted by our expert panels, of which there are 3, the atmospheric that I chair, the oceanic and the terrestrial. And it's an iterative process that goes through, it's not quite IPCC, but it is a public engagement process. There you go. And they're right, we condense this down thematically, and we think this is really important to come up with themes. And the first theme is do no harm, ensure sustainability, protect what we have. Don't go into actions to produce shiny new baubles and forget about the baubles that are already hanging on the Christmas tree, because we really need to protect those. Fill the data gaps. Improving data quality, availability, and utility, including its reprocessing. This is where reanalysis comes in. Managing the data. There's no point taking observations and not thinking about the people who will follow us. They will curse us if we have not curated the data well. It is extremely unsexy stuff, but it is the stuff that in 20 or 30 years will matter. Our shiny new products today will not matter at all to people in 20 or 30 years' time. They will curse us to the end of time if we do not retain the fundamental climate data record in good shape so they can produce their products and services in 30 years' time. Engaging with countries, we need to do a better job, and we need to look at emerging needs. And again, we're going pointer. So these are just a selection of them. I'm not going to read them through. All I want you to notice the number of these turn red when I click, and hopefully it actually works. Click again. Oh no, we didn't go there. We had some of them go red. These are just the ones off the top of my head that I believe C3S is contributing to already. Bear in mind this implementation plan followed rather than preceded all of the launching of the vast majority of contracts under C3S2. So you're already contributing. There is certainly space for additional contributions. And we will again play the pointy clicky. Someone needs to put a new battery in this in the break. Who has to act? So these are our actors that we have put. We have not got C3S named here, but I would say C3S does fit really into 4 of these categories in various ways, shapes, or forms. So it is an actor against the GCOS implementation plan. GCOS will monitor progress. GCOS is an active participant in some, but the vast majority of this requires third parties to GCOS to step up and act. WMO, National Meteorological Services, the space agencies, but reanalysis centers, global data centers, research organizations, funding agencies, these are all things where arguably C3S falls in various ways, shapes, or forms. And we'll click the sticky pointer. So I'm just going to finish with some examples. And Carlo touched upon this first example, and this is one example where we're talking about the future researchers. So GNSS precipitable water measurements are measurements made from monumented receivers on the ground of time delays to various satellites, navigational satellites. Their noise, because these are not maintained typically by meteorological services, their noise is our signal. They're actually after things like geological movements, earthquakes, detecting whether a volcano is growing or shrinking, therefore whether it's going to explode or not. They're interested in a whole bunch of other things. So they have not worried about the preservation of this and the sharing of it with the climate community, but it has proven remarkably valuable from NWP and therefore reanalysis and in its own right in climate. We have a formal agreement whereby C3S will act as the formal global fundamental data repository, and this is the fundamental repository. This is not creating shiny products. This is retaining that raw data that means in 30, 50, 100 years' time, somebody can come and reprocess that data. There is a contract in the in situ family that is building incrementally that global archive. It requires brokering those agreements. The fundamental RINEX files are what will be preserved for perpetuity. C3S will, of course, also make value-added products, but from GCOS's perspective, it's that fundamental data record preservation that matters. We'll play sticky pointer again. There you go. So the next is rescue of in situ and satellite data. So we have made many observations that costs of billions and billions of euros, and a large proportion of those are not exploitable for various reasons, but principally they are, in many cases, it's because they remain in inaccessible formats or inaccessible to the community. Through both the C3S phases, significant progress has been made in the rescue of both in situ and satellite data. For example, in the last contract, C3S brokered access to the ACMAD collection of fiche and microfilm data and rescued those at least to image stable electronic image form. These were in danger of atrophying to vinegar and being unusable. We would have lost a huge amount of information on African data. Now, we haven't yet rescued that and have it available in machine-readable format, but we have at least got the possibility down the line to rescue that and put it in machine-readable format. Much work does remain. You can see our poster for some details on the subsequent rescue activities, and if you're in academia and you want a nice piece of participatory learning coursework, trust me, there are millions of images to go through. You can give these to your class. They give them the opportunity to rescue the data. And this is scalable in theory to secondary school. Wouldn't it be cool to have every student, 16 plus, digitizing some data as part of their coursework, owning a part of the global climate data record? Much work remains to be done, particularly for in situ data rescue. There is a parallel session tomorrow. I would urge you to come to that. We really need to shake down some ideas. There is a huge number of bottlenecks in here that need to be unstuck. A third example, the AOPC task team on Lightning, so task team under my group, requested help to secure a repository of Lightning Day data. This is a binary data set. Either Thunder was heard or Thunder was not heard. So it's Thunder Day database, sorry, not Lightning Day, it's Thunder Day database. It precedes the spherics-based and satellite-based data. So if you want to know very long-term Thunder activity, this is the only show in town. Did the synoptic station observe or not hear thunder during the day? As a capture of opportunity, we offered to the Lightning task team to bring it in through the C3S data deposition service. We have curated it at the moment. That's all we're doing with it. But in theory, it's exploitable in future in myriad ways. So we have a stable repository for it. And then coming to the last and the biggest example is the provision of improved reanalysis products. The operationalization of global and regional reanalysis products production and provision is a major response to the IP already. Learning through doing leads to improved quality products with each cycle. And the underlying activities are, if anything, as important. They speak to things like fundamental climate data record preservation, improvement of in situ holdings. They are enormously valuable. And finally, we're greatly appreciative that C3S hosted the recent joint panel meeting at the Bonn facility. The excellent organization was second to none. The active participation of a range of C3S staff greatly improved the meeting outcomes. So thank you very much, Carlo and colleagues, for hosting it. We're also grateful to C3S staff in active engagement in our panels and steering committee. We will have a new task team on ECV rationalization, which I hope C3S will also play an active part in. And that's it, and if I go to that, that's the final slide. Thank you very much.
Peter Thorne, thank you very much. So it is time for our first coffee break. Coffee will be served right outside the room. I'd like to ask those who will be on the second panel to come to the stage for a quick chat with me before they take their coffee. Please try to be back in the room no later than 10:40, so we can start on time. Thank you very much. Quick note, apologies, I said 10:40, but I meant 11 and 10 minutes. But I guess you figured that out. Many thanks. Oh, I'm very sorry. It was okay? Mic check, mic check. Okay, everyone. Please take your seats so we can start. Thank you. Precipitation. So, welcome back. We will now continue the first thematic session. We have one more speaker left before we have a Q&A session, and we very much look forward to your comments and questions. So you are encouraged when you're online to contribute your comments and questions through Slido, and when you're in the room, there will be a microphone. You can raise your hand and we'll get to you ASAP and listen to what you have to say or ask. Our next speaker will talk about evaluating Era 5, precipitation, and an opportunity for a future improvement. Working at ECMWF, I'm happy to give the floor to David Levers. Give him an applause, please.
Well, good morning, everyone. It's lovely to be here with you this morning. Wonderful, thank you. As I say, good morning, everyone. Lovely to be here. Nice to see old colleagues and new colleagues and new friends, I hope, as well. So thank you, Ali, for the introduction. So I'm going to present some work in threes here today. So it's evaluating Era 5 precipitation, and then also an opportunity, as has just been introduced, for future improvement. And the three different topics I'd like to introduce to you. Number one is, where do we use Era 5 precipitation in our climate monitoring activities? And I should highlight as well, this is kind of a bridge talk. So I'm bridging between the reanalysis and all of the hard work and dedicated research that's done there, and then towards the climate monitoring work and the climate intelligence team, which will be the next session. So I'm kind of the bridge between the two. So the first one is, how do we use the information you've seen in the first session, which I'm still in our climate monitoring activities? We don't just do monitoring, we also try and do research and evaluate the tools and materials we have to see what more can we say about the products we have, what confidence can we have in these products. So I'm going to go through briefly an evaluation of Era 5 precipitation against station observations. And then finally, we know that with Era 6, which Hans introduced earlier, that there will be improvements in model physics, in the grid resolution, which will give improvements in precipitation. But in the meantime, or potentially in Era 6, can we get a more skillful estimate? And I hopefully will show you that there is scope for that as we go through it. So the first topic, what do we use Era 5 precipitation for? That is the European State of the Climate Report, which has been introduced by Carlo. It will be introduced by my colleague Rebecca in the next session. So this is just to show you the 6 different reports that have been done so far. These are the front covers from the top left to the bottom right, the latest in the bottom right, which was released in April of this year. And just to highlight to you one of the results from that study, this was the first figure of the precipitation section. This gives you an idea of the different data sets we use. We use the Era 5 reanalysis. So in the top row, we're looking at the annual precipitation anomalies across the European continent from 1950 to 2022. We use Era 5, we also use the EOBS observed product and the GPCP as well. And generally there's a good relationship between them, which gives us confidence in what we see in Era 5. And just to highlight in that top panel that last year, as you may well remember, was a pretty dry year, and certainly dry compared to the 50 years previously. And then just showing in the bottom panel, we don't just look at the annual, but also the monthly. What is the variability in the precipitation that we see? So firstly, we use it in the European State of the Climate Report, which will come up later. Secondly, these results literally were released last week. This is our monthly product, so we do monthly climate monitoring as well. This is just showing you the precipitation anomalies from ERA 5 again, in terms of global plots. So the European domain on the left as you're looking at it, and if I can ask you to look at the North Pole perspective, polostereographic in the middle, and then the South Pole on the right. And just to pull out a few main events for you in terms of monitoring, so if I ask you to look at the left-hand side, Slovenia was hit by some devastating flooding, which you can see, and surrounding areas as well, which you can see on the left-hand side. Also, the Nordic countries had a very wet period, which comes out very clearly. So again, this gives us confidence. We see what's happened, not just in the news, but in flooding products, but we see it in ERA 5. And I'd just like to draw you to one other event. If we look at South America, so we're interested in global events as well as Europe. If I just ask you to look at the right-hand panel, just on the Chilean coast of South America, you can see quite a distinct spot there of intense rainfall, and that was to do with an extratropical cyclone and an atmospheric river that affected that part of the world. So, as I mentioned, we're also interested in evaluating precipitation. So I come from diagnostics and evaluation as well as climate intelligence, so it's trying to bring these two fields together, or areas together. And this was a paper last year with Adrian Simmons, Freya Van Boy, and Mark Rodwell, and we were interested in trying to show what can we say, where can we have most confidence in ERA 5 precipitation. It's produced everywhere, so what can we say in terms of products and then in terms of our monitoring? And if I just go to the next slide, I'll just give you some large results here. The first thing, what I'm showing you here, this is, to be precise, 5,637 stations. You can tell I've looked at it a lot. These are all over the globe, so we've got a good global coverage. It does come back to a point that was raised in the last talk. There are certain areas which are data sparse, which you can see on the maps, but generally there's a good coverage. And this is a 20-year period. I'm just showing you the mid-season months of January, April, July, and October. And the first result, most of these stations look quite blue, which means that there's a slight wet bias. So this is a forecast minus observation. This is a mean bias over those months. And generally, there is a slight wet bias at these stations. For the sake of time today, I'm just going to highlight two other main results here. The first, if I just ask you to look at the bottom left-hand panel, so this is for July. And if we first look at West Africa, there's a dry bias in ERA 5, so we don't produce enough rainfall in that region, which partly to do with the convection in that area. This is hypothesized to be improved in ERA 6 with the improved moist physics scheme. But then the other very interesting area is the USA-Canada border, and it almost looks like a different bias as you cross that border, which doesn't look quite natural. Hypothesis is, or there are two. Number one is that, and it does link quite well, and that's in terms of we don't have irrigation in our ERA 5 system, and the dry biases match up quite well with soil moisture biases and then areas of irrigation, so we don't have the correct soil moisture. The other one is potentially the assimilation of NEXRAD radar, which is on the US side of the border, not on the Canadian side, which does kind of tie up there. So that's just a few interesting results there. And as I say, we're really trying to get into the diagnostics of why, and then we can try and improve. And then if this will play ball. Yes. This is another metric evaluation tool. This is the root mean square error. So this is now looking at that metric across all of these stations, again in the mid-season months. And I'm just going to do this very briefly. So generally in the northern hemisphere, so if we just look at Europe and let's look at January, the errors are quite small. Mostly red colors, so we're looking at very small standard deviations of the error. So this is a random error compared to the mean bias before. As we move to the northern hemisphere summer, so if we compare the two left panels, if we go from A down to C, the error does increase at this time of the year, largely to do with smaller scale precipitation systems, convection, which is more difficult and challenging for the ERA 5 system to capture. But what we find is that the extratropic scale never drops as low as what we see in the tropics, where we have hurricane activity, tropical cyclones more broadly, and more convection. And one area I'll just pull out, so if we look at July in the bottom left, you can see Southeast Asia has a really big issue with the monsoon and the Mayu front. And this area does actually move. So if you, again, just compare panel A with C, we see that the errors are mostly from northern Australia across Madagascar, Africa into South America. This then shifts with the season up in towards the northern hemisphere, which follows the ITZZ, intertropical convergence zone. Now, moving on. So based on all of that, one of the questions that we were asking in the team is, can we improve the ERA 5 precipitation estimate now, as opposed to waiting for ERA 6, which we all look forward to, but what can we do now? So with colleagues, Hans Herzbach, who I'm very grateful to for the discussions and the ideas around this, and Adrian Simmons and Mark Rodwell, again, what we've done here is, at all those same stations, we're using the same observations as I've just gone through in that last study. What we're doing is not using the ERA 5 precipitation from a short-range forecast, which we do currently. We are looking at the last trajectory of our data assimilation system, the 4DVAR assimilation system, to see, is this more accurate? And the reason why we think it might be, well, it is, as I will show you in many cases, is that it has assimilated observations. So you're drawing the product closer to observations, which then should be slightly more skillful. So in this bottom, big panel here, the big map panel, this is for all days over a 20-year period, the same number of stations again, and this is the relative percentage difference of the root mean square error in the ERA 5 precipitation estimate from 4DVAR. So that's this different method. So it's got a slightly lower lead time or shorter lead time. And we're looking at that compared to our current formulation, our current computation, which is from the ERA 5 short-range forecasts. And this is the relative percentage difference. So wherever you see blues, this means that the ERA 5 4DVAR precipitation is more accurate. So there are lower, and this is the root mean square error, so this is taking into account mean biases and random errors. And the statistic is that 87.5% of these stations over all days give you a more accurate estimate compared to our current methodology. And just on the right-hand side, to summarize, this is a box plot just to show you the distribution of those relative percentage differences at all those stations. But what I would just like to show you on the next slide, which has gone on too far, I think. This is okay, so the animation isn't working, so I'll just talk through it for you. What we've done here is we've looked at what you call the stable equitable error in probability space, and I am not going to go through the details of that now with 48 seconds on this clock. What it is, it's looking at how does ERA 5 discriminate different categories of precipitation. So these are dry days, light precipitation days, and heavy precipitation days, and we can discuss that after this. What it shows here, sadly this animation isn't working, is that numerical weather prediction models do have what they call a drizzle problem, so you can get too much light precipitation on a dry day. And we do find that across Europe, that by using this new 4DVAR, or this 4DVAR computation, there's a slightly higher wet bias, so we overpredict rainfall on dry days. The flip side of that, the benefit of that, is that we capture the heavy precipitation better. So this is, again, relative percentage difference that you see on here, and this is showing you that on days where we have heavy precipitation and light rainfall was forecast, we get it better in this new product. So there's a good trade-off in that one there. And just, because I am out of time, just to run through these very briefly with you. So ERA 5 precipitation is used broadly in our monitoring activities, state of the climate, as well as the monthly bulletins, which have just released last week. We can have most confidence in our precipitation in the extratropics, less confidence in the tropics. There is an alternative precipitation estimate which we could consider, and it's a possible consideration for future activities, whether that's monitoring now, ERA 6 in the future. And on that note, thank you for listening. and I hand over to Ali. Thank you.
Thank you very much, David. I kindly invite you to take your seat at the front, and the same goes for the other speakers. Please join us on the stage. That is Hans, Chiara, and Peter. So we can start our Q&A session. As I've noted earlier on, if you are joining us today online, then please join us on Slido to ask your questions and make your comments. Hans, if you will, please join us on the stage as well. Such a modest man, Hans. And you are highly encouraged to contribute to this discussion, as that will ensure a higher quality. Raise your hand if you have a question. Excellent. I see two at the front. Could we have a microphone? And we also need a microphone at the stage, apparently. So one hand went up there at the third row from my perspective. And I kindly ask you to keep your questions concise so we have more space for input. What's your name? Hold on a second. Let me see if you're amplified. Now
Okay.
repeat, please.
Repeat or
Yes.
Barbara Früh from Deutscher Wetterdienst. My question goes to Chiara and maybe also Hans. So I was surprised that you said reanalysis can also be used in the context of adaptation, and there I would be very hesitant to doing that because, well, we know that climate is not stationary and therefore it might be difficult. So just want to know your thinking on that.
Chiara. I think it's on.
Okay. Yes, thank you very much. Yes, thank you for this question. So in the adaptation context, so the use of reanalysis is mostly done to define specific references, time periods, that help to connect what happened into the past climate and the historical climate with respect to the climate projection scenarios. And I agree with you that, I mean, having this non-stationarity is, of course, the non-stationarity of the climate is one of the key elements into the climate adaptation. Yes, of course, and this has to be considered. So this is why I think a nice and a seamless connection between the climate projection and the different scenarios with their own uncertainty and an historical definition of reference climate is one key action that can help by merging and by putting together information coming from both the reanalysis and the projections. And maybe another element is that for this climate adaptation context, there is a need of defining information coming from different elements, from different components of the Earth system. And this is why having this more consistent development of reanalysis that takes into consideration more components of the Earth system at the same time may be beneficial for the exercise of responding to the needs for the climate adaptation exercise.
Many thanks, Chiara. Let's take a note from... Yes.
Hello, thank you. I'm Anka Brookshaw from C3S. I have a question for David and maybe colleagues who work with him. You told us about this alternative to the direct precipitation output from ERA 5. Do you have a plan as how to deploy this? Because we know ERA 6 is at least 3 years away for users. Is there any discussion yet as to how that might be deployed throughout the timeline of ERA 5 and indeed used?
Anka, thank you for the question. There isn't. Hans and I have literally just finished the work. It's under review currently. We haven't had those discussions other than that the opportunity could be there. But I'd be very happy to have those discussions. And maybe Hans has something to say. Thank you for raising it.
Yeah, so what David showed today, these data, they're all available as well, but they're not on the regraded data set, but in the data set called ERA 5 Complete. So there we have everything. It's just that at some point when we produce ERA 6, we have to make the decision what is the most suitable choice of these different alternatives we have to make available in that easy to use regraded products. And that's why we start to store all these alternatives, from the last trajectory, because there we also have that information, so that we can make up our mind and to reconsider maybe for era 6. But precipitation, there's many more other fields than that. And of course we want to make sure that we're making the right decision, so you have to do it really carefully. But at the end of the day, all this data is already available in era 5. It's just that in the recreated data set, we chose to use the short forecast rather than these data sets. So it's accuracy, which is important, but also spin-ups. So these when you look in this last trajectory, you will suffer more from spin-ups, and that's why we chose to use the short-term precipitation, because there's less of a spin-up.
Excellent, thank you very much. We'll have a question from Carlo, and then maybe we take a question from the online audience.
Yeah, I think I put it online as well, so it counts one fewer from the online. And my question, I guess, is from David, for David and possibly Hans, because in your plot on the bias for precipitation, the northern Sahel was sticking out as a dry bias.
Yes.
And then you sort of described the bias also in the Indonesian region and in India. And I was wondering whether there is, in your opinion, a systematic behavior of the reanalysis in the monsoon region, or whether it's something specific to the Sahel that is problematic.
So the monsoon in Southeast Asia?
Well, monsoon in general, the monsoon process.
So generally we have a wet bias in the monsoon area. So, and this again, there are many hypotheses of what this could be. So basically what we could see is that there's far too much water vapor transport across the area, and then there's too much rainfall. Generally, as I say, it's a wet bias. Could be to do with the resolution of the mountains in Southeast Asia, which means we then get too much spillover of moisture into that region, which then gives you development, convective activity, but we haven't got to the bottom of what that problem is. But it is a big issue, and it's not just a mean bias, we also see this random error. So trying to get that region correct, it's a challenge, but certainly something that we are thinking about, Carlo. Yeah.
Thank you very much.
Okay, so we have a question online, so it's coming from Adrian Simmons. It's for Peter, and I think he's challenging your statement that the new GCOS format is better than the old one. He's asking, the briefer GCOS plans and reports are easier to digest, but are they as helpful as points of reference for those working directly on improving observations?
So this really depends upon who are we aiming the GCOS implementation plan at. Is it so everyone has something that they can point to in a national funding call? Or is it to really try and make the difference that we can, the maximum difference that we can? The Global Climate Observing System, despite its name, does not actually de facto make any observations, with the notable perhaps exception of the GCOS reference upper air network. So we're advocacy, and really the question is, if you create a very big, deep book with 300 plus recommendations, is that actually going to get traction versus a smaller piece with fewer, more integrated actions that call out, in many cases, thematic aspects rather than specific aspects? It was a choice that was made by the team this time. The jury is out whether it will be successful in seeing more action. The proof will be in the pudding when we come to the next status report and we see whether there has been enhanced uptake and whether there is a greater degree of progress seen between the implementation plans. So like in anything, like in my experience in IPCC and different assessment cycles, you always are learning through doing. In the same way the reanalysis is, we are in GCOS. We think it's better, but we will only know it's better in 4 or 5 years when we see whether there has been enhanced uptake of implementation plan actions and more activity as a result of the way that we have presented them this time.
Thank you very much, Peter. The room's quite rectangular, so let me see if there are questions a little further away from the front, in the area where usually the rebellious children sit in the classroom. Raise your hand if you do have a question. Raise your hand if you have a question, regardless of where you are at the rebellion graph. The gentleman over there. That's also fine.
Okay.
No worries, go for it, and then you'll be after, sir.
Not my fault. I was given the mic. It's just a small comment about Peter's presentation on GCOS, where you praised C3S being very active, and thank you for that. And yes, we take it very seriously. I think the praise should be extended to the European Commission, because they are also putting a lot of resources supporting the GCOS Secretariat. So it is really something that I think should be acknowledged. And I mean, Francesca is here. That's not why I'm saying it. But I think it's an important mention which should be made, because it's actually quite substantial what they do for it. That's all.
Yes, thank you for making that point. And in my time in GCOS, which has been longer than I care to imagine, we have seen waxing and waning in the strength of the GCOS Secretariat, and certainly without the support of European Commission and Copernicus, that's why the branding is on the GCOS template, GCOS would be in serious trouble. So it is absolutely key support, and thank you for making that point.
Thanks, Jean-Noel, for giving credit where credit is due. Yes, sir.
Hello, Jason Box, Danish Geological Survey. Could you just tell us about the accuracy of extreme precipitation in ERA 5?
Probably this is for David.
Yeah, it's a good question. Thanks, Jason. So, I think that you can put this into two parts. ERA 5 picks up the pattern of extreme precipitation well. So if we think back to a very tragic event in 2021, the flooding in Germany, the pattern was picked up really very well in ERA 5. When it comes to the magnitude, because of the grid resolution of ERA 5, and we don't capture all of the physics associated with particular storms, then we can have an issue. We do certainly see that if you look at the comparison of annual maxima in the observations compared to ERA 5, we do underestimate them generally. I mean, that's partly to do with a point observation against a grid, but generally captures the pattern. When you get towards the really extreme end, it could be a tropical cyclone, for example, or an intense convective event, we don't do quite as well, but generally the patterns are quite well captured.
Excellent, thank you very much. Are there more questions, whether online or in the room? Raise your hand, please, and keep it up so I can see it. Brilliant.
Jan Wandel from Deutscher Wetterdienst. I have a question to Hans. You showed the improvement of the forecast skill when initialized from ERA 5 compared to ERA interim. Do you expect similar jumps in forecast skill when going to ERA 6 compared to before, or is it becoming more challenging?
No, so we've done some experiments and we looked at the impact compared to ERA 5, and we really got quite a big improvement, so good that we are worrying that we did our evaluation incorrect, so we have to do it very carefully. So yes, at this number we improve 1 day a decade in forecast skill. So, and we are now 7-8 years compared to ERA 5, so we hope that we will gain another half a day to 1 day in this skill scores. But of course, it's early days, and we only have done a few experiments in recent periods. So yeah, we hope to achieve that yet again. Yeah.
Thank you very much. Please join me in thanking our speakers, Hans, Peter, David, and Chiara. We will now jump to the next session. Session 2 will consider climate intelligence. And this time we have 4 speakers, followed by a Q&A session. And the first speaker works for Czech Globe, and he'll be talking about the method of analyzing soil moisture anomalies between 2021 and 2023 and its connection to impacts. Please give a warm welcome to Mirek Tyrenka.
Okay, I hope it's working. I hope you can hear me well. When I learned that I'm supposed to give a talk and I was invited for the climate intelligence group, I was sort of a bit worried. and my kids get a good laugh of it. But anyway, I'm really thankful to be able to deliver the talk at this distinguished floor, especially being able to finally meet in person people behind the ERA 5, because that's a tool that we are using in every day. Okay, and I hope this is going to work. Okay, seems so. Okay, we work with a very simple model that is definitely not up to the level of the ERA 5 and ERA 5 physics. We have a very simplified model of a soil moisture, but we use the ERA 5 data to feed in. I have to. Okay, so it's a semi-empirical model that tries to take advantage of data that we have available. It estimates soil moisture for different layers, and that's what we use for the climate report. The reason is we can much easier fit the model to the data, the other data than just the climate, that are not as good as the ERA 5 data, not as detailed. And therefore, we get a reasonable estimate of a soil moisture that is of interest. I'm thinking, where is the receiver? Okay, anyway. So the model has been validated many times, but at the moment we run, the biggest challenge was the uninterrupted run from 1981 to present. The model doesn't drift anywhere, so it's also a testament how the ERA 5 data are robust and fairly well. Okay. Okay, we carry out comparisons with different data sets like GPCC. Of course, when we take a soil moisture anomaly, which is on the right-hand side, with the drought indicator based on SPI and SPI index on a monthly basis, and we take a daily anomaly, we of course get a discrepancy. But of course, the many major droughts and drought anomalies that are short-term, and those are which interest us on a seasonal scale, are well captured. So this is this is one of the examples when we compare it to the well-known US drought monitor, which is a standard in the drought monitoring, one of the oldest drought monitoring projects, and we are doing a pretty good job in terms of sort of patterns. But of course, we have differences, especially when the drought starts, like here in the east. It's early this year, and you can see that in April we already seen the drought that has been developing later on in the course of the spring. Of course, the problem with drought is, what is really drought? In 1985, Professor Wilheid and Dr. Glantz made an analysis when they already counted 85 different drought definitions. It was 1985, and I wonder what you would count today, and I don't dare to estimate a number. So what we use as a proxy for drought is the soil moisture anomaly over various variable depths from 10 centimeters to 2 meters, because we then see a soil as an amplifier or sort of accumulation factor of a drought. But you can use many different terms or many different sources, like they use in the short blend in the US drought monitor, where they factor in and precipitation anomaly, vegetation indices, and short-term drought indices, and they produce a map. Interestingly, they lead to different maps and the different results. The advantage of soil moisture anomaly, this is something that is physically sort of observable. So on a European scale, we of course have a JRC product from the European Drought Observatory that also assimilates many other products. And again, when we compare it with the SoilClim results, the outputs are quite interesting. You get similar patterns, but you have a different you have a difference there. The great advantage of working in C3S group is that we can sort of sort out the differences and understand it. It's not that one or the other method would be wrong. It's more like that we are each observing something different, and I'm going to show you how that works in the report for 2021. I will just skip the Australia and go to one of the results. Unfortunately, we don't have over 5,000 rain gauges like David was presenting. They're in the Technical University of Vienna, which holds the Soil Moisture Network archive. There is about 1,000 stations, less than that have a reasonably long coverage. And this is just the first run, when we basically assume only the data as they are in the database, and we compare the daily run with our daily model. And you can clearly see also the red points that are pointing out, mostly, fortunately, not error in the model, but error in the data. Again, we have a fairly good performance of the system in most of the temperate regions. These are different land classes. However, SolClim model, because it's originally developed for the cropped and vegetation cover, doesn't really work well in the barren soil. There is one reason in the barren soil. Of course, the precipitation is much more sparse, and the ability for the point measurements to capture the sparse precipitation is much lower. So there are reasons for that, but overall the system seems to be working quite well. And here is promised contribution to soil moisture modeling to the report 2021. If you remember well, we had a major problem with the high temperatures over Italy, and that was one of the focus chapters in the report. And just to draw your attention, I mean, the model predicts, or basically says, based on the ERA5 data, it was dry Mediterranean summer as usual. What is different, okay, it's faster than I wanted. Okay, I'm going back. The second set of maps is showing anomalies. And what's interesting, while Iberian Peninsula, Northern Africa, Anatolia is mostly dry, in the July, Italy and Apennine Peninsula is still relatively wet. And that was one of the reasons why the drying the drier than usual soil profile was one of the contributing factors to the heat wave. There is always a compound effect. One is sort of the driving the other. Definitely the drought was not the initial cause of the heat wave, but it was something that was clearly depictable that it made it worse. We had a heat wave also over the Spain, but the anomaly over the Spain were not that severe compared to Italy, which was interesting. That was one of the reasons why we get much more sort of reports on the Italian heat wave than the Spanish ones. Okay, and I'll try to go to the 2022 report, which was more detailed because there was a chapter on drought, and we sort of captured the anomalies as they develop across European scale. You can see that February for the EU was pretty good, unless you were living in Spain, which suffered from early drought, which then returned at the peak of the summer, and we again saw the anomaly across the most of the Rhine catchment. If you remember that drought, it was tremendous, at least to my experience. I never imagined that we can have a drought in Europe that would have almost a flash drought features that would affect the Rhine catchment, Rhine basin in its entirety. And it was not only the Rhine, it was also the French rivers that were suffering. Because we are working with, okay, I'll just, this is another way to look at the drought using the drought intensity that is based on the percentiles, and it pretty much shows the similar pictures, the anomalies, again showing that at the middle of the summer we had Germany and eastern France really sort of suffering by major soil moisture anomaly together with the northern Italy. And if you remember, some of it persisted up to early this year. I think I can skip this contribution, which is, okay, I have to find, okay. What we also do in our group is that we are not only working with the soil moisture modeling, but we try to look at the impacts, and we, in near real time, with about 1 week lag, monitor all the reports that are on drought impacts. And 2022 season was quite helpful over to Europe, so we could pick out the drought impacts quite well. Of course, there is a bias towards the languages in which the internet is publishing, so if the drought hits the English-speaking countries anywhere in the world, you always get a big sort of hit. And I am afraid to say if it hits the French or Spanish-speaking world, we get a much less sort of reports on drought, and that's something that we are working on how to correct this bias. I had the last 2 slides that try to see what's in the future, and as been mentioned for the climate, how we can use the ERA5 for the climate change. We can look at the trends. So the soil moisture trends across many parts that are interesting for us, and especially Europe, are negative. That's not surprising, given the driving parameters. These are the distribution of soil moisture across the continents, with Europe being here at the sort of right middle spot. And it's clear that we have seen shift towards the drier climate over the past 20 years from in the 40 years of ERA data. But it's not only for Europe. If you look carefully, you can see that most of the continents, least in Australia, so which is because it's probably too dry anyway. I would like to acknowledge to my colleagues that were part of the author team, and I would like to sort of thank to our collaborators on the climate status report. So many thanks.
Thank you very much, Mirek. On behalf of the AV team, apologies for the not so effective clicker. And the receiver is quite far. We'll try to solve it as best as we can later on. Our next speaker will talk about the European state of the climate methodology and highlights. She works at ECMWF. Please give a warm welcome to Rebecca Emerton.
Hi everyone, it's great to be here this year for the C3S General Assembly and to meet many of you in person for the first time, which has been really nice, and I look forward to meeting even more of you over the next couple of days. For those of you who don't know me, my name's Rebecca. I've worked with the forecast evaluation section at ECMWF for a few years, and in January this year was fortunate enough to also join the climate intelligence team, working on editing and coordinating the 2022 European State of the Climate report. So I was just asked to talk a little bit today about some of the work that goes into the report and some of the highlights from the 2022 report. So as David mentioned in his talk earlier, the 2022 report was the 6th edition of the State of the Climate, which has really evolved and grown every year that it's covered. The report covers a few kind of main areas, the first being a quick overview of global climate highlights. And then we go into a lot more detail about the state of the climate in 2022 in Europe and in the Arctic. And we also give an overview of longer-term trends in key climate indicators. So the report it really is aimed at a very broad audience. It aims to inform policymakers and decision makers about the evolution of the climate in Europe. It supports scientific research, and it provides public awareness about changes in the climate. I think it really provides an important role in climate monitoring and international collaboration. It's a great example of collaboration across Europe from a huge range of organizations. To highlight that point, this is my kind of list of non-climatic European State of the Climate stats. So for the 2022 report, we had 73 contributors, many of whom are in the room today or joining us online across 36 different organizations. We have a fantastic editorial team at C3S. I think many of you already know Freya, Julian, David, Francesca, Annabelle, and Sam. We have our fantastic science writer. This year we had 18 different reviewers for the report, and we used 32 different data sets across the 16 chapters and sections of the report. And that's not including the 10 climate indicators that we also update at the same time as writing the report. And we heard some of the stats from Carlo's talk earlier. There is also, beyond the writing, an absolutely huge communications effort that goes into the European State of the Climate report. The production of the summary, which many of you will have seen, is a beautiful document full of satellite images, highlights from the report, the website, which is a huge endeavor in itself, all of the infographics and the videos that we produce alongside the social media, other articles about the report, press briefings, dozens of interviews and other events. So really, alongside the writing of the report, a really huge communications effort. So in terms of the report itself, for the European and the Arctic sections of the report, we kind of structure these like this on the website. So if you're not familiar, most of the report is fully web-based. Every chapter of the report has its own separate web page full of all the information. So for these, we have monitoring sections and spotlight sections. And the monitoring sections kind of each feature every year. Sometimes we add new ones if new data sets and resources become available to write about those. And in these, we kind of provide an update on how those associated variables looked during the year and compared to the reference period. And these cover things from temperatures and SSTs to wildfires, hydrometeorological variables, to circulation and energy resources. And then we also have these spotlight sections. And in these, we take a look in much more detail about key events that happened during the year, typically large transboundary events within a climate context. So once we've written all of those chapters, gone a bit too far now. Those are not the same. So once we've written all of the chapters, all of the data processing that goes into those, producing graphics, writing up the analysis, I think a really important part is the science writing that the report goes through, so taking this really technical scientific content and making sure it's really accessible to a very broad audience. And then we have the comms side of things that I mentioned. So on the right side of this slide, you can see a snapshot of a selection of some of the videos and the infographics that were created about these spotlight sections and about some of the key messages from the 2022 report. And so much work goes into producing these to help kind of with spreading the key messages of the report in a really engaging way. And so then when the report is released, we typically hold an embargoed media briefing for the press the day before the launch. And this year we had an online media briefing, I think with about 100 journalists attending. We had statements from Mauro Fahini, the head of Earth observation for DG DEFIS, and from Carlo. And we had a panel discussion with Sam, Carlo, and Vincent Henry to answer questions from the press during that event. And then this year, I think for the first time, we also had, following the report, a policy event, which was kindly hosted by the German embassy in Brussels. And this really aimed to increase the awareness and engagement with C3S through discussion of the European State of the Climate report and the use of climate data. So we had a range of speakers, including the German ambassador to Belgium, the Belgian Minister for Climate. We had a fantastic panel discussion. There was a really lively panel discussion on kind of how data can be used to influence policymaking across Europe, how to access the data, usability of the data and the products across Copernicus services, and more. So we had attendance there, including ambassadors from the German embassy, from countries across the world, EU representatives, local media, and several people from across the European Commission, who of course make up a key part of our report audience. And I think this was a really great event for awareness of the report in policy circles, and it was great to see feedback like shown on the screen here. So Zakia, the Belgian Minister of Climate, said the European State of the Climate report from C3S is an invaluable resource for policymakers in Europe. Ooh. So I'm going to try and give a really quick overview of some of the key highlights from the 2022 report in my remaining time. So we've already heard that 2022 was the second warmest year on record for Europe. For many countries in the southwest, it was the warmest year on record. And for Europe as a whole, the warmest summer on record by a huge margin, at 1.4 degrees C above the reference period and 0.3 to 0.4 degrees above the previous warmest summer, which was only in 2021. And of course, this year has been extraordinary throughout the summer as well, and Sam will be talking more about this summer's events a bit later. So not only the land and surface air temperatures, but also the sea surface was generally warmer than average. Across Europe's seas, the average sea surface temperature was the warmest on record, and we had record-breaking marine heat waves across the Mediterranean during the summer, and in other regions at other times of the year. And one of the new monitoring sections that we added in 2022, which has received really a lot of interest was on the land cryosphere. So in this section, we discussed the kind of winter snow deficit and the impact of this combined with the summer heat waves on Europe's glaciers, and in particular, the record loss of ice from the glaciers in the Alps last year. And I think Frank will talk more about glacier monitoring in the next talk. And of course, it would be hard to talk about 2022 without talking about the heat waves that occurred not only in the summer, but throughout the year. So we had a spotlight section that kind of looked in a lot of detail at every single one of these heat waves from March, May, the entire summer, October, and December. So as well as looking at all of those, we also looked at the heat and health impacts of the record-breaking summer temperatures. So we looked, one of the things we looked at was the heat stress, so not only accounting for temperature, but also the humidity, the wind speed, the solar and thermal radiation, and the impact that has on the human body. And we reached record-breaking numbers of days with very strong and extreme heat stress in Europe and Southern Europe last year, and again this year so far. And we also looked at surface ozone, which reached potentially harmful levels across much of Europe last year during the summer heat waves. And of course, last year, as well as the extreme heat, we also saw the second largest wildfire burnt area on record for the EU countries. Another event that we looked at in detail, which we've also just heard a bit about, was the widespread and prolonged drought that we had last year. So I won't go into too much detail, but in terms of soil moisture, the second driest in the last 50 years. In terms of river flow, the second lowest average river flow for Europe on record. But actually, in terms of the area affected, it was the worst year on record, with 63% of Europe's rivers seeing lower than average river flow. And then the final spotlight section that we looked at last year was an Arctic focused section, looking at the extreme ice sheet melt that we had in Greenland associated with 3 atmospheric rivers and enormous temperature anomalies across the country during September last year, which I think led at the peak of the first heat wave to almost a quarter of the Greenland ice sheet being under surface melt. So I think that is just about all of the time that I have. So thank you for everyone for listening today. Thank you to everyone here and online who has contributed in any way to the European State of the Climate Report. I'm really pleased with all of the work that we've done, and I look forward to working with many of you again on the 2023 report, for which planning is already starting. So if you would like to hear about the changes coming for the contributions for the 2023 report and start planning the content, please do come along to the side event tomorrow afternoon. Thank you.
Rebecca, thank you very much. I don't know about you, maybe it's because I'm not a climate data expert, but it's been quite an onslaught of highly information density that is very high. So let's revitalize our ability to focus. I invite you to stand up before we move to our next presentation. All right, excellent. Now, let's just take a moment and breathe while looking forward, not focusing on anything in particular. If thoughts come in, just let them go. Don't comment or judge. Now I invite you to breathe in deeply through the nose and then breathe out through the mouth. One more time, deeply through the nose and out through the mouth. Excellent. As you breathe in deeply, you turn your neck to one of the sides. Let's go this way. Breathe out. You breathe in again. Breathing out, bring your head back to neutral position. We do the same to the other side. Breathe in while turning to the other side. Breathe out. breathe in, and return to central position. Excellent. Now we breathe in while bringing up our arms. Breathe out, bringing them down. This is a good photo moment. Let's do it again. Now keep them up while you breathe out. Breathe in, and when you breathe out, you go to the side. All sing along. Breathe in one more time. Back to neutral position, keeping your arms up. Now you try to stretch your body upwards. If you're wearing a jacket, you're not in luck. Stretch the arms as far as you can. Tilt your head a little up as well. Breathe in and then breathe out, bringing everything down. Brilliant. Last exercise that I learned from my 9-month-old, and apparently it's called a psychological sigh, which has a reason. And it's like this. 2 short breaths through the nose, and then you sigh out. Now you do it one more time. With your sigh out, you sit down. All right, give yourself an applause. Frank Paul of the World Glacier Monitoring Service of the University of Zurich. There's no better preparation for your presentation than this. You will be talking about glaciers in the ESOTC context. Give Frank a big applause.
Thank you very much for the introduction and also for the opportunity to speak here. I will now talk a little bit about glaciers, and I assume you all like glaciers because they have been very prominently featured, I think, on the title of the last 2 reports. So it seems to be some very important thing. Let me maybe ask one very short question to all of you. Who of you have ever been on or at a glacier? Ah, so nice. Okay, then I skip the more basic introduction and go just right into the problem. And assuming that this will work, yes, this will work. You see here, not from space, but from a webcam that is publicly available, a collection of pictures that have been adjusted spatially in PowerPoint to get them on top over 8 years from the Pasterze Glacier in Austria. And what you can see here is quite a lot of things. I can talk about this maybe about half an hour. But the thing is here, within these 8 years, the most prominent thing you see here is that the glacier surface is rapidly down-wasting, which is, of course, the result of too little snow coming from the higher regions. Here, this is the accumulation region of the glacier. And you see here that the flow-through is very strongly thinning, and this entire big tongue will be just dead ice in a few years from now. So the point is now, what can we observe from space in this regard? And of course, we are interested in the amount of shrinkage, not only the vertical amount, but also then the horizontal amount, the change in length, so to say, and also the change in extent. You see that the glacier tongue is also shrinking. So I go away now with this picture. There's some more animations. When working with glaciers, you have to consider there are about, let's say, 215 or 250,000 glaciers on Earth, smallest size 0.01 square kilometer. And they're all a little bit different, and they all want to be treated a little bit special. So it is quite not quite straightforward to put them all together in one big box. However, you see here famous Aletsch Glacier, famous Aletsch Glacier here, and also glaciers in the Arctic, which looks a little bit different. glaciers calving into lakes, or glaciers that are driven by sublimation instead of melt when losing mass. What we want to know is how much glacier ice is out there, so by volume and of course where it is and how big the size is, and then how fast do glaciers change. These are the two questions we want to investigate. And we do this with the following methods. I shortly introduce what we are doing now in the service. You see here Aletsch Glacier from a nearby mountain peak. And what we are basically doing is that we convert satellite images like Sentinel-2 into glacier outlines, which should show up here in green. And then we do this not only for one glacier or those in this picture, but for all of them in the entire Alps. And we need 15 Sentinel-2 tiles for this. And then we do it not only for the Alps, but for the entire world. And of course, within C3S, we only do a part of it. So to get the entire picture, not just the 4,000 glaciers in the Alps, but the 215,000 glaciers globally, we need a big team. And we do this together with global scientists in all parts of the world. Just as a number, when all the glaciers would melt, the sea level would rise by 30 centimeters. And when we talk about glaciers, that's also important, we exclude Antarctica, apart from the glaciers disconnected to the Antarctic ice sheet, and we only talk about the peripheral glaciers on Greenland, as we say. So the Greenland ice sheet is also excluded here. And just to show one more animation, so this is now the satellite perspective of the loop. Again, something like 15, 16 years, but we are now in Patagonia, and there's lots of precipitation, 2 to 3 times more than in the Alps. Nevertheless, the big glaciers, shown here in false colors, also retreat downwaste and produce new lakes at their fronts. And this is also an important aspect because a part of the glacier melt does not go and contribute to sea level rise. So it sticks into these lakes. And in the field, we are doing one glacier, and globally about, let's say, 100, where we measure the annual mass balance with field surveys. So digging snow pits and drilling ablation stakes in autumn, and then go back in end of winter and end of summer and see how strong the melt was. This gives then for an individual glacier this time series per glacier per year. When we go to space, we have a lot of possibilities to assess how glaciers have changed. And the most prominent one, I focus on this one now, is digital elevation model differencing. So we create digital elevation models from 2 points in time, subtract them, and hope that the glacier change will come through. And it comes. The point here is that we only have here something like decadal mean values, so not year to year. And the positive part is, of course, we see all the glaciers. So just recently, a publication was out, one back please, showing for all glaciers in the world the elevation changes, converted also to mass changes, for the time period 2000 to end of 2019. So we now have a fantastic calibration data set for all the glaciers in the world, which we could then, of course, also use in Copernicus and go ahead with the important question how to combine them now. The glaciological measurements we have for individual glaciers, but on an annual or biannual basis, and the geodetic ones, which are only decadal, but for all the glaciers. And I will not go into detail here because time is not too long, but just to announce it here, there's a poster out there where I can explain things in more detail. But the basic principle is that we have a selected time series of the annual changes based on all the glaciers in a given range. And then we calibrate this time series against the geodetic mean for the same region and adjust, so to say, the annual time series of these particular glaciers to these decadal mean values. And with this, we get the annual fluctuations for the entire region. And Yeah, these two parts are the basis for what we provide for the European State of the Climate Report. So we have the extents of the glacier, know how large they are, and we know the specific elevation change, which means we call it water equivalent, but it's in principle a change in meter per square meter. So when we talk about volume changes, we can easily multiply this change with the size of the glacier to get the values. And I said before, in the State of the Climate Report, the glaciers are quite prominent. So they are there on the global scale, on the European scale, as a highlight and as an indicator. So we have to provide some input for all of these four things. And yeah, as said before, volume changes is the specific mass change for the region multiplied with the size of the glaciers, which of course also means that we frequently need to update the glacier inventories, because at one point in time, a 10-year-old inventory does not represent how much ice was there. So this is a continuous effort under current climate conditions. So yeah, this is a very laborious part. And one more slide here for the different parts shown in the report. We have cumulative glacier mass balances. The source is the global mean of the field measurements, in this case, for the reference glaciers we have. We have, on a global scale, the annual mass balances in gigatons, and here the source is the glacier area from this Randolph Glacier inventory, the global one, multiplied with a specific annual mass balance. For the European part, we have selected, of course, the mass balance glaciers in Europe and their sizes, and then calibrated the data sets for the regions with this time series. And the new product that we now create is a gridded version of this global glacier inventory, which gives, for example, the percentage of glacier area within each 1 degree tile. And we have a time series of mass balances for each year since 1976 that is calculated according to the just presented methods. And as a final point, this is what we had in 2008. So that was the first try to estimate in different parts of the world mean glacier mass balances. And yeah, now we are at a 0.5 degree spatial resolution global grid, thanks to Copernicus. With this, I thank you for your attention.
Thanks, Frank Paul. The Deputy Director of C3S will now talk about the record-breaking summer of 2023. An applause for Samantha Burgess.
Okay, thank you, everyone. And we're going to transition now to this year and what's happened this year. And first and foremost, I'd like to make 2 points on this slide. So there's a huge team that contributes to this work and to the media, the press releases and the figures that we see in media outlets all around the world. And they're included within that, there's a huge number of unsung heroes. So this is really my opportunity to say this is an enormous team effort, not only within C3S, but also the C3S contractor community and beyond that. Also on this slide, I'd really like to highlight that last year we had feedback that we were absent in the communications of the extreme heat that we saw in the 2022 summer. So we really took that feedback on board and have invested a lot of effort in communicating what the climate is doing this year. Lastly, as Rebecca highlighted in the climate intelligence session tomorrow afternoon at 4 p.m., we've got it's a twofold session. So the first part is on the state of the climate preparation for this year's report. The second part is a bit of a brainstorm on climate monitoring and what other activities the community would like to see the climate intelligence team do. So I welcome all of you there to help us brainstorm and provide feedback. One of the first deliverables that was discussed last year was adding a climate dashboard to the C3S website. So this is updated annually. It's the same data that's available within the State of the Climate report, and it really gives us a snapshot of how the climate is changing, and we have ambition to update and evolve this with the rest of the community. In terms of what we did over the summer, it started quite early on, and this is a fantastic graphic that was prepared by Adrian Simmons, which showed breaches, temporary breaches of 1.5 degrees above pre-industrial. And ironically, we were actually above 1.5 degrees when the Paris Agreement was signed in November, December 2015. So we've had a number of temporary breaches, as you can see from this bottom figure, and that has escalated over the summer period. So the next record-breaking event that we had was the anomalous sea surface temperatures around the world. And I think the anomaly that we had in the North Atlantic off the coast of Ireland and the UK was really surprising to many people. So we had an initial press release on the record sea surface temperatures, and we also had a record associated with June being the warmest June ever. So, which maybe, yeah, that's on the next slide. So as part of this, there are a huge number of media mentions associated with June, so over 5,000 clippings, press clippings online, and our data was picked up by other organizations such as the WMO. Because of this, and because of our careful climate monitoring, we didn't click through. There we are. We decided to update how frequently we were communicating on the climate data. So we now have a FTP site where data is released 2 days behind real time. So early on in July, we were aware that the 6th of July was the warmest day that humanity has ever had, and this was quickly superseded by the warmest week, the warmest 3 weeks, and then the warmest month on record. And you can see here the 2 tweets that were 2 days after those record events happened. So because of this, we collaborated with the World Meteorological Organization and also collaborated with the UN Secretary General's team. So this led to a joint press release, which Antonio Gutierrez gave a press conference. Carlo and Chris Hewitt from the WMO also gave a press briefing ahead of time to really highlight the extreme temperatures that we faced in July. And I think it surprised a lot of scientists, and there was a lot of interest in the community and in the media about the rhetoric that the Secretary General described of, the era of global warming has ended. We are now in the era of global boiling. It's probably not something that I'm very comfortable with, but I think when rhetoric is your only tool to elicit action, then I think, it got a huge media uptake, so that was very interesting. And from a perspective of the total media mentions in July, it was over 12,000 press clippings across the month of July. And you can see how anomalous the July temperatures were. So July 2023 is at the far end and head and shoulders above any previous July on record. The records continued to keep dropping, proverbially speaking, and so there was also a news release and a lovely article that the BBC did on the record sea surface temperatures. This got picked up almost 300 times from this one article, and well, fortunately, unfortunately, who knows, but I gave the BBC my phone number. I ended up having 6 interviews in one day, which was great in terms of showing the public interest. And I think this is one of the things we struggle with as a community. It feels like these records are broken all the time. And is the public engaging with this information? I think what we saw this summer is yes, and we're working really hard to make sure the data and the communication is as timely as possible and is as clear as possible. So we've really worked very hard on improving our graphics to improve clarity, and I'd like to give a shout out to Julian Nicholas, who's been working incredibly hard behind the scenes to work on these compelling visualizations. August, so we released our monthly bulletin for August last month. August was also record-breaking, the warmest August on record, and the second warmest month in human history. So again, we had a press release with the UN Secretary General. This one was kind of a lighter lift the second time round, but it worked very well. And you can see in this figure, these are not in temporal order, but in record order. So if you can't read the captions, it's all JJA. And the June, July, August for 2023 is again head and shoulders above any previous boreal or northern hemisphere summer season. So the fact that 2023 has exceeded any previous JJA by 0.3 of a degrees is a lot. And I think it's also really important to mention that there was a lot of noise in the media over the summer. There was some confusion about surface air temperatures, so 2-meter temperatures, which we report on, versus other outlets that report on ground surface temperatures, and the difference between those scales, how they're measured, what they're useful for. But I think as well the understanding of these records is improving all the time. So, and as we saw from the interest in the late July sea surface temperature articles, the sea surface temperatures continue to rise over August. They've dropped off a little bit now, but we've had record-breaking heat waves, marine heat waves over large parts of the ocean. I think the NOAA data says at one point during this summer, something like 60–70% of the ocean had heat wave conditions. And this is all obviously extrapolar ocean, so 60 north to 60 south. Finally, and it looks like I'm ahead of time, which is great news for the discussion section, if it clicks on. Oh, sorry, penultimately, in the context of all these record temperatures, we also have record low Antarctic sea ice for this time of year. So you can see this curve. This is our version that we publish, and again, it came out in the August monthly bulletin, but there are other data sets around as well that really show the trend this year is significantly below the growth that we would expect at this time of year. So we're coming up to the maximum sea ice extent for the southern hemisphere, and it's not where it has been in the past. So this means, and there was a Nature article that came out last week from the British Antarctic Survey that showed that, for example, emperor penguins had a complete failure of their breeding season last year due to the record temperatures last year, and this year's even worse. So the impacts on biodiversity cannot be overstated. So finally, I think the elephant in the room is the El Nino. So we announced I think it was in May, that we were transitioning to an El Nino event. The WMO formally announced in July that we are now in an El Nino. The reality is the global ocean has never been warmer. Every single El Nino event is individual and unique, but this El Nino event is starting from a warmer ocean than ever before. So who knows what's going to happen, but I think we'll continue to be amazingly busy. So thank you very much.
Samantha, thank you very much. You now hold the record for the shortest presentation in the 6th GA. But nonetheless, a very clear and important one. May I please invite you, as well as the other speakers of this session, to come forward on the stage and take their seats so we can start our Q&A session, which will be followed, by the way, by one more presentation before we head to lunch. If, meanwhile, we could have sufficient microphones, as well as the lights turned on the stage. Let me also invite those who are remotely following the discussion to please contribute their questions over Slido. All right, brilliant. Welcome our speakers one more time with their generous applause.
I was aiming for the least amount of words.
So raise your hand if you want to contribute. Brilliant.
Hi, yeah. Can you hear me? Yeah, there you go. Question is for Mirek.
Perhaps you could stand up.
Okay.
And introduce yourself.
So I'm Edward Commonplatt from the CDS team at ECMWF. I got a question for Mirek. It was about the missing soil moisture. Where does it go? Does it end up in the sea, like melted sea ice? And if so, how much is it? If you take the change in soil moisture from 1981 to 1990, I think was your historical record and your current statistics. How much does that compare to the sea ice we've lost to the oceans?
That's an excellent question to which I don't have a clear answer. I have to admit that there are better experts in the room also that manifested that some of the changes in the soil moisture can actually be detected in the sort of sea level the other way around. If you have too much of the soil moisture, given the heavy precipitation, then you can actually see some of the impact on the sea level in the region. But as far as the global drying of the soils, quite a lot of this water, I suspect, is in the atmosphere because of just the increasing volume that can be taken up by the atmosphere due to higher temperature. So that would be my direct response, but we are not really doing the modeling in this direction.
Many thanks for that response. I saw at least one more hand go up. Yeah, let's start with the gentleman over there.
From SMHI in Sweden. I was wondering about your use of ERA 5 for reporting on temperature records, and especially ERA 5T. So this, I saw in your first tweet or X that you called it also temporary or like first indications show that, and then, but you're not in the 3 months periods, you're not in ERA 5, so how reliable is ERA 5T on this short notice? And do you report back also when you get more observations in and follow up on these communications later on?
Shall I take that? Yeah, so I'll start on that, but we can follow up afterwards. So ERA 5, and we had the question in the earlier session about how good it was for rainfall extremes, and David's very eloquent answer was patterns good, magnitude bad. Temperature is much more competent. The signal to noise ratio is much better, so there's very little divergence between ERA 5T and ERA 5 consolidated, and every time we do the longer term reporting, we always match it back to EOBS, so we're comparing it all the time, even in the seasonal lookbacks, and in the state of the climate reporting as well. So we're always verifying that the anomalies are relevant to reality, effectively.
Many thanks. Anyone else who wishes to contribute to this one? Seeing none, returning to the room. Yes, sir.
Gerrit van der Schier, KNMI. I have a question for Mirek. So you showed the wonderful example of the Americans with their drought monitoring system, which is indeed far ahead of what we are doing in Europe. And you also showed the European Drought Observatory, but that is much more from the perspective of the emergency services. Do you think there's room within C3S for a drought monitoring tool more from a climatic service?
I think it's an excellent point, and I think there is. Frankly, I try to illustrate it with the last two slides that there is overall trend to the soil moisture decrease, even though we are facing higher variability in the precipitation, and that we have to deal both with floods and droughts. And to me, droughts are becoming one of the biggest menaces for the climate change. So I think definitely there is a huge potential. We have tried to develop something of that kind. That the work I've been showing is actually based on the ERA 5 and also the IFS data from ECMWF operational at the wind platform that is available. So it's doable, and based on our estimates, it really gives a quite quite useful results also for the state of the climate report, because we can look at it directly as the drought happens, and we can confront it with the newspapers, with the clipping services. So I think there is certainly not only the room for collaboration, but I think it's needed.
Thank you very much.
Thank you. My question is about glaciers, so I guess it's for Frank, because this summer we've seen two phenomena that sort of exhibit a really non-linear transition. One is the drop in sea ice extent in the Antarctica, and the other was the SSTs. In both cases, the jump was enormous with respect to the previous one. And I was wondering whether, in your opinion, we have seen anything similar for the glaciers in Europe, and whether it's likely to see something like that, like a very non-linear transition in the melting in the near future.
Many thanks, Carlo.
We certainly can see in the mid-1980s a big jump in the mass balances of the European, and not only the European glaciers, that was unsurpassed. So that was really likely related to some oscillation in the oceans. There was also an increase in temperature in Europe by close to 0.5 degree at least, and it never came down. And this was then directly reacted with the glacier mass balance. That was before, let's say we talk about the 100 years before, we have something like surface lowering over the entire glacier, something like 30 centimeters per year. And after that, things jumped to 60 to 90 centimeters per year. So it was really a big thing. And now we are at more than 1 to 1.5 meters per year in the Alps. And in 2022, we had partly -4 meters over the entire surface, including the accumulation region. And this is simply incredible. And it goes on. So, there's for the next 10, 20 years, this will continue, and we can just see and, oh, yeah, it happens.
Thanks. The lady over there, perhaps. No, go for it.
Also to this glacier.
What's your name?
My name is Christina Fröhlich, Deutscher Wetterdienst. I'm responsible for the seasonal forecast, and our model doesn't take into account any glacier melt or something like this. So, but if the glaciers are contributing water to the water cycle, and so there will be a continuous runoff. So I think maybe it would be very interesting for us to know so the increase or the deficit that we will have in the water balance if we do our global water balance, and then it would be good to know maybe each year how much data has been added to the water cycle or something like this. Would this be also feasible to give these numbers from the monitoring?
Yes, this is currently the front of research, I would say, to really assimilate then also all these data we have now for something like, let's say, annual runoff contribution per catchment. What we know and what is done is that the glacier information, let's say, from the past is used in connection with the climate model output to assess how glaciers will develop in the future and when per basin peak water will be. So the point in time where the contribution from glaciers will start to decline. And this is certainly for the European Alps not too far away. For other regions in the world, it will be a little bit more in the future. But I would say we do not have yet such a product. But I know that hydrologists and glacier modelers all over the world are exactly working on this now with this calibration data set we now have, where we can really have the global picture. If it is be on a credit basis or whatever, this is more or less flexible.
Many thanks. I think we have a contribution from the online
Yes, it's a question which is more general about not just glaciers, but if we have reached basically maybe a tipping point, a question of a breaking point or non-linearity in the climate system.
I'm sorry, this went a little too fast. If we've reached a
breaking point or tipping point
in the climate
system.
Excellent.
Yeah, I think I can start on that. I think there's a lot of nervousness about that, but the reality is there is a huge amount of variability in the climate system. So we're doing everything we can to report on the observations that C3S is competent to report on. Whether it is a tipping point, I think this El Nino is likely to be the strongest yet. That's, if I was a betting person, that's what I'd say. And I think we really need to see what the Antarctic sea ice does this summer to see if it does recover. But I think we may be looking at drastic changes in the ocean. And the reality is the ocean has absorbed 90% of the excess heat. A lot of that has been invisible to us, has been trapped in the deep ocean. Now is more visible, so understanding, and I guess this would be a plea for funding agencies to really ensure that they are investing in the science to understand whether we are facing a tipping point. That's really critical.
Thank you for that excellent question and answer. I think there's a contribution from the gentleman over there.
So we have an accurate picture of the past, but we're flying into the future facing backwards. And I'm wondering, this hasn't come up, the integration with, say, the next 10-day forecasts about alerts. It seems like that is a relevant service for this community to partner with the operational forecasting about alerts across all of these parameters.
So I'll start on that one, but I feel like that might be a better lunchtime discussion. The C3S benefits enormously from being in an operational weather forecasting center. However, they're still our remit versus the remit of ECMWF and the remit of the national meteorological agencies. So any time we deviate or adapt and evolve from what was in our contribution agreement, it needs to be done in collaboration from the community. So I think it's a really interesting suggestion that we need to take on board. As Carlo mentioned in his opening words, attribution and perhaps having a forecast of attribution and a forecast of heat waves, that might be the intermediate step. But is C3S the appropriate vessel for early warning? No, there's a emergency management service. So I do think there is a question of, if we are transitioning into a different climate state, how do we work collaboratively to ensure that decision makers have the data they need to make decisions appropriately?
Mirak, very briefly, if you want to contribute.
I just wanted to point out that C3S has a clear mandate, and while it is also partnering a lot of different organizations like ACECLO, which is part of Academy of Sciences. So we have a freedom to do some of these things experimentally. So we experiment with, for example, drought forecast or the fire weather forecast for next 10 days using the ECMWF data. And I think there is operation, it's doable. It has a value. It has a users that are willing to do it, even though 20 years ago when I started, a drought forecast was something that was laughed at, because who is interested in drought forecast for 10 days? But there are people that need that.
Excellent. We have a highlight presentation, which is about machine learning approaches in climate science. It'll be delivered by Matt Chantry of ECMWF. He is online. While you give him an applause to welcome, give the excellent members of the panel an applause to thank them for their contribution in the interest of time. Thank you. Thank you very much. Matt, are you able to hear us? We cannot hear you yet. What's 5 plus 5?
It's 15? No,
15.
No, that can't be 10.
All right, I'm starting to worry. Please give Matt an applause.
It's a very good question you asked, actually, because I'm going to talk about machine learning, and I'm sorry to be the last person between you and lunch, but I'll try and keep it quick. People quite liked asking some of these large language models, which is a topic I'll touch on very briefly, to do basic arithmetic, and found quite mixed results when they did so. So I'm going to be talking about some work that's gone on at ECMWF, but also capturing things that have gone on wider in the community on how reanalysis in particular, as part of one of the sort of C3S data sets being offered, is really empowering machine learning to do really rather amazing and exciting things around the world. And if you wanted a better introduction, I could have asked a large language model like you see here, and you would have gotten this as an alternate. So I'll leave you to judge which one was a better opening. And we'll move on to the next slide, please. So I'd say that there are three broad classifications that have led to there being a boom over the last few years, not just of machine learning in Earth system data, but machine learning worldwide across many different domains. And those have come via three aspects. One has been advances in machine learning architectures, training algorithms, and frameworks. One has been big advances in computational power. So NVIDIA and other of the tech providers are providing ever more powerful GPUs and other accelerators. And then the third thing is the ability to, and the data sets created to allow these models to consume vast amounts of data. So the language models that everyone likes to play with are the result of training on almost any and all vaguely language data that these models can get access to. But in general, you do have this guide that if you train on bad data, particularly if you train on only bad data, this will lead to bad models. So if we go to the next slide, we'll see. So what about sort of focusing in on the Earth system, on what we might do there? So the top two, I think that those are broadly there. We can take lots of the interesting advances in architecture, and we can take lots of the advances in computational power. But what about the data sets? So one approach is to learn from observations, but that's really hard. It's not to say it's not being done, and there aren't people doing really exciting things, but there are loads of challenges there. So data might be stored in many different places and formats. Observations might change over time as satellites come into and go out of existence. Data has biases and errors, and requiring multiple variables for a task might require many different observation data sets. If we go to the next slide, we'll see how sort of reanalysis is in no way perfect, but helps address most of those issues and provide a singular sort of point of truth to work with, where you might have many variables on all times, on all points in space, all accessible from one sort of easy to use access point. So if we go to the next slide, we'll see some of the interesting ways that people are using reanalysis to and machine learning to do very interesting things. So just to sort of pick a few highlights, sort of post-processing to try and use, say, ERA5 to remove bias and calibrate forecasts, downscaling to increase the resolution of weather or climate models, learning observation operators, or even things like hurricane forecasting. And I checked the other day, so there are about to hit 10,000 citations to ERA5 online, and about 2,000 of those, so about 1 in 5 are going to be mentioning machine learning. So if we go briefly to the next slide, I mean, the most extreme end of what people are looking to do is actually to try to replace weather forecasting models and to try and predict the weather using only reanalysis. So let's go to the next slide, and I'll give you a brief introduction of how that's framed as a problem from a machine learning perspective. Next slide, please. Yeah, so is reanalysis, this is the question being asked, sufficient to learn a global weather forecasting system, particularly from ECMWS perspective, learning a medium range weather forecasting system? So the problem here is to say, well, given a state of ERA5, a state of reanalysis at a point of time, can you construct a model, a neural network, which is parameterized by a very large number of weights in some settings, to predict a future state some time step forward in time, so maybe 6 hours? And then how this works as a supervised machine learning problem is you seek to minimize some function. Here might be mean squared error of how far away your model is from your truth. And you iterate many times through your data set. So you might pass through the ERA5 data set, order 100 times to do this. So if we go to the next slide, we'll see how this is sort of taken off over the past few years. So this was introduced as a concept back in 2018, but got some sort of low level of exploration in the period, so 2018 to 2021. And in 2022 onwards, we've seen a really fast evolving landscape in that time, where we've seen some researchers, but also a lot of big tech companies get involved in this field, interested to explore their knowledge of these big things powering machine learning developments. So explore the new hardware, the new machine learning algorithms, and to really see how good of a job you can do training a machine learning model entirely from ERA 5. So let's skip forward and see what these models look like. How good are these models? This is something, so now we take over. Some of these models have been made public. What do they do? So as of just the other week, we now host 3 of these open source machine learning models on the ECMWF website for people to go and look at, verify themselves, test what they're saying for different places in time. And so I've given you a forecast live for almost exactly now. We're just 1 hour out by my reckoning. For Europe, for temperature at 850 hectopascal. And we're seeing here a game for you to play. 3 of these are machine learning models. One of them is the operational IFS system. And I'll let you see, and I'll give you some clues over the next few slides, which one might be the real one, or the IFS as opposed to the machine learning models. So next slide, please. So verification is a really important part of assessing whether these models are going to be interesting tools for making accurate weather forecasting systems. And so one of the ways we've been looking at this is looking at a time series of errors. How accurate is the model every day as we step through a couple of year period? And what you can see is the scores for geopotential height as 500 hectopascal for the IFS and one of the first of these publicly available models, which is called Pangu Weather. And the interesting thing here is that they track very, very similarly. They have a very high correlation. And what's more interesting is not that they're highly correlated when the error is low, so when the values are down at the bottom, but actually we have a forecast bust in February of 2023. And this was almost identically caught by both the operational model and Pangu Weather. So they both suffered from challenges in the initial condition, and both had similar propagation of errors, meaning that they had lower quality forecasts. So this actually means that they're behaving very similarly to operational models, and they've learned something very similar to our physics-based model. If we go to the next slide, we'll see a sort of headline scores. So this is anomaly correlation. So you want to be at the top. That would be a perfect forecast for 2 different fields. And here you've got red is the IFS, blue is one of these data-driven models. And you see that they are very, very close, or in fact, for some variables, the machine learning models can be superior. So headline scores, we've heard a lot about. All these works came about with publications that assessed the headline scores. They showed very good results, but obviously, particularly connecting to what Samantha was talking about just before, high impact events are obviously a really important use of weather forecasting systems. So let's test how they behave here. So let's skip across and look at some high impact events. So on the next slide, you're going to see a cold snap that happened over Europe in February 2023. And this is a series of forecasts, all valid for the same time. And so what you're seeing on the left, the right panel, but the left-hand side of that right panel is forecasts from increasingly far back in time. So where forecasting is an increasingly difficult perspective. And the big umbrellas, the big whisker plots are the ensemble, the ECMWF ensemble. And you can see at the beginning, there's no real sign of this very cold temperature that hit Finland in February 2023, which is marked by this green hourglass down in the bottom right. And what you can see is that about 10 days out, some of the forecasts started to get a sign of this. None of them ever reached the low that we wanted to see. None of them reached the -28, which was hit. But in fact, Pangu Weather, which is one of these models, was earlier to diagnose that we're going to be very, very cold temperature and got to just as cold a temperature as the IFS. So in this very extreme example that ended up being outside the climatology for this point in space, these models performed equally well to the IFS system. If we go to the next scenario, we're going to look at some tropical cyclones. Here you can see a couple of different machine learning models, the analysis in the bottom right and the IFS in the bottom left. And you can see that they all have the tropical cyclones, this twin pair of Idalia and Franklin, in very similar locations. But if we go to the next slide, we'll see that there's sort of a mixed story at the moment for tropical cyclones with data-driven models. So the position error, which is on the left, this is showing the error as a function of lead time, shows that one, or in fact lots of these data-driven models can achieve very comparable skill to the IFS, which is an extremely impressive finding. But at the moment, all of them suffer from an intensity bias. They're too weak. They're weaker even than tropical cyclones are represented in the ERA5 data set, and they're significantly weaker than the IFS, which is obviously going to limit their use. So we go on to the next slide, and we see one of the other reasons that this is perhaps an exciting tool, and perhaps a sort of a democratizing tool, these data-driven models. So ERA5 was very, very expensive to create, but it has many, many uses around the globe, not only machine learning. In comparison with this, if we measure how many compute units we spend to build an operational forecast, this is the relative mouse in comparison to this elephant. But if we look at these data-driven models, they're a fraction of the energy or time to solution that you need to run an operational forecasting system. They're the ant in this picture. And so what you have here is a system that can be run not needing a supercomputer, but by someone with a singular accelerator. So on the next slide, we'll see some sort of summary and outlooks. So this and many other of the operational models are showing very, very promising behavior in this sort of nascent technology. This has really emerged over a very small span of time, and yet they're already comparable to operational forecasting systems over many aspects. There's still some challenges. The intense tropical cyclones, they're not there yet. The models don't have the same amount of small scales as the other systems, and there's not currently a prediction of precipitation with many of these models. Model uncertainty is also not considered, so we don't have a reliable ensemble yet. So I've run out of time, so we'll take us back onto the next slide to this game that we've got. And I don't have time to ask you to put up your hands for which one it is, but think to yourself, and then I will reveal on the next slide that the answer was that the bottom left panel was the IFS forecasting system, and the other three were different data-driven models, which we don't really need to delve into the details of it. So the final slide, the final two slides, the results can be captured in a couple of talks, so newsletter articles and journal articles we've done. And finally, this work, and to sort of summarize, would not be possible. People couldn't create these models without ERA5. So if we go to the final thing, we'll see that the acknowledgements from all the papers I've got here have realized this. They can see that ERA5 has been the answer to do this. And people are very excited for what ERA6 could bring to further improve these data sets. And I'm personally excited for some of the other data sets that are part of C3S to see what people can do interestingly with machine learning to leverage these other data sets. So thank you very much.
Thank you very much, Matt. A few practical remarks before I set you off to lunch. If you have not turned in your poster yet, please do so ASAP. The next session will be a joint session with the EU MetSat conference that is taking place in Malmö, which is why it's extra important to be on time. So I kindly ask all of you to be in the room no later than 1:55. The speakers in the next session, I ask them to meet me in the back of the room at the AV team immediately before they go to lunch. And also, we will ask you to respond to the following question on Slido. For practical reasons, we need to know how many people will be participating in the communication workshop tomorrow. So the question will be screened in a bit. If you connect to Slido, you can respond to the question, why you queue for lunch? Enjoy your lunch. Thank you very much. Sound check, 1, 2. Welcome back. Please take your seats so we can start ASAP. Thank you very much for your collaboration. Do we have a connection with Malmo now? It's ready.
Can you hear us as well here? So.
All right, ladies and gentlemen, good afternoon and welcome back. As I've announced before lunch, this will be a joint session between C3S and EU METSAT, who are having their meteorological satellite conference in Malmö, Sweden. And this session will be on monitoring the hydrological cycle and related extreme events. So let's see if we have a working connection with Malmö. The moderator in Malmö is Marie Dutrieux-Boucher. Marie.
Yes, hi Ali. We can hear you very well, and we are all here in Malmö, ready for this joint session. So I hope we will manage it all right and on time. We have a little constraint here on our side because we have a next session starting at exactly at 4 p.m. So ideally, we would like to finish 5 minutes before.
Well, don't worry. If we go on too long, you just switch the satellite off.
Yes, exactly.
How about we do a joint applause? I'll announce the session one more time, and then Malmö and Brno will applaud. Ladies and gentlemen, this is our connection with the Malmö conference, the third session, which will be about monitoring hydrological cycles and related extreme events. Excellent. If it's all right with our colleagues in Malmö, allow me to introduce myself. My name is Ali El Jabri. I'm a professional moderator, a former TV correspondent for Associated Press, and a public policy lecturer at The Hague University. I chair all kinds of events, quite often related to the climate. It's a great pleasure to be with you. Allow me to share with you how the format of this joint session will look like. It'll consist of 2 parts, each dealing with an adjacent but different theme. The first part will have 5 speakers, and the second part will have 3 speakers. When we're done with all the presentations, we'll have a joint Q&A session where we are looking forward to your active participation. Your questions and comments will be of utmost importance for the quality of our discussion. To participate in the discussion, we will all, whether you are on site or online, we will all use Slido. May I please request our AV team to show the Slido QR code? Here it is. I suggest that if you have not connected yet, that you do connect to Slido. Alternatively, if the QR code does not work, you just visit slido.com and enter the event code, C3SGA23. You may send your questions in at any time. And we do encourage you to do so because this gives our Slido moderators more time to read and receive your questions. And at the end of all the presentations, I will invite the speakers to come forward and we will present them with your comments and questions. Since this is a joint session with quite a large number of speakers, I'm very happy that the speakers have all promised that they will try to keep to the allocated times per speaker. And the first speaker will be speaking here in Brno. And the title of the presentation is the EU-METSAT Continuous Support to Climate Services and Science. We'll be listening to Jörg Schulz of EU-METSAT. Please give him an applause.
Yes, so welcome everybody in Malmö and also people in the room here. I think it's It's a great thing to do a joint session, which we started when we saw the dates were clashing. So, and thanks to all that were involved in organizing this, it wasn't easy, but I think it's working now. So we'll give you a short rundown on what we do in continuous support to climate services in science, and give credit to basically my own team, but also to a lot of other development teams in EUMETSAT, and also a lot of fellow colleagues in other space agencies, and particularly also on C3S LIGOS, where I used a couple of slides from them. Okay, so in one picture, so what we are up to, and in Europe this is very much implemented, is that we have a good connection between the space segment, which you see in the lower left. So this is just what EUMETSAT is operating. And we know that much more is going into the reanalysis, and we will come back to that. We have our own operational production of data sets, which is in the Secretariat in Darmstadt, and of course in our satellite application facility network that produces also a lot of ECVs. And you see a couple of them here on the right in particular, and some of those have already been used also in your State of the Climate report. So like the OSISAF ice we saw in the morning already, but also the sunshine duration and others. And it is also extending now more and more, also doing Copernicus mission data. So we also do full reprocessings like on the Sentinel-6 altimetry. So have that done twice by now jointly with NASA. And we have really responsibility to do this for all the Copernicus missions that we operate. So this is extending also to S4, 5 and the CO2M, but also Sentinel-3. And the latter is really getting closer to time length, which becomes relevant for some climate work. So these things, and there are others like ocean color, sea surface temperature, and so which we produce. The mainstay, of course, is on the upper left, which is producing a lot of these FCDRs that are assimilated in particular into the reanalysis. And what we do now is, of course, improving the stuff that there is a better Era 6 compared to the Era 5. And that's quite an exciting work that we do since about 10 years now with ECMWF, and I think it's a great team that is addressing that. I think altogether in Europe, of course, we address more than the Climate Change Service, but also other services, Copernicus Marine Emergency Atmospheric Monitoring Service. They also need all these reprocessed data sets, mostly. We have also things, of course, in the IPCC assessment and a lot of work with the research. And I think commonly together, we actually address then the policy question that is rather at the table at the COP, where the C3S is the one that acted, as Carlo has nicely described, with these 8 events that they had just last year there. So that's nice. The space segment continuity is the baseline for that, and it needs to be actually hold up very strongly and have value for climate. So that's not only weather. Some people misunderstand that, but at least in Europe, this is well understood. So what we were up to, where do I need to point to? Here. So in the early days of this second phase of C3S, so with Bill Bell in particular, I think we needed about 2 years to get our heads clear to determine what we're going to do. So it was an analysis of where there are some weaknesses in the Era 5. What can we do anything about regional reanalyses, for example, in supporting that? And we had already done a lot of data reprocessing, so everything that is in blue basically here that we had already done in the first phase. So we came up with everything that is in red here, and some of the stuff is new data, so data that have never been used in NWP, for example, and some data are improved version of existing data, because sometimes they're incomplete and you still have new ideas of do better calibration in particular. And I will just talk about 3 things in the following 3 slides. So one is about SSMT, so the special sensor microwave for temperature sounder. I will talk about a very old infrared instrument called the THIR. And this is about, can we do some atmospheric motion vectors in early 1970s? And I will talk about Meteosat rapid scan radiances and what you may do with them in the future. Okay, let's start with the SSMT2. So this is a radiometer that is a bit more enhanced compared to what everybody knows, the microwave sounding unit that is so very popular also in climate monitoring all the time. The advantage of SSMT is it has also some stratospheric channels. We heard already before about the iris assimilation, that helps with that. This is another element, in particular in times before the MCUA became operational, so in the early 1990s. So what we did here is calibrated the SSMT data from the raw measurements into the brightness temperatures that you can assimilate. And then we did comparisons for the later years, because otherwise there's no overlap, with MSUA data and radio occultation data. And this is what you see in the blue dots. Over 1 year of data, you see that they agree very well with simulated brightness temperatures from derived radio occultation temperature and humidity profile. So this is it's an amazing result that we have not applied major corrections to the data, and it comes out like this out of the box if you start from the raw measurement. So this is very good. If you line up all the different satellites from the F10 and F15 of the Defense Meteorological Satellite Program, then you see that there are some systematic differences that we could take out with a harmonization approach, but in the reanalysis data assimilation, so the bias correction takes also care of that. And I think Bill is now doing testing for ERA 6, and I really look forward to see the impact results for that. So number two. So number two is the THER. So what you see, so we undertake a feasibility study if we can actually derive some winds from that. So what you see in this time series plot, so this is the coverage of data from 4 different satellites, and they were all done by the Satellite Data Rescue Project in C3S, which is also another very nice collaboration in building up data sets that we can use. So this is Nimbus 4 on the left, and then 5, 6, and 7. You see nice coverage in 7, but this is not the important bit because there's huge overlap with the AVHR, so where we can do AMVs anyway, so we have something in addition. But look in the first bit on Nimbus 4, so that's just a complete year of 1970, which is looking actually pretty good. So we manipulated our algorithm, and one of the first results you see in the right plot here, and this is basically wind vectors, and on top is plotted, so this geopotential height from the reanalyses. And you may identify, I cannot point here really well. No, yeah, you can, but others couldn't see. So there are 2 low-pressure systems, one here and one here. And you see actually the winds are actually pretty much aligning around that. You have a harvest of only a few winds, but it could still be enough to really impact the reanalysis, I hope. If you compare that with ERA 5, so this is just the number of winds, so most of them are pretty much up in the troposphere. There is a pretty constant bias of about 2 meters per second in the troposphere, which is very similar to what you mostly get for AVHR. And the RMS is a bit higher than AVHR because a lot of noise in these brightness temperatures. So from this point, I think the feasibility study can probably conclude that it's really feasible to do winds and try to assimilate them. And then you will get better winds in 1970 where you have no other observation. Okay, I need to speed up. So, Severi rapid scan, so some of you may know, some don't. So in Malmö, they would always know. So for the European sector, there is a rapid scan with 5-minute resolution. So, and we basically reprocessed all the rapid scan data for Severi with 5-minute resolution and calibrated that against the full disk Severi that has been calibrated against the YASI spectrometer before. So, and what you see is just an output of that, the radiance in a 13 micron, so CO2 absorption channel, and then you see this is particularly suffering from icing on the detector. And of course, this is correcting away this icing. So there's a whole record of 3 Meteosat satellites where you correct the radiance against this icing effect without physically modeling that icing effect. So we can take that out and you get a much cleaner series. So this could be used for doing winds, AMVs, which we will do next year. So it's still part of the C3S. This is not doing anything anymore. So AMVs from that in pretty high resolution, so that's going to be 15-minute resolution. And this is useful for European reanalysis. It may come too late in this season, but it's still useful for the next one. And it has other implications. So if we can do that for our rapid scan, oops. Can we do this also on the whole geostationary ring? So we really, this year, started a new project together with NOAA, really to go back in the deep history of the geostationary data and go work from scratch and rescue data. And funny enough, everybody, I think, has thought that over the Americas, so the 2 left columns here, the data have only about 3-hourly resolution. Well, that's actually wrong. So for most of the GCOS times, there were data that have never been digitized and never been used. So in reality, for the first 7 satellites of GCOS, it's 30-minute resolution. So we can use that. From GCOS 8 onwards, really they went back to 3-hourly, so nobody would understand why you would do that, but anyway, this is a fact. But they do partial scans of the full disk, And we find ways to stitch this together to end up really in a 30-minute resolution global data set. And the baseline will be something like 30-minute resolution, 2 to 4 kilometer. And we will amend that with polar orbiting data in the north and the south, so with using everything that flies from AVHR to SLSTR to get to a kind of an instrument-independent gradients data set for all common channels, which is very useful if you want to do ECVs. For the data assimilation, you may not need this mapped product, but you can use the individual GeoF CDRs. That will always be there. There's a gap in the Indian Ocean which we still want to fill. For the modern times, so from GOES-R, FCI now or so, we can even go to higher resolutions and beat the sampling down for 10 minutes, which has implications for many variables. One of them would be fire on the surface, which you can monitor much better. But it has also implications for the last thing I will show you, which is deriving information about mesoscale convection. And we had this talk about the Sahel precip deficit, and I think one part of the story is that the model at the resolution as you run it is not really able to depict mesoscale convection very well, I think. So in that sense, there's a method, this is long time known, to really monitor these systems, and you can basically derive the whole life cycle of each individual system. But the minimum that you need in terms of temporal resolution is 30 minutes. So unfortunately, the ERA5 outputs with hourly are not, it has been tested, it's not good enough to monitor these systems. So people would ask for 30-minute outputs on that. But it's a lot of cost, as Hans described. It's a lot of data. And so they can use this, doing this from satellites. And of course, you could expand that to the GeoRing. So what you get from that is something like this. So you can build a real climatology of the fraction in space of these systems, and you can really analyze trends. It's pretty stable, but you can also provide a lot of other metrics like duration of systems and maximum extension of these systems and how that changes over time. And that's a very useful input also for what is called nowadays ultra-high resolution climate modeling, because they suffer in how many systems they produce, too small, too big, too much rain, and so on. And this is a good baseline for validating and developing climate models as well. So I'll leave the summary up for you to read because the time is up, and I thank you for your attention. Right.
Jörg, thank you very much for your excellent contribution and for being impeccably on time. Back to you, Marie.
Yes, okay, so it's now my pleasure to introduce here in Malmö William Moutier, who will present, who is from the Royal Meteorological Institute in Belgium, and he will present climate data record of latent and sensible heat fluxes.
Thanks. So before to start, I would like to thank the organization for letting me the opportunity to present this climate data record, and to thank all my collaborators because it's a joint project. So I would like to thank everybody. So here is the outline of the presentation. So very classical, introduction of the variables and the characteristic of the climate data records, model description that we use, the algorithms, validation with an example, and conclusion and outlooks. So you may know that latent and sensible flux are key variables. You can find it in key topics like hydrological and climate cycle, monitoring climate change or desertification, water management, but also Earth radioactive budget. So it's a CMSAF project. We provide 3 parameters, latent and sensible fluxes, but also evapotranspiration. We cover different period with MVRI and SEVERI periods, so 1983 to 2020. So we cover the meteosat disk, so 60 degrees north-south, east-west, with a resolution of 0.05 degree on a regular grid. We provide hourly, daily, and monthly data, but also the monthly mean down eye cycle. And as I said, 38 years. So just a few words about the framework. So why the Institute also the advantage? So in the same building, we have 2 teams working in 2 SAF. So the land SAF with experience in land surface model with a very good near real-time product. And we have the CMSAF, so my team working in with a large experience in climate data processing and analysis, and we really want to use this complementarity to provide the best data sets that we can. Inside the CMSAF, we have, of course, different collaboration with the DWD, but also with MeteoSwiss to provide us the key input, like the surface albedo, but also shortwave and longwave radiation. We use ERA5 for meteorological data, so we use a linear interpolation to get at the desired resolution. And we use the algorithm of the Landsat, as I've said, and it's a tile approach. So basically, for you have a Meteosat image. For each pixel, thanks to the CCI input, we split the pixel in different tile. So you have the fraction of the different long cover. For each tile, we have this this method. So you have different modules according to the long cover, and we have an iterative method with a surface energy balance and to get the latent and sensible fluxes. So just a few words about the validation strategy. So we have 3 main steps. We compare the output with the reference dataset at station, so FluxNet and ECOS network. Then we look at spatially. So we compare with other dataset, satellite-based input products on reanalysis like ERA5 and GLDAS, on the Landsat product on GLIM, and we use a common grid at 0.25 degree. And then we have specific analysis of the monthly mean decentralized bias for the stability. So just quickly about the in-situ station. So we use 30 stations, well-established stations, already used by the Landsat, like that we have a good idea of the station. Data quality, ability to sample different climates and biomes. We use gap-filled data, and you may know that you have a surface energy imbalance. So we use a corrected version to compare the same thing, as we have also we have a closure. And we use exclusively good measurements, so a high quality control. It's important to keep in mind that even in-situ measurements are subject to typical error of 20%. So here is a comparison for daily product. Today I will just show the daily, not hourly and monthly, because we have the same conclusion. So I want to keep the time for other slides. So at the left you have the comparison for latent heat flux, right? Sensible heat flux. You have for each color a comparison with the different products. So in blue you have the CMSAF, green ERA5, orange GLDAS, violet you have the Landsat. Top panel, you have the bias. Bottom panel, you have the unbiased Rossby square difference. We use exactly the same matchup for all comparison, like that the metrics are comparable. So for the latent heat flux, you can see according to the stations that vary quite a lot. We are sometimes quite close to 0. But when we tend to have a higher bias value, we tend to underestimate around minus 10 watt by square meter. And we tend to underestimate as compared to other products, but we have a similar mean absolute difference, and we are still okay with the literature. Concerning the unbiased Rossby square difference, we are around 20, and it's very similar to other products, same range that we can find in the literature. Concerning the sensible heat flux, so it's right panel, we have a bias around 0. We tend to be a bit better than other products, even if I don't really like the term better, because each product has advantage and inconvenience. It's just to say, okay, we look at it and we are pretty good. We have a similar mean absolute difference. And concerning the unbiased Rossby square difference, we are around 28, which is really similar to other products, as you can see. And we are in the range expected with the literature. So now we can look at spatial variation. So here I just picked the year 2005. So you have the yearly mean 2005 for all the products. So top left CMSAF, so our product, the Landsat, then GLDAS, then GLIM. GLIM, we use an assumption of temperature of 20 degrees to convert the evapotranspiration to latent heat flux. Then you have ERA5 and ERA5 land. To the right plot is the latitudinal means. So in y-axis, we have all the latitude, and x-axis, the latent heat flux. For each color, you have all the product, and in blue, you have the CMSAF. So first thing, we can see that we have a good pattern. We follow exactly the same variations than other products, so that is very good with higher value around the equator. However, we tend to underestimate, especially in southern region. This region, it corresponds to deciduous broadleaf tree. So we know we have that. And it's really interesting to look at the comparison with the Landsat, because as I said, we have the same core model. So which can explain the difference is really just the input or parameter. So here you have the comparison of the sources between the CMSAF and the Landsat. So you can have key parameters that change, like the shortwave radiation, surface albedo, soil moisture, but also land cover. As we have a specific area where we have a lower value, I find it interesting to show you the land cover. So around the equator, it's really evergreen. So we have the same thing, but around where we tend to have lower value for us is deciduous broadleaf tree area. But for the Landsat, it's evergreen on or grass. So which means it's completely different modules that it uses, different parameters. So that explains also why we have differences. Then we can look at the sensibility flux. So they are the same graph, but for the sensibility flux, you have all the product. We don't have GLIM because they don't provide the sensibility flux. So here it's very good. We are really around the same value for all the different latitude. You are a bit higher around the equator for especially the corn in Africa. But clearly we have the same order of magnitude and we are really at the middle of other products. So just an example of how we can use the two variables. So I know it's a bit a lot, but it's the evaporative fraction. So it's the ratio between the latent heat flux and the sum of the latent heat flux and sensibility flux. So here it's Western South Africa in winter, so in June, for all the year of the dataset. And you have the average just below the map. And for this region, you have to know that to supply the need in water in summer, that really depends on what you get in winter. So that's why I pick winter. And it's interesting to see the year 2017 because the value is the minimum, is the lowest value of evaporative fractions, which means that we like almost no evaporation. You can see it's very rare, red in all this region. And even the years before, it was slightly red. And at this period, you may know that it was really a water crisis. Here is the image of one of the reserves in this area, and you can see that the next summer you have almost nothing in 2018. And why I picked this example is basically because I was there at this period. It was during my postdoc at Capton, and I really undergo this water crisis. We were really afraid. We have just 50 liters by day by person, which is very low for shower, toilet, everything. We are very afraid to have to running after water and don't have tap water anymore. So it was really a crisis, and I find it interesting that with this type of data set you can follow this type of event. So then I present you the stability of the CDR. So you have two key questions. Do we have trend and do we have jump in the dataset, especially at the transition between Meteosat first and second generation? So here you have the deseasonalized bias of the latent heat flux compared to the different datasets. So ERA5 in green, Landsat in violet, GLDAS in orange, and GLIM in blue. You have the trend value for each comparison. The red axis at the right is for the different satellites that we use. We don't really see the mark. I don't know why, but anyway. So it's interesting to see that we don't have any jump, especially at the transition. So we were very happy about these results. So for the full disk, we have a very good stability for the latent heat flux. Concerning the sensibility flux, it's a bit more difficult. We do see a transition. So what I did is I split the map in different regions. So you have South Africa region, North Africa, Europe, and South America. So here are the results at the bottom left for Europe and South America. And we see that we are pretty good. We don't have a jump at the transition between MFG and MSG. The slope are very good, so it's really good. We do have a transition for North Africa, which is quite important in this region. So what I did is I simulate my output with input base from MFG on MSG, and I made the difference. So that is a plot here at the bottom right. And you can see that you have very certain regions that are really impacted. On its warm surface with high reflection and basically desert area. So what could be how you can explain this error? So for my input, it's due to the albedo on shortwave radiation. So I have a strong relation between the decentralized bias of the albedo and the sensibility flux. And it will be due to a miscorrection of narrowband to broadband visible canals for this type of surface or a miscalibration of METEOSAT canals. That will explain the result because you have higher variability in the reflection for this type of surface. So it's a work in progress, and we will try to fix that for sure for the next version. So in a nutshell, important further of this data set, we have a unique combination of high spatial and temporal resolution. So it's very suitable for climate analysis, especially when we cover 38 years with over a large domain of the METEOSAT field of view. It's highly complementary with other data sets, so that is really an important point for me because, as I said, we don't have a perfect data set, so it's important to combine everything and try to get the maximum information from each. To conclude, we also successfully validated this data set by comparing at station, but also with other products and the literature. We have very good stability for the latent heat flux, for a good stability for the sensibility flux for most of the map, and we really well define where it's wrong, which is also important for the users. And for the outlooks, so we will try to fix those regions, so improve the sensibility flux stability. We will work, of course, on the energy repartition to reduce the underestimation, and we will estimate globally, including water. And the data set will be released by the end of the year and fully available on the CMSAF website. Thank you.
Okay, thanks. Thank you very much, William. I think I have to hand over to Bruno right now. Ali, I think it's your turn for the next presentation.
Thank you very much, Marie. Our next speaker will talk about monitoring soil moisture from space, a European perspective. Please give a warm welcome to Joaquin Munoz Sabater of ECMWF.
Okay, thank you. Good afternoon. So I'm going to give now a presentation about soil moisture from space, and just focus mainly on the European efforts. And just a little disclaimer here, actually don't intend to provide a absolutely full, complete view of soil moisture from space, because certainly in 10 minutes it's impossible. And also, I might make some errors. Please give me feedback at the end if you find any. So, roughly speaking, we are talking about 75% of the land precipitation that globally enters the soil. But that will depend on what is the state of soil moisture at that moment. So if, for instance, we've got a soil that is saturated in water, then the precipitation will just simply run off. A characteristic which is very important of soil moisture is there a very high variability, both in time and in space. And this is going to be controlled by all the different drivers depending on the scale. So for instance, if we have a large patches of soil moisture that looks more or less the same, that could be, for instance, be the consequence of a front of precipitation that just sweep in one area. But then if we go to the local scale, then we've got things like the soil texture, the structure of the soil that is going to govern this, what is the moisture at that moment. All in all, we can have, just in a few meters, a very strong gradient of soil moisture. So, of course, that poses a lot of challenges at the time of monitoring soil moisture at different scales. Why is soil moisture important? Well, for hydrology, obviously, because it's the main source of water supply. It will also will be the source that will replenish the underground reservoirs. We use it in NWP since decades ago. We make sure that a very good initial condition of soil moisture, they are important because the short-term and medium-range weather forecast depend on that too, and even a larger time scales. And agriculture is also obvious. It will also provide all the water which is needed for all the cultivated and non-cultivated agriculture, and etc. Users, we've got a very wide variety of them, from meteorologists, hydrologists, to water resource managers, forest managers, also for monitoring extremes. Today there was the talk by Marek about droughts, so that's also another important one. But all in all, soil moisture is really considered today one essential climate variable, and as such, we need to monitor it continuously and globally. Now, to monitor it, we could just look at in situ networks, which is the best probably. It is where we have the ground truth, but as usual, and it happens with many of the variables, they are generally they are unavailable, or they are sparse in space. Sometimes they are often short-term. There's no guarantee that they are continued in time. And from space, the most sensitive part to soil moisture of the band of the electromagnetic spectrum are microwave, and in particular, low-frequency microwave. For instance, they are transparent to the clouds, and they provide, as many other satellites, it's all the 24/7 measurements. So we are really gifted to live in this era of satellites. Microwave measurements, they are particularly sensitive to the dielectric properties of the soil. And this is very important because this is the key. The key is really the very strong contrast between the dielectric constant of water, which is very high, and that of the soils, which is really low. So when we're looking for microwave and we're looking at the soil, we will see really a big contrast if we have a patch of bare soil and a patch of wet soil. But also in the microwave signal, you can also find the roughness of the soil impact their own signal, and also the vegetation. The vegetation also is embedded in the own signal. So it's quite a complex signal to disentangle. Now, there are two main ways to measure soil moisture from microwave. One is using active sensors. So we are talking here about radars. So radars, in general, what they do, they emit a pulse of energy to the target, and what the radars measure is the backscatter energy. So in other words, the reflectivity of the target. In the radiometers, which are passive, this is the passive sensors, what they will measure is the self-emission of the object. So, and this is quite incredible because the sensor will receive a tiny amount of radiation, and from that tiny amount of radiation, we have to really disentangle the signal and to see how much water there is in the soil, with uncertainty that sometimes is just a teaspoon. So this is, I find it fascinating. And both radars and radiometers, they measure basically the same variables. So they are very much related by the law of Kirchhoff. So basically, if soil moisture is increased, what we would do is that the electric constant of that soil will be increased, and that means that the reflectivity also, so the backscatter signal will be increased, and the emissivity, on the other hand, will decrease. So then that the brightness temperature, which is what it measures the passive sensor, it will also be lower. Now, if we look at the active side, we've got already a long history of use of data to derive soil moisture. So all started in the ERS series, and we start with a really moderate resolution, a moderate daily coverage. And already in 2002, we've got already the first global soil moisture data set. And it is not done before, because remember that scatterometers, the main objective is not measure soil moisture, but it's measure wind over oceans. So this is a subproduct, but still we can derive it from there. Of course, technology gets better, algorithms that get better, and then we've got all the series of METOP satellites. So in the METOP, we increase resolution, we increase also the daily coverage, and we already in 2008, we've got the first operational service of soil moisture. So this is produced and delivered by the EUMETSAT Hydrology Satellite Application Facility. And today we're receiving products like near real-time, offline, and data records in an operational manner. Looking at the future, it looks very good because we've got all the METOP series, which also will include new, better resolution, more increased coverage, etc. Looking at the passive side, before the SMOS era, there are also another sensors like SSMR, like AMSRE. I don't mention it explicitly because they are from, I'm trying to focus only on the European part, but I think SMOS deserves a very special mention because this is the first satellite which is, it comes out of Earth Explorer call that is specifically designed to measure soil moisture of the land. So it does a resolution of about 35 kilometers, and you've got here an example on the right-hand side. SMAP is shaded, and I did it on purpose because you already know it. It comes from NASA, but I think still it deserves even a shadow, but a shadow mention, because it's also another satellite which is specifically designed to measure soil moisture. So this is the American part. And in the future, we can also look at the CMAR, which is also, it will include a L-band, is part of the Sentinel expansion missions. And for the same reason, I should also have added ROS-L in the active part, which also include a radar, and I didn't include it here. Now, active measurements, they are more sensitive to surface roughness, also to vegetation structure, okay. They are all, but maybe they are less affected by the surface temperature. And mainly the main advantage is that they have higher resolution. So on the left-hand side, you've got a plot. It's just simply moisture over one region with a radiometer and with an radar. So on the bottom one, you see more structure as it is. So you see much more structure there, but be careful with the signal because here it looks that it is a drier patch, but it's not drier. It's simply that's the signal of the vegetation, which increases the emissivity of the signal, and then apparently it will look like it's drier. So you have to be very careful when interpreting these signals, and also we need good forward models to make sure that we represent it correctly, the mission. Then low frequency is passive, so they have better penetration depth, they are more sensitive to soil moisture, but they could be affected more by radio frequency interference. And that was the main problem of the SMOS satellite. So here you can see, this is the standard deviation of the observations over a month, so more or less the variability over that period. This looks very, very suspicious. It's quite artificial, and this is created by artificial sources of radio frequency interference. On the right-hand side, we apply some filters, and then it is a cleaner picture, but of course, all that area, you lose all the signal, so you don't have any more soil moisture there. Now, why not taking the best of both worlds, of active and passive, and create a multi-sensor fused product using all the active and all the passive data that we've got. And this is what is done in the ESA CCI soil moisture project. So it takes all the series of data using active and passive sensor, and then we produce data records, long data records since 1978, either only with passive data, only with active data, or just with a combination of them, which is a blended product, which is a combined, and theoretically, it could overcome some of the problems of the individual sensors. Now, in C3S, we're trying to go a little bit beyond that. So we broker the CDR. So this is a soil moisture data set. And then we try to extend it in time. So we make sure that the data is always up to date, and we can really serve those users that also use their operational systems. So the data providers are mainly EODC, TUV, and Vandersat. Now, to download the data, we offer data records in 1978, a quarter of degree in a regular grid, and we've got all the three streams, only passive data records, only records with active data or a merged product, and always updated CDR, which I think is very important for operational users. The data also, we have a lot of independent quality assurance, which again, I think you have already heard several times during this morning that also quality assurance is very important for C3S to provide authoritative data, and comprehensive documentation also that we offer for all type of users, also either expert or non-expert, they always use the data. And this is my last slide, so I just wanted to make, again, looked at it's very important for us quality assurance. So here is only the new data records, the updated data records. We always make sure that it really is of the best possible quality. And every time we update a new data record, it always provide a data record which is even better than the previous one. So this is what we do with this. I'm not going to enter in details because I don't have time. And just, and I think I've finished that. Only my summary, which I think you just can, I leave it there just for everyone to read. And yeah, that's all. Thank you very much.
Joaquin, many thanks. Allow me to encourage you once more to do send us your questions and comments over Slido, and we'll address those after we finish the presentations. Our next speaker will talk about temperature extremes, the 2022 extremely warm summer over Europe. What can we learn from the satellite perspective? Formerly, he used to work for the Portuguese Institute of Sea and Atmosphere. He has now been taken over by C3S, and his name is João Paulo Martins. Please give him an applause.
Thank you for, oops, I don't think, thank you for your presentation. So this presentation reflects a bit the things that are happening with my life right now. So you see a former, the former template. This is the EUMETSAT template. And it's also nice to be speaking to Malmo, because, hi Malmo, because this abstract was initially submitted to the EUMETSAT conference. So I will show you some information about LSTs and how we can use it to monitor warm extremes. LST has gained some popularity in the news, in the science blogs. You can see a bunch of articles, a bunch of examples of articles that are already available in these type of websites. And we have to be very careful when you show these pictures, because they look very pretty, but they don't tell you about 2-meter temperature, which is the variable that we use as scientists to monitor heat extremes in general. So I will try to give you a perspective of what different information can LST give us to monitor these type of extremes. So this is really weird. Yeah. So I was based in the Landshof, and this is the catalog of LST products that we had there. This is how you can access the website. And you have different products based on different satellite platforms, both polar, both geostationary, and depending on your application, then you could select the data set that fits your purpose best. For the purpose of this presentation, I will use the LST All Sky, which is a relatively new product. It's based on MSG measurements. This is what it looks like. So this on the left you have the standard LST product, and on the right you have these mostly gap-free products. Those gaps are caused by clouds. Because in general, infrared measurements cannot see through clouds, of course. And then we use the scheme that William just described for their evapotranspiration and the sensible heat products. That same scheme also returns the skin temperature that we use to fill in these gaps. So basically, we have the level 2 product that is filled in with this information from this surface scheme. We now have it as a very long data record. It's now available since 2004, every 30 minutes. It's not really available on our website yet, but you can request its usage to use it to the Landshof. We will make it available hopefully in the end of this year, because we are still finalizing the validation, the formal validation. And this is how it looks like for the anomaly. So what you see here is the summer LST anomalies for the warmest years on our data record. So 2018, 2019, 2021, and 2022. You can see how 2022 looks really exceptional compared to the other warmer years. It's very overwhelming how red the map looks like, especially there in the Hungary and the Romania regions. And so you can see that this magnitude of this event was really unprecedented. It wasn't always like that. So it started as in June as a already big anomaly, but the anomaly grew really big in the August, especially in the Western Central Europe. The anomalies reached at around 10 degrees in August. And then we have to ask ourselves, can we use LST to study heat waves? Is this the information that we want to study? So what we see here are differences between the LST and the skin temperature on the left. The skin temperature from reanalysis, which is a standard data set to study this type of thing. And then the difference between the LST and the 2 meter temperature. So this is the differences between the anomalies. And what you see is that in the beginning of the summer, you see that they're mostly comparable, except for a few regions. And then the differences between these data sets grow throughout the summer. And especially the LSTs anomalies are much higher than the 2 meter temperature anomalies here in August. And here you see also that the ERA 5 underestimates the skin temperature. So compared to LST, LST is much warmer. This is a well-known result. We have some work on this in our group. Okay, and not too much. Can you go back, please? Yeah, another one? Yeah, no, sorry. No, this one, sorry. So this is, again, the same differences we've seen before, and those are the anomalies for vegetation, so fraction of vegetation cover. It's also a product from the Landsaf, and soil moisture from the HSAF. And you can see that the largest differences here can be associated in general to those patterns of negative anomalies there. So when you have negative soil moisture and negative fraction of vegetation covers, that's anomalies of those quantities. That's when those differences become greater. So this gives you some information, because if 2 meter temperature can be compared to EOPS, for example, and you see that they are good, they are realistic. And when you see, and LSTs are also observations. So when you compare LST with 2 meter temperatures, you see that these differences are actually physical. So they should be different. That's what I mean. And they are different because the representation of vegetation is not correct, because you have an anomaly that the European Center model doesn't see, because the vegetation is fixed. Then we also computed some diagnostics of heat waves. We define a heat wave over like a period of 3 days where the maximum LST is above the 19th percentile. And then we define this metric, the daily magnitude. It's just the difference to the 25th percentile divided by the interquartile range of the fold distribution. And then we can sum these daily magnitudes over a period, for example, the summer, to get the heat wave magnitude index. This is a standard metric used in the heat wave studies. And here on the right, you can see some of the diagnostics that you can obtain with LSTs. So, for example, you see the number of hot days for 2022. So these regions here, you can see that there are some regions where the numbers were above 50, 60 days, 60 hot days. And then the corresponding heat wave magnitude index here on the right. And here you can see the temporal variability of these events. So you can see these peaks here, which correspond to large areas, large fractions of land area over Europe covered by extreme temperature conditions. So you have spatial and temporal indicators. And then this is the only slides that I already include 2023. You can see that this is a ranking of the LST anomalies that you can derive using this data set, so from 2004 to 2023. And you can see that 2022 really stands out, both in terms of the LST anomaly, the area covered by extreme temperature conditions. It only rivaled with 2018, more or less. And then here the number of hot days also very big compared to the closest contestants. And then this heat wave magnitude index, it also stands out very evidently compared to the other years in the ranking. So, just some take-home messages. You can see that the All Sky data record is allowing now to monitor these heat waves, because you already have almost 20 years of data, and you can compute relatively robust anomalies. You can see that the satellite observations provide realistic view of the surface energy balance quantities, basically because you have better clouds when compared to models and actually reanalysis. And we also see that in drought conditions, LST anomalies are increased and are greater than the 2-meter temperature anomalies, and that's expected. And then we can see that the summer of 2022 was actually exceptional in terms of a number of heat wave metrics. And finally, I would like to stress that this cross-cutting anomaly analysis can actually provide additional confidence in the consistency of each data set. So this, I think, could be part of the AQC function of the CDS for satellite ECVs. That's an idea that I leave now. So thank you.
Thank you very much for your contribution. Our next presentation is pre-recorded, and it is by Patricia de Rosani. It's about 5 minutes. Patricia works for ECMWF, and the title of her talk is Next Generation Reanalysis, Results from the Ceres Project. The presentation is about 5 minutes.
Good afternoon. The title of this presentation is Next Generation Reanalysis, Results from the Ceres Project. Ceres stands for the Copernicus Climate Change Service Evolution. It's a 4-year project from 23 to 26, funded by the European Union and coordinated by ECMWF. We are 12 partners in Ceres, indicated at the bottom of the slide, and I've indicated here the name of the scientific work package leaders. In Ceres, we support the long-term evolution of C3S, both for regional and global climate reanalysis and multi-system seasonal prediction, towards an Earth system approach with a focus on land-atmosphere coupling. So this is illustrated on the right. Moving towards an Earth system approach means that we account for several Earth system components using a coupled modeling system. And because of the specificities of each of these components, there are different time scales, there are different spatial scales, we use a dedicated data assimilation system for each of them. And we use coupled data assimilation to ensure the consistency of the initial conditions that we will provide to the coupled model. There is a key role of interface observations in coupled data assimilation system to constrain the Earth system components across interfaces. So what is the rationale for land-atmosphere coupling in Ceres? So developments of land data assimilation systems in the past 20 years improved a lot soil moisture data assimilation, snow data assimilation. They also allowed to bring satellite observations in land data assimilation systems, but still the systems that we currently use rely on relatively simple approaches and which are univariate approaches. In addition to this, relatively little effort has been dedicated to land atmosphere coupled data assimilation, in contrast to what has been done for ocean atmosphere coupled data assimilation, despite the fact that near surface conditions over land are of critical interest to users. And the climate bulletins from C3S, for example, attract a lot of attention, with a special interest for surface air temperature anomalies, for instance, and an increasing interest in other land surface variables, such as soil moisture, which is illustrated on the right. What do we do in Ceres? We develop land data assimilation systems and couple land atmosphere data assimilation toward the fully coupled Earth system approach that we want to use in the next phase of Copernicus. We explore machine learning-based observation operators to improve the exploitation of satellite observations with a focus on interface observations. We are developing multi-decadal representation of evolving vegetation and lakes, building up on the CONFES project, but extending further back in time for the vegetation and extending to the lakes. We are delivering prototypes of seamless reanalysis and multi-system seasonal prediction. So it's a key aspect of SORIS to have a high readiness level in our developments so that they can be used already towards the end of this phase with ERA6 land and in the next phase for the global and regional reanalysis as well as for seasonal prediction. So we are targeting, for example, ERA7 and System 7. And we develop novel diagnostic tools to assess physical consistency of Earth system reanalysis and prediction. This slide illustrates some of the ongoing activities conducted in SORIS related to snow data assimilation developments. A well-known issue in ERA5 is a step change in 2004 when we started to assimilate snow cover. You see it on the right with this plot. This is from 1969 to recent periods, the Northern Hemisphere snow depths, the mean value. ERA5 is in black, and you see the change in 2004. So snow data assimilation reduced the positive snow cover bias, but it amplified the negative trend that we have in ERA5. ERA6 will benefit from various snow model and snow data assimilation improvements. It will also benefit from assimilation of snow cover from earlier periods, from 1982 with the CCI product. So based on these developments, we produced the first ERA6 non-prototype in SORIS. It is covering 1939 to 2022. And this is the red line here, where we don't have this step change in 2004, and we don't have a discontinuity in 1982 when we start assimilating snow cover. To summarize, we are improving the quality and consistency of the C3S tools, directly addressing the evolving user needs for improved and for more consistent C3S Earth system reanalysis and seasonal prediction products. And I invite you to see the poster on SORIS for more detailed information. Thank you very much.
Patricia, thank you very much. This concludes the first part of this session. The second part will deal with climate challenges with a focus on droughts, impacts, and monitoring. But since this is a 2-hour-long session, I suggest that we energize ourselves and revitalize the capability to focus. And I invite both audiences in Brno and in Malmö to please join us standing. And I ask the AV team here to put the camera on the stage so I am visible to Malmö. Am I visible to Malmö? Question to the AV team, am I visible to Malmö? Maybe Malmö can applaud if I am visible. I guess they are. All right. So, just take a moment to focus on your breath. You can close your eyes if you want. You don't need to ignore thoughts. Just let them pass by. Now breathe in deeply through your nose and breathe out through your mouth. We do it again. As you breathe in deeply, you lift your right arm. Breathe out and put it down. Do the same for the left arm. Breathe out and put it down. Now you lift your right knee while you breathe in. Breathe out, keeping your balance. Lift your left knee while you breathe in. Don't put your right knee down. And put it down again. Now take another moment to focus on your breath. Breathe out. Now I want you to make eye contact with people around you. Do it subtly, but do make the eye contact. Go ahead. No talking. You can also look farther away, 3, 4, 5 rows behind you, as long as you make eye contact. Now get back to your original position. Take another deep breath. Breathe out. Next thing you do is you put your hands together like they do in Asia. You breathe in, and when you breathe out, you put a lot of force on both hands. Excellent. Keep those hands together. Now you make eye contact and you bow like a samurai to people around you. Also, people farther away. The deeper you bow, the more respectful you are. So lots of bowing going on in Brno. Good. Now, breathe in one more time deeply. Breathe out. Now we're going to put it up a notch. Now you just high five everyone around you. And do it quickly because there's little time. Go for it. High five. Give yourself an applause as you sit down. Thank you very much. Mindful of the time, let me quickly, now that you're better able to focus, announce the next speaker. And he will talk about climate change adaptation and tackling droughts in the Danube River Basin. His name is Zoran Major, and he works for the International Commission for the Protection of the Danube River. There he is. Give him an applause, please.
Thank you very much. I hope that you are all invigorated and woken up. Now I will not go into so many technical details like some predecessors, because this is more about supporting policy making and transboundary cooperation in the Danube Basin. But first, to introduce you to the Danube Basin itself. It's about 800,000 square kilometers. It's encompassing 19 countries or pieces of these countries, about 80 million people, and it's a high diversity environment. There are contracting parties to the ICPDR. There are 14 countries, out of which 9 are in the EU and 5 are hopefully on their way to join, but they are still non-EU members, which means that there is a lot of effort that has to be put into cooperation, which has started on this level or approximately at this level some time ago. Back in 1994 in Sofia, Bulgaria, we had the Danube River Protection Convention signed. That was the beginning of the process, which entered into force in 1998, and then we had establishment of ICPDR expert groups. So how is it being done? I'm working in the Secretariat in Vienna, where there is a very small group of people, like 6 technical experts and the Executive Secretary. All the work, physical work, is being implemented in the countries. So we have hundreds, if not even thousands, of technical experts, which are divided in 6 different expert groups, then the task groups, and so on, which are dealing with certain topics like the pressures and measures, like the floods, like the river basin management, information management, and so on and so on. And we have these expert groups and secretariat in place, and in 2000 in Sofia, non-EU member states have a pledge to implement the EU Water Framework Directive and the Floods Directive as possible, as far as possible. So for them, it's not the legal obligation, but for them, it's their own free will contribution. But they are in this process adopting the standards and learning about the processes of reporting and cooperation. So in ICPDR, transboundary cooperation is the key to effective addressing of climate change, and it's reflected in many topics that we deal with. Here you see some of them. We have decades-long transboundary monitoring network. So this is about hundreds of different monitoring stations which are observing hundreds of different parameters, discharges, water flow, the chemical substances observed in water, water temperature, and stuff like that. This is available in our information system, and this is also something that even you as experts may have some interest in. On top of that, we conduct periodic joint Danube surveys every 6 years with participation of experts from all of the countries and stakeholders from throughout the Danube Basin institutes of various types. We record data on numerous chemical parameters as well as on biological and hydromorphological conditions of the river watercourses. Then we have the accident warning system, which is quite important. It further increases the resilience of the aquatic systems in Danube Basin, and special attention is given to addressing the issues related to water users and to foster coordinated efforts in application of commonly developed guidances. So this is a difficult task, of course, because the sustainable hydropower, you know, the people from the hydropower and the energetic sector, they have their own goals and agenda, but we managed somehow to get to develop and then to respect, let's say, common guidances. We don't have the mechanisms of pressure or punishment or implementation, but we build this on the live and good constant incentive and fostering the cooperation. And then, on the other hand, there is a tough cookie also with sustainable agriculture. You know that agriculture has a lot of impact on the quality of waters and the quantity of waters as well. And we have developed a manual and good practices in sustainable waterway planning from the navigation perspective. But when we talk more specifically about addressing the issues of drought and water use, the ICPDR has developed, together with relevant stakeholders, several related policy papers, such as guiding principles on sustainable hydropower development, where we take in account the aspects of the water scarcity and droughts. Then policy paper on sustainable agriculture, again addressing some topics from this perspective. And then joint statement on guiding principles of development of inland navigation. Further on, all countries of the European Union are using a river basin approach for water management since the adoption of the EU Water Framework Directive. And it's providing legal framework to protect and enhance the status of aquatic ecosystems, prevent their deterioration, assure long-term sustainable use of water. So this approach is origin of two crucial documents that we are periodically renewing. One is the Danube River Basin Management Plan on the left-hand side. Currently, this is the third edition. So each 6 years we had in 2009, 2015, 2021, and we will have one again in 2027. And then Danube Flood Risk Management Plan. This is now the second edition, which is with the same time rhythm produced. These documents are accompanied with yet another very important document, which is in focus of interest for today's presentation, and that is the Climate Change Adaptation Strategy. Now, this here is the second edition of that. So we had one in 2012, and then we had a renovation of that in 2018. And I'm pretty confident that we will have in next year another one, and that inputs that we have seen today will probably play some significant role in that. ICPDR is leading in this way as pioneering river basin organization regarding climate change adaptation. We are including the following approaches, which are based on the principles as laid down in the climate change adaptation strategy, and that is fostering integration of climate change adaptation measures into water planning, not only on the basin level, but on the country, on the national level as well. Supporting consistent actions in transboundary context by providing toolbox of measures. So one of the results was that we have developed some sort of a toolbox which is available to all of the member states and to all of the technical experts, where they can look at the typical solutions they can use when tackling the issues of the climate change. And currently we are finalizing the development of the one information system we are finalizing, that is Danube HIS. I'm involved in that. There is a platform for exchange of the basic hydrological data observed in all 14 countries in a common format, in a standard database, and in one web portal. So ICPDR is developing this so-called Danube HIS, Danube Hydrological Information System. It will be made available to stakeholders, interested experts, and even the general public based on, of course, some restrictions from the data providers, which is always respected. but mostly it will be made available. It will consist of a data which is the water level, the discharge, the water temperature, and precipitation, daily and hourly data from hundreds of stations in the Danube Basin. And there will be a web interface which will enable you to explore the data and even to download it if possible. In addition to this, we have identified in our plans the significant water management issues. By previous reports, these were the organic pollution, nutrient pollution, hazardous substances, and hydromorphological alterations. But lately, we have realized that we need to put additional emphasis and make more attention, and we have promoted these effects of climate change, drought, water scarcity, extreme hydrological phenomena, and other impacts as one of our most important topics in our plans. The end goal, of course, is to remain and to achieve resilience and ultimately sustain the ecological and cultural values of the aquatic environment in the Danube River Basin. And special focus will be on the preventive measures to mitigate the impacts of climate change, to adapt to it, and to minimize the related damages. So the SWIMI report, which we prepare, is dealing with the significant management issues. The result is more attention will be given in the plan to measures related to prevention, to vulnerability reduction, to planning, and to preparedness. We are making efforts to step away from managerial practices that were reactive based on the incidents and shift focus more to the planning and to the protection, to move from crisis management to risk management. And that was also one of the recommendations we had in the drought-related project, Dry Danube, maybe some of you know about that one. The cross-cutting character of this climate change adaptation SWIMI is related to other SWIMIs, and in all other topics, we always also look into this. Therefore, the respective measures must achieve desired results without negative side effects, even from other topics to the climate change. So ICPDR is integrating climate change concerns into the approaches of other significant water management issues. And climate change in the Danube Basin, okay, we have noticed what was happening. I will go quickly through this because I don't have much time, but you're familiar how it was, especially in 2022, and then in 2023 we had these floods and extreme downpouring events in Slovenia, for instance. And I will let you all look into these trends, which are mostly called red and negative, for the certain aspects like changes in forestry, agriculture, floods, and low flows. So going through all this, not to steal too much time, this is the last thing I would like to say, and this is the considering the droughts at 25th Ordinary Meeting in December 2022, which is the main meeting of our organization, annual each December, and at the 21st Standing Working Group, which was in June recently. We have decided that droughts and low water is considered as important for further actions by ICPDR. The internal ICPDR workshop was done on the droughts and low water level in Belgrade, 16th of June, and we have agreed to develop overview on approaches, activities, and policies in Danube, and plan to implement processes to update the joint statement, also addressing climate change and drought accordingly. So we are looking forward to learn more about your products and services that you can offer, and also to offer you more info on our activities and needs, and all in sense to keep the Danube cleaner, healthier, and safer for us all. Thank you.
Zoran, thank you very much. Our next presentation will be about monitoring and forecasting drought conditions, the experience of the Copernicus EMS Drought Observatory. The speaker is with us online. His name's Juan Acosta Navarro of JRC. Juan, are you able to hear us?
I can hear you fine. I hope you also hear me well.
Brilliant. I'll give you the floor, and thank you in advance for being mindful of the time, given our very tight schedule.
Sure.
Here's your applause.
Thank you. Thank you very much. So on behalf of the droughts team from the Copernicus Emergency Management Service, I'd like to thank the organizers for this invitation and for allowing us to showcase many of our products and share our experience. So I think, next slide, please. The previous speaker already set the stage and introduced very nicely the importance of droughts and why they're becoming so relevant from many perspectives. We know that they are increasing in frequency and severity in many parts of the world, and in particular in Europe as well. They are a transboundary problem, and they are a global hazard that has a very substantial economic, societal, and environmental impacts. In fact, it's one of the costliest natural hazards at present day, and these trends are projected to increase dramatically in the coming decades. What we offer is early warning. We monitor, we forecast drought, but also their impacts. And we use a wealth of observations from satellite data, from in situ sources, and also from hydrometeorological modeling to build our indicators of drought. But we also do some research on risk assessment and other aspects of droughts. Next slide, please. We have two dedicated web services that provide our information that we keep near real time. One is the European Drought Observatory, started more than 10 years ago. And the other one is the Global Drought Observatory, which is sort of a mirror of the European one. It was started more recently in 2016. They're both part of the Copernicus Emergency Management Service since 2018. Next slide. We have just a few months ago deployed this more responsive web mapping tool, which combines both the European and global data, and is intended to be a much lighter version for users who don't have, for example, a very good internet connectivity, or if you want to consult from your cell phone. This is a much lighter version with all the same functionality that we had in the previous web services. So what you see in this picture is the combined drought indicator, which is our main indicator for agricultural drought. And it gives different levels of warning depending on a combination of precipitation, soil moisture, and vegetation properties that I will talk more in the coming slides. So if you're curious about it, please go to our webpage and have a look at it. Next slide. So starting from the water cycle, we monitor the different indicators. So the ones highlighted in red are the parts of the water cycle that we're currently monitoring on a near real-time basis. Next slide. And if you see, they cover the different definitions of drought, from going from meteorological to hydrological and through agricultural. So each one of these indices is dedicated to understanding how the drought situation is for each one of these different definitions of drought. But next slide. Most importantly, we are mostly focusing on agricultural drought because this is where the impacts tend to be the largest. So if we go, next slide, we go back to the combined drought indicator, our flagship product. Now we are in the third version 3, and it's this indicator for evaluating agricultural drought and its impacts on vegetation. Now we have a high resolution of 5 kilometers. This is real-time data provided every 10 days since 2012, and it can be visualized through these interactive maps in our web server. Next slide. And this indicator is made from the information extracted from SPI, so a standardized precipitation index of 1 month, 3 months, the soil moisture anomalies, and the fraction of absorbed photosynthetically active radiation to give different warnings, as I mentioned before. And the warnings are only active in this current version during the crop growing season. So there are no warnings, even if you have for example, a signal in one of the indicators. Next slide. The current version is using data from ERA5 for precipitation. For soil moisture, we use the least flood model, which is an in-house model developed here at JRC and operated by ECMWF at the moment. And for the vegetation, we use the satellite information from VIRS. The plans for the next version are including Sentinel data for FAPAR, if possible. And we're also studying other sources of data for soil moisture that are perhaps satellite data. Next slide. As was mentioned in one of the previous talks, and I think the case was the summer of 2022. It was an extreme summer, both in terms of temperature, but also of drought, and they were compounding continuously. So we have created this index that is called heat and cold wave index, for monitoring heat waves and cold waves on a near real time. So you have two examples there. One for August 2003, it was the extreme summer of 2003 in France mostly. But also we had the last heat wave this summer in Europe was just a few weeks ago. In Southern Europe, it extended over a wide area in the southern parts. And an indicator gives the duration of the heat wave based on combination of both maximum and minimum temperatures from weather station data. Next slide. We also provide information for standardized precipitation index in the coming months. And this is SPI1, SPI3, SPI6 warnings. Is based on the seasonal forecasting system from ECMWF. And we have an example here of, again, 2022, and the extreme summer, or late spring summer. We have observed anomalies, observed SPI indices on the left, and in the center, the forecasted indicator. So we have in this particular case, it was a very good match. And next slide. We are looking of currently many ways of how to enhance our forecasting capacities with different approaches. One quite simple is to also integrate past and future information in a way that the forecasts are also aware of the situation you are in now. If you have had, for example, a period of very low accumulation of precipitation, the conditions in the future may matter much more than if you're well above the average, like what you see, for example, in that slide there. It's for this year in some location in Southern Europe. We also are looking on other indicators such as SPI, which include the evapotranspiration and the use of machine learning in combination with different techniques to sample from large ensembles, such as the one available through Copernicus C3S. And again, we have a team dedicated to detecting and attributing extreme drought events on a near real time, because this is quite important information once the drought has passed. One of the key questions is to know how much has climate change made this event more likely. So this is one of the activities. Next slide. And the last but not least is the work going beyond the hazards. So enhancing resilience and adaptation to drought conditions. This is a European project. It's an initiative from DG Environment and working together with DG JRC. And there are three main objectives. One is enhancing the drought risk assessments. And this is by doing a multi-sectoral risk atlas that is going to be published very soon and presented to the European Commission in 1 month from now. Again, and together with a impact database that will be available openly through our web service. And it's the first of such kind because it's a multi-sector impact database. And another thing is that the project aims to fostering connections between the different drought practitioners and to establish and to help establish drought observatories in member countries. Next slide. And this is my last slide. So once there is an important drought, we provide analytical reports on it and with a much in-depth analysis of the drought conditions, all the indicators and the impacts of that particular drought, not only for Europe but also on a global scale, and also daily maps that are available through the Emergency Response Coordination Center of the European Union. And with this, I would like to finalize and thank everyone for the attention.
Speaker will talk about synergies between CAMS and C3S on hydrological modeling. Sean Harrigan, ECMWF, the floor is yours.
Hello, everybody in the room and also in Sweden. I work for ECMWF, both as a technical officer on the water service, but also as a hydrological forecasting scientist within the Copernicus emergency management component that we also run at ECMWF. Today I'll give an overview of some of the 6 synergies we have currently ongoing within both of these services. Yes. Okay, there we go. Back. So first, I thought I would give a brief overview of the Copernicus Emergency Management Service. Juan mentioned the drought component, but just off, today we're obviously talking about C3S, but the CAMS is also one of the 6 services. It's been operational since 2012, and really the components of CAMS is providing both Earth observation and rapid satellite mapping of the current situation, monitoring and the ongoing risks, as well as an early warning and monitoring component of some of the most important natural hazards or man-made disasters. Mostly through, as we heard Juan just previously, with droughts, but also the floods and fire across Europe. It's implemented by the Joint Research Centre based in Ispra. And one of the main users of this output is the Emergency Response Coordination Centre from the European Union based in Brussels. This is really providing at the heart of the European Union civil protection mechanism, and they're providing 24/7 kind of access and monitoring of the current ongoing situations with these multi-hazards. And today I'll focus on the hydrological modelling component, so CAMS. And at the European Union's 2 hydrological modelling systems are the European and Global Flood Awareness Systems, so EFAS and GLOFAS. These are run and managed by the GRC, but ECMWF is running the operational functionalities and is the computational centre. And so the table just gives an overview of both EFAS and GLOFAS in terms of what these models are producing. So you can kind of see EFAS almost as analogous to a limited area model and weather forecasting. It's the kind of the more in-depth. It's using the best available observations we have in Europe. It's got a long partnership back to 2012, officially, operationally, but even back to 2003, the initial ideas for this model. And a bit like the previous speaker earlier in the session in the Danube, this was the first multi-model, continental scale model that the European countries could have as a consistent system. And so in terms of its older or bigger sibling, GLOFASS, you can see that both are using the same hydrological model at core, but there's a couple of differences. So EFAS is higher resolution, run more often, it's twice per day instead of once per day, and at a sub-daily time step, comparing that to a 5-kilometer global for GLOFASS. But both have a seasonal component as well, so mainly daily flood forecasting, updated every day, but there's also a seasonal hydrological component to EFAS and GLOFASS as well. It's run once per month out to the 7 months ahead. And all this raw information and data is turned into products that we serve through a web server. And just one example here is the flood hydrographs that we can see. So in any one day, we can see an ensemble of a flood signal, but there's also products in seasonal forecasting and other things. And so on to the first synergy. And this is the use of the ERA5 data within the GLOFASS flood forecast as well as the seasonal. So the first thing, we take the output from ERA5, so there's 6 variables in total, such as rainfall, temperature, wind speed, and some of the radiation terms. And this goes into the Listflood hydrological model. This is then turned into, we generate a GLOFASS hydrological reanalysis. And if you look at the map on the bottom right, bottom left, you can see we produce from 1979 up until near real time, we produced effectively a data set of the rivers across the globe. And where we use this in the model chain, the first component, and I'm looking back to the annual seminar last week, the fact that ERA5 is operational is such a key thing and has allowed applications such as this to exist. So we initialize our flood forecast based on the near real-time component of ERA5. But also, the second main component is, unlike other variables like temperature or precipitation, river discharge, it's not a meaningful variable in terms of magnitude very often. We have a lot of biases in our model, so we need a long climatology to understand if a flood signal is actually extreme and we should be worried about. So having this back to 1979 allows us, for every river in the world, to have a model climatology, and we can compare whether a flood's expected to exceed an extreme threshold. So both the operational component of ERA5 as well as the longevity of it is core kind of, in terms of user requirements for us, it was absolutely essential. The second synergy is then around the use of enabling scientific research in hydrological impact of different reanalyses. So this example by Joaquin, led by Joaquin a few years ago, was looking at, could we understand the hydrological impact of moving from ERA5 to ERA5 land? And because we already had the workflow set up from ERA5 to move towards a new data set or a new and upcoming data sets was relatively easy. We also were able to explore and use the global database of hydrological observations used within GLOFASS. So unlike precipitation and other meteorological variables, the data are less shared internationally. So we have a GLOFASS partner network that we're able to use in parts of the world, but we really wanted to understand the hydrological impact of such changes. And in this example, we just see that we get a 16% reduction using ERA5 land and biases using ERA5 land compared to ERA5, as well as improved performance in 65% of catchments. All the CAMS data are on the CDS and available through users. This was a major achievement. And so for each of the systems, there's 5 data sets each, so 10 in total. So we've been quite busy. I apologize to the CDS team and other colleagues. So both the models have the historical reanalysis, the real-time forecasts, a corresponding set of reforecasts for the flood models, and then we have a seasonal forecast and seasonal reforecasts each. And one of the big things our users have been asking is when we launch a new model, sometimes they're not ready, they need to test thresholds. So we've been putting pre-release of our new models ahead of time on the CDS. And when we go operational with a new system, sometimes they're also not ready, so we have a legacy system afterwards. And this is just because we're updating every year, there's just some organizations not able to make the switch. And so we've been really kind of pushing the CDS probably outside of what it was designed to do, but it's just, I suppose, testament to the operational nature of it and the request from users. We've also noticed turning that raw data into information. There's quite a large gap in the hydrological community being able to use these large gridded models. There hasn't been such a history compared to climate meteorology and other fields in many parts of the world, in many different industries. And having GLOFAS on the CDS, the C3S data tutorials has been a really nice step in that direction. So being able to show users through Python, Jupyter notebooks, how to download the data, extract the area they need and be able to do some basic plots, I think is a step in the right direction, and looking forward to seeing where it can go. The fifth synergy is around the use and the collaboration of the EFAS, European Flood Awareness System data, in the European State of the Climate since 2018. So it's the fifth year this year that we've been contributing river discharge as a section. And just some of the headlines, I think statistics like the second lowest on record discharge across Europe, that type of statistic wasn't possible to be presented before this. We had the data for flood modeling. It was sitting on archives. We updated every day for the flood model. We have a long history, but it was really through the collaboration with the European State of the Climate that we could actually use this data for something else and look and see, can we monitor rivers across a large continental scale. And I think that the bottom statistic, showing in 2022 that 63% of rivers were below normal discharge. With observations alone, these type of statistics aren't possible. So being able to use these operational models on gridded can really uncover a lot of different patterns that weren't possible before. So we hope to continue that collaboration. The final synergy is around the C3S operational water service and the collaboration with CHEMS. So this is both working at a European and global scale and provide a multi-model seasonal hydrological prediction service. Both EFAS and GLOFAS seasonal will become part of that, and we also are collaborating on definitions of data standards and making sure we have consistency across both. So we're really trying to increase the kind of efficiency as much as we can. And all data sets will be available through a common CDS. And as well as that, the observations that we collect as part of the EFAS, the meteorological observations as part of the EFAS network, we also feed that through the other hydrological models as well. So we have the best kind of scientific and hydrological prediction in Europe as well. And Peter Berg from SMHI will give a talk tomorrow on this. And there's also posters from Peter Berg as well, and Robert Sweppy from UFZ. So if you want to know more detail, please follow these. So finally, just a tour around the 6 synergies that are currently ongoing, from the use of the ERA 5 data in the CHEMS GLOFAS, the increase in scientific research that we can do on that, to the use in the CDS, and more recently, the exciting prospects that Carlo mentioned this morning about the operational seasonal C3S water hub and the collaboration with CHEMS, EFAS, and GLOFAS within that. So looking forward, we really see that, I think, expanding the C3S and the next generation of tools. I know Earthkit will be mentioned later, and I think that's going to be an exciting direction for increased use of that data. We mentioned earlier as well, hydrological products. I think there's a lot of coordination that can be continue to be done among C3S, CDS, CHEMS, and others, as well as increasing the European State of the Climate contributions and any hydrological related streams. I think there's a lot of extra things we can do there in terms of looking and reporting extremes. Early testing of C3S data by CHEMS, so looking forward to products like ERA 6 and having kind of advanced understanding of the hydrological impact of those is going to be quite important. And as well as David mentioned, with increased precipitation products quality, that's something that we're also trying to investigate. What is the added benefit of such products in hydrology? And finally, I mentioned earlier as well by Hans, is the need for observations, both hydrological and meteorological observations. These models are nothing without these, and I think increasing the exchange of data flows of the observations between both these will just increase the user experience. So that's all from me. Thank you very much.
Many thanks, Sean. And as the speakers who are on site here in Brno come forward to take their seats on the stage, I thank our participants in Malmö for joining us, as well as thank Marie and your speaker in Malmö. Marie, back to you.
Yes, okay, so thank you very much for having this joint session. I think that was really nice. The only problem here, and I apologize, I was trying to exchange with Bruno at the same time. due to the fact that we have a special presentation at 4 o'clock in this room, I think we will have no time for setting up the question in real time with Bruno right now. So the plan is that we stop here the exchange. So for direct people with William, you can talk to him later in the session or at the end of the room if you have questions for William. And otherwise, if you have questions for the speaker in Bruno, I would encourage you to write emails to them, and I'm a bit sorry, but that's what we have to do. But anyway, it was really nice to be able to have this exchange together and this session jointly together. And I hope you also enjoy it. And thank you again, and thank you, Bruno. I wish you a nice question and answer session there on your side. Bye-bye, thanks.
Thank you very much, Marie. This then concludes the joint part of this session. We will now run the Q&A session like we did before. The difference is, however, that questions have been sent in over Slido. However, in the interest of keeping things dynamic, since we're not connected to Malmo anyway, if you wish to ask a question, even if you have sent it over Slido, do raise your hand and a microphone will be there. But let's start with one of the Slido questions, and I'll be helped by Joaquin and Jörg, as they have been keeping an eye on Slido. Don't select questions that are only easy for you.
Thank you, Ali. So the first question is going to be for Joao. Sorry, Joao. So the first question is well, you know how hot this summer has been, and communicating about land surface temperature is not been easy. So the question is, what do you think we should do differently in order to communicate it better?
But it was you, Carlo, that made the question.
Yes.
I was wondering.
It's Carlo question. It has been promoted. It has been promoted. The question.
Maybe you could elaborate a bit on the type of difficulties that you had. I think I have a microphone, right? I don't need. You don't need that.
Yeah, let's just use this
maybe.
one.
Oh, yeah. What type of difficulties did you have? Maybe that will help.
I didn't have a difficulty myself, but interacting with a journalist was difficult in the sense that there was a lot of misunderstanding of what the LST was with respect to the 2-meter temperature. And this actually created a bit of a headache. ISA was faced similar challenge, and I think anyone speaking around topic related to air temperature versus land surface temperature had that challenge. And I was wondering whether, from your point of view, you have some advice or suggestion to make on how to do better next time.
I actually want to add to that because I've actually seen some fact-checking, those fact-checking journals trying to disentangle between this, what is the land surface temperature versus 2-meter temperature. I think the advice is whenever you put a news piece out there, you have to explain what it is, what we are looking at. I think that's the way, because people are not just used to think of the temperature of the surface instead of the air temperature that we feel. So I think we really need to tell that it's a different quantity, and it will tell you a slightly different story. For example, when I showed here the ranking of the heat waves and the characteristics of heat waves according to the year, I couldn't help noticing that the 2023 actually didn't seem very nothing special compared to, for example, the information that you provide in the climate bulletin. And that's because the drought conditions were not that high, and so LST goes down. So it's a different story. You can, for example, I think one potential use of these LST anomalies is to try to study the coupling, the reinforcement of the temperature anomalies that you feel with drought. So the link between the two can be studied using LST anomalies.
Excellent, thank you very much. As we take the next question, allow me to ask the AV team to arrange for another microphone for the room. Another one from Slido.
Okay, so the next question actually came from Malmö, so they will not hear the answer, but we're going to anyway ask the question. So it's from Apai Devastale, so he's with a Swedish Meteorology Service, and it goes to Joaquin, and he's asking, so on soil moisture, how reliable are soil moisture products over the Scandinavian regions? So there's a large forest variability and many inland water bodies.
Can you hear me? Yep, okay. So yeah, I mean, this is a good question. It's about soil moisture when we have dense vegetation. So the problem is that the more dense the vegetation it gets, the less sensitivity over the soil moisture we have. So when we have forests which are dense, the problem is that the microwave signal will saturate. At that moment, we don't have more sensitivity to soil moisture. So at the moment, we rely on the network of the in situ stations from the International Soil Moisture Network to validate soil moisture products. Unfortunately, they are very, very sparse, and as usual, we've got quite a lot of stations in the US, in part of Europe, but not in the rest. So we have to rely on these measurements to validate these data sets. So when we get to forests and wetlands, then it becomes very challenging. And at that moment, yes, it's true that it could be less reliable. I think the other thing we can do is to, at the moment, just rely on models too, and reanalysis, and see whether they have show some degree of consistency. But still today, this is still a challenge. Going into soil moisture over that area densely vegetated is a challenge, and of course, we lose sensitivity to soil moisture.
Many thanks, Joaquin. Let's turn to the room. Even if you sent your question online, it's also nice to ask.
Sam Armand, ECMWF. So this is a question for Zoran.
The question is for?
Zoran, okay. For the Danube. So for your climate adaptation plans for the Danube, what climate information do you use? And the second part is if you use C3S or not. And the third part is if you don't, what are the barriers to uptake?
Yes, thank you for this question. This is one of the reasons why I came here today, not only to present the ICPDR, but also to learn about these services and to consider how they can be used in future. We have been using the JRC results. We have been using the European Drought Observatory. We also had information and cooperation with the Drought Management Center for the Southeast Europe, and so various sources. And I'm very much keen into learning how we could not only incorporate these sources of information in our future plans, but also how to use our organization as a platform to share this knowledge with the member countries so that they can, through our expert groups, maybe on certain topics which are like floods or monitoring and assessment, or we have this, hopefully, I mentioned, but I didn't have time enough, we are looking forward to get, or to see if it's going to get approved, the project for the water balance. And if that goes through Interreg new call, then we will also be using a lot of information that is available. Thank you.
Many thanks. A question from Jörg and Joaquin.
So that question, yeah, this is a question for you, Jörg. So
what a coincidence!
And I think it comes from this room. I think. So this is about what are the priorities for the next phase of reprocessing in COP3 for reanalysis?
So it's a good question, actually, and I know it came from Bill. So because I passed by in the middle of the session and he was telling me that he asked that question. But anyway, so I think one thing is about data that are assimilated. So I think we will do a similar assessment as we did last time. So we need to identify what are the remaining gaps that we haven't worked on. So, and I think we have still a long list of things we do not address, and there are still some open options that we are not certain how and when we're going to exercise them. So I think there's still some ammunition of past data that we can use. But then there's also probably a second part of that, as you seemingly use a lot of data at the interfaces. So snow cover, land surface temperature, and there was actually another question that we could probably combine here. I think it came from Paul about the long records on land surface temperature using AVHR and others. So where you rather use derived quantities from remote sensing data, if the input data for that are fit enough for doing this on long records. So this I would also consider in the next COP. And of course there will be a lot of support external to Copernicus or being done by our own Copernicus contribution agreements or reprocessings of data that are anyway instruments still in space will be regularly reprocessed, and you can use that. So this, for instance, altimeter data, and we also think about redoing altimeter records backwards, because we basically have all the data and all the methods to do that. So there's a lot on the list, but I think most important is that you, as a user of those data, come up with your needs to us, and then we can see what is possible and how much it may cost.
Many thanks for that answer. The gentleman in the back, and then we move to the front.
Gerrit van der Schrier, KNMI, Dutch Met Service. I have a question for Zoran. So there are many contrasts in the Danube Basin, and one of those is that the countries in the basin have very different data policies. So more to the east, it's very easy to get lots of high-quality data, but much more to the southwest, it's very, very hard to get your hands on decent in-situ data. And we've seen many examples today that adding data to the C3S products actually increases the quality of the data products quite a lot. So is there anything you can do in your capacity to make sure that some of these countries open up? And I understand that this is a very difficult question because it's probably not in your hands, but
well,
is there...
it's maybe not in my hands to make a decision or to put extra pressure, but it is in my domain of work, and I'm very grateful for this question. So actually, we have a very well-developed data policy, but the ICPDR as an organization is built on the voluntary cooperation of the countries. And the long term, for 30 years now, we have managed to achieve focus of attention and the good level of cooperation. It's the technical experts, but every 6 years when we have our plans, then we have ministers or state secretaries that come together on our meeting and they endorse these plans. So they have high level of encouragement to cooperate. And we have developed a very detailed data structure where, of course, we do respect the limitations individually given by the countries. But the system is very transparent and it's all visible. Whatever is not restricted is shared with the public, and what is restricted can be requested for. And there is a good overview of the information. And specifically about this, I mentioned today 2 things that may be of interest. So not coming only to learn about your products, but having something to offer. That is that transnational monitoring network, so-called TNMN, which has, like from 1980s until today, the data about the discharges, the water flows, the chemical substances, and so on. And what we are just about to open by the end of this year, hopefully, I'm saying again, Danube Hydrological Information System, there will be hundreds of these observation stations with the water levels, discharges, water temperatures, and precipitation data related to these stations which are on the rivers. Excellent. So hopefully that will also be useful for you in the future.
Thank you, Zoran. Sam.
Yeah, hi, question for Sean. In terms of, and thanks for all the excellent presentations, and thanks also for describing synergies in between C3S and CHEMS, particularly on data. So my question is on improvements to EFAS and GLOFAS, particularly with some of the floods we've seen this year. There's been challenges associated with lack of access to river gauge data, but there's a European law that says that publicly funded data collection must be open access. So my question is, what do you see the benefits of this, and how quickly can it be included to make EFAS and GLOFAS better products?
I think the question is, it actually links back to, I think, the AI question earlier, because at the minute, the current way we do the hydrological modeling, we effectively gain hydrological observations, meteorological observations. So increase in meteorological observations could be an immediate impact, because this is what we use to force the model. So any improvement in initial conditions would be immediate. But in terms of calibration of the hydrological parameters, these are done usually about once a year, once every 2 years. So if we get new data, it could be 2 years down the line before realistically any user, any country would see a benefit in the hydrological performance. Of course, we can increase the resolution of the model, increase all the land data sets, which we have done, and actually next week EFAS 5 will be launched, 5th version, and there is a lot of improvements there. But we compare that then with the AI approach to hydrological modeling, and this is a more immediate thing. And I think this is something that we have to bridge and understand the kind of a hybrid model. I think we need to get that turnaround to increasing the observation into the system to see improved benefits. One thing we have seen with the Greek flood is the ability, at least for a validation point of view, we're actually using the satellite sentinel flood extent to verify really how the hydrological model is performing, and it's actually doing quite a decent job, but there's other elements in terms of magnitude we've issues with. So twofold, I think it can be improved, but it needs to be faster, and I think that's a real challenge.
Thank you, Sean. There's quite some questions on Slido, so we'll go over time just a bit. Could you share another interesting question?
Yes, so as we love to play ping pong, there's one on the C3S project, which Joaquin is supposed to answer. So in this presentation, you propose to use more satellite observations to constrain land and future reanalyses. So can you tell more about SAT observations and that you are planning to use in the future?
Oh, yeah. Well, I didn't change names, so I'm not Patricia, but so I'll try to answer for Patricia, even if she's not here. I think it refers mainly to the land-only reanalysis, so it would be something which would be the equivalent of ERA 6 land. So in that, if that's the case, I think it would add really value in the moment if we are able to assimilate observations from that we don't assimilate at the moment in the IFS. So, for instance, I'm referring to local networks of stations, for instance, of snow depth, of soil moisture, and others. That at the moment they are not part of the stream of assimilated data in the IFS. But we have to be very careful because the main strength, or one of the main strengths of the ERA 5 land in this case, is that it's very consistent over a long period of time, over decades. So that's very good for a trend analysis and for climate variability. So if we are not careful with that, we can come back to the same type of problems that we've got in ERA 5 with the surface field, is that at some points, especially with those variables that have long memory as soil moisture, we can have jumps in time. So this is why I think it makes sense to go for new observations and to assimilate them, but we have to be very careful, because otherwise we'll come back exactly to the same problems we've got in ERA 5, and then we will not add an extra value. So maybe that answered the question. Maybe you want to add something, because this is the series, which I'm not...
Basically reading out what Patricia emailed me. So that's for the land demonstrators that we will have. We also do coupling reanalysis, because C3S is also about actually 3 components. It's about the unifying the land data simulation system, because now they're all univariate. Then also increasing the coupling between components, and then a better coupling of the land with the atmosphere, and also to make use of interface observations. So for the second and the third, which is not purely a land product, but just a whole proper system, including all the different components, there we also plan to use SMOS data, SMAP, EMSA2, ASCAT, soil moisture, and we will also prepare for the Copernicus expansion mission SIMMER.
Thank you, Hans.
Fantastic. So on that note, please join me in thanking the speakers, but not before you hear these few technical remarks. If we could have the poll on the communication workshop come up again, that would be excellent. Please respond if you haven't. Speakers for the next session, please meet me in the back of the room immediately after I end this session, so next to the AV team. We now have a coffee break, and please be in the plenary room at 5:30. Now join me in thanking our excellent speakers. Perfect. Did I leave my phone here? No, I didn't. Shall we start? Yes. Shall we start? Shall we start? I'll do my best. They're saying if the deputy doesn't go in, we're not going in. Jörg, bring your coffee inside. We're going to start. Thank you. We're going to start. We're going to start. If you don't mind moving in, that would be great. We're going to start, but you can bring this in. We're going to start. All right, everyone. Please make yourself comfortable in the seat of your preference so we can start the last session of the day. Okay, brilliant. As the last of you take their seats, allow me to read out to you the title of the final session of the day, New C3S Infrastructure and Tools. In this case, we have 4 speakers. The final speaker will deliver a quick workshop that we're all looking forward to. There is no Q&A in this case. Now that you are all here, allow me to give the floor to the first speaker, who will talk about operational report and statistical updates. All speakers, by the way, work for ECMWF, and the first one is Irina Rosen. Please give her a big applause.
Good afternoon. I'm going to tell you about what happened with the CDS Climate Data Store since the last General Assembly. I'm also going to provide you with information what we can provide in terms of cloud resources and dataset statistics and how to request both. Okay. So, since the last General Assembly, the Climate Data Store was doing very well. Currently, we have over 240,000 registered users from over 170 represented countries. Over the past year, in average, we had about 4,800 new user registrations per month, which equates to 160 new users daily. Majority of users are from the academic background, and in terms of world region, roughly 45% come from Asia, 36.5% from Europe, and 18% from Americas. Over the past year, the Climate Data Store delivered to the users nearly, on average, about 3,000 terabytes of data per month, which is 100 terabytes of data daily, and processed around 20 million requests monthly, which is around 600,000 requests daily. That's a huge amount. Oops. Okay. So currently in the Climate Data Store, we have 138 data sets. Over the past year, we had published 12 new data sets, and the list of data sets is listed here. We also deprecated 4 data sets, and these are reanalysis, Era 5 reanalysis preliminary back extension data sets. Out of these all the data sets, we have 58 data sets which are automatically updated using a preset update schedule. In terms of catalog applications, we have 38 applications, 9 viewers, and 40 applications available via other platforms. This slide shows statistics for Climate Data Store datasets, split by dataset family. As you can see, our most popular datasets come from the reanalysis family. And for all datasets, majority of users use CDS API to request and come from the academic sector. And if we are talking about individual data sets, then reanalysis Era 5 single levels, reanalysis Era 5 pressure levels are the most popular data sets. This slide shows a typical weekend in the life of the CDS system. So we are looking at Sunday, 10th of September. Typical weekend, nothing special. We have 1,745 active users doing requests, sending requests for data. On this date, we had nearly 1 million completed requests. Some percentage of requests failed, but these failures are due to users submitting wrong CDS API requests or requesting data which is not yet available in the CDS catalog. Such huge, a system with such huge demand from the users requires very good monitoring and troubleshooting activity. So this slide shows one of the tools we have at our disposal to monitor the evolution of the queues in real time. Here we are looking at 4 hours of 10 minutes data. So in order to detect if there are any problems, what we look for is a sudden change in the combination of running and queued users and requests. For example, if we have a huge amount of active queued users and very little running users, then this indicates a problem and we need to take actions. Some troubleshooting can be very simple, for example, adjusting some system parameters like a number of available slots per user, and some troubleshooting actions require more drastic interference into the system. So now I'm going to tell you about introduce a new contractors portal called COPCO. It is accessible using this link. This portal was created to simplify communications between contractors and SMWF staff. And it's specifically for contractors for dataset ingestion, requesting cloud resources, applications, training, and evaluation and quality control. So if to request cloud resources, a user needs to go to this area called Cloud Resources. After clicking, the user will be redirected onto a GUI where the user needs to fill in contract start and end date. Contract number is very important, name of technical officer, and cloud resources particulars, like requested disk space, initial and projected, number of CPUs, number RAM, desired RAM, and also provide a data management plan or server management plan, and describe properly what is the plan for the server, what the user is going to do, whether it's only a dataset storage server or whether the user is going to run a specific service or very demanding computations. More guidelines are available from this link. Oops. Okay. So for data providers, we also provide statistics on demand about the performance of their data sets. To request statistics, please go to CDSI and then click on other CDS icon. Guidelines for statistics are available from this link. So what we can provide is statistics on number of requests, retrieved data volumes, number of users, and we can do totals split by dataset, variable for various time intervals. We can do distribution of users by sector and distribution of users by geographical location. We also have 2 ways of providing the statistics. First is sending a PDF file with graphs or providing reports of simple statistics in CSV format emailed at a certain date and time on a monthly or weekly basis. And to summarize, the climate data store remains fully operational, and we have a growing number of users requesting data at any time, weekend or weekday, doesn't matter. For any communications with the CDS team, please use COPCO, new portal for contractors. For cloud resources, please follow this link. And for statistics, please follow this link.
Many thanks, Irina.
Thank you.
Our next speaker will speak about the CADS 2.0, Status of Development and Envisaged Transition Roadmap. Angel Lopez, here he is. If you're not too tired, an applause would be appreciated.
Okay, so good afternoon, everyone. It's late in the afternoon, so I will try not to make it too technical. It's just to explain what had happened, what had been doing, and what is the plan ahead for the so-called CADS. So the first thing I want to do is to clarify a bit the concepts, because I think there is a bit of confusion when we refer to the CADS or to the CADS. So let me briefly explain. So the CADS, we can refer to it as the infrastructure that we are putting in place at ECMWF to support the implementation of the Copernicus services. And this covers two parts. Is the cloud, so we have the cloud infrastructure, which is in our Bologna data center, and we have the software, which is the set of components that we are creating and that combined together in a cluster, they offer access to the service. And then this can call the infrastructure layer. The CDS is what we could call the business layer, is what the user sees, is the interface and what the user sees, the interface that the user sees. This is the climate data store. So we could say that the CADS, which is the infrastructure, is the one that is being modernized. And the CDS, for example, we could say that a new data set will be published on the CDS because it's where the user will come to discover the new data set. Then we have the concept of the Earthkit. The Earthkit will be a dedicated presentation later, explaining more, and there will be a workshop on Wednesday just to introduce to you how this is going and start playing a bit with it. So it's this open source Python project that provides a set of tools that will be able to deploy and run everywhere. So in a brief schema, we have in one hand the source code that is provided by our contractor. We have the cloud. We deploy the instance, and then we have with the user C. In this case, it's the climate data store, but it's also the atmosphere data store. And we are also using parts of the infrastructure to support the implementation of the thematic hubs, for example. So this presentation is taken from last year. So this is a rolling process. So we are always learning from the past, so from the success, but also from the failure. So whenever there is an incident, we learn how to solve it, we know how to manage, and we implement a solution. So we are always learning. But we are also taking care of the present. I know there are plenty of users right now using the system, so the system now is alive. So someone in the team has to be looking into it to see how it is doing. And we are preparing for the future, because in the future there will be more users, there will be more interaction, there will be new data sets, there will be new functionalities. So it's completely rolling. The next year, the green arrow will be farther below. So at this moment in time, I want to ask you, who has not renovated or do some construction in the house? You have a nice house that you built time ago. It's perfect. It's perfect, have a lot of space, it's quite robust, it's suit perfectly for your family at that time. But suddenly the family start growing, there are new kids, the kids start with the bike, and then we go with the car, and they start bringing friends, and then there is a lot of activity there. So you decide to renovate the house, to extend it, to make it more bigger, more modern, to accommodate this all new stuff. But there is an in-between. And in this in-between is where we have been for most of the year. But yeah, not too fast. No, we are again in the in-between. No. Well, so this between, as I was saying, is where we have been transit most of the year. So in one hand is all the development. We have all the people working in the renovation, in the extension of the house. We have also to take care of all the furniture and all the stuff that we have inside. We need to move it somewhere, and we need to accommodate it in the new house and things. But we also need to live. We are living. We need to continue with our daily life, so we need to maintain the operation. That is what Irina was explaining now. So these three activities has been our main activity in the CDS team for most of the year. So we are reaching the point where we are planning to enter living in the new house, but we are not still there. We see part of the things, but we will enter on that next year. So the in-between is all the people working. There is a mess in there. There is a lot of people working. It's the carpenter talking with the electrician talking with the architect. There is a lot of people there. It's our contractors. The EQC team is talking with our developer contractor. So there are different components that we are developing in parallel. So we have what we call the CADS core components, which is all the broker and all the things that will be managed, the big part of the processing of the request. We have a new component for monitoring. We are planning to improve the monitoring and statistic capabilities that we have. We have a dedicated component for EQC, where I think will be explained on Thursday with more detail. We have an observation repository in order to improve the way we provide access to observations data. So we are trying to reach the status, which is the beta status, that we are happy enough to open the system to the new user. There are some conditions that we need to reach before opening, so we are working to be there. And then we have the Earthkit. The Earthkit, I think there is a lot of interest. What is the Earthkit? The Earthkit, we could say that is the kitchen. Is the main part of the house, is where you cook, where you interact more with the people, when you receive some of your friends for cooking and things. Italians know quite a lot about this. So Earthkit is being developed a little bit independent of the core CDS. It's an open source. I think there will be a presentation later explaining more in detail what is Earthkit. The good thing is that it deploys and runs anywhere, so there is no CDS editor in the new system. And this Earthkit will be powering parts of the CADS, but also all the visual interactive content that we are going to put together, and also the training material, and much more. So I think James will explain later more in detail, and you have this training tomorrow if you want to join. So this is the architecture of the system, the pillars, the fundamentals. So in the new house, everything, because the pillars were so robust at the beginning, now they are called FAIR, but it was something that we were already considering with different names and different terminology when we defined the architecture some years ago, but today it's called FAIR, and we want to be fairest, because we know that we are there, we are implementing our findable things, so you are able to discover your catalog, you have accessibility to the data set, we are interoperable, and we are able to reuse thing. So all these different components you will recognize from the past, because at the end it's the same. You have the adapters to interact with the different data sources. This will be improved. You are the different components inside, which also interoperate among them, because each component needs to talk with the other. So there is also internal interoperability and internal fairness of the system. And then it's all the interfaces that we are going to expose to the user. We have the web portals. We will have a new API. We are able to accommodate new standards. We are aiming to implement these ARCO services, is the Earthkit, and so on. So the idea is that we will be able to have more people coming to our house, more staff, more things happening in our house. So the furniture and all the stuff that we have in the house, we need to move things. And we have managed already to migrate most of the content. It has been based on an automatic process that we have internally developing. We are tuning it because not everything is exactly the same, but we are able to automatize things thanks to the things that we put together at the beginning. So we need to work. Once we open the new system, the idea is that the full catalog will be replicated and will be working. So there will be the same data, the same access that you have now will be in the new system. For the data providers, will be no difference. There will be a moment that we are working and publishing things in the old system. Suddenly, we will move into the new one. So just to refer, this is thanks to the architecture that we put time ago. Everything is in a set of configuration files. And then there is a process that is able to take these configuration files, deploy it on the system, and the system is able to expose these interfaces. And this provides us with quite a lot of flexibility to accommodate new standards, because it's just a matter of fulfilling different templates or different formats. So whenever there is a new requirement, a new template, a new format, a new standard, we are able to easily to accommodate this, and this is quite flexible for us. So the transition is when the house will be ready and we need to start moving things. We need to start moving the family, we need to start moving the staff, we need to decide when and how we are going to do so, where the rooms, each kid will take different rooms and things. So there will be a strong communication campaign on this, because people need to know what is going to happen and what they need to do. So in overall terms, we are still planning and tuning this. We will start the transition. We will officially open the new system. And this is expected to happen at the beginning of next year. And then the users, there are two kinds of users. New users, no problem with those, because they will do directly into the new system. They will register in the new system. For the historical users, they will take an action is to activate the account in the new system. This is because we need to extend a bit the information that the users provide in order to extend the capabilities that we have for the reporting to the commission. So we need more information from the user. We need users accepting the new terms and conditions. And then they will be able to start using the system. Still, this plan needs to be adapted, but this is the plan. We will start moving some processing capabilities from the old system to the new system. We expect this to take just short time, 1-2 weeks, no more than that. And then we will close the system. We could maintain the old system running in the background in case there is something that we need to keep alive for a while. But the idea is that once there are no dependencies, we will close the old system. Nevertheless, if you have any question or doubt or concern about how this transition may impact your activities, in case you are running something on top of something and you are using whatever, just let us know, approach any person on the team or myself, and we will explain more in detail. And another important thing is that it's not just us evolving, it's also the neighborhood what is evolving. So we are not alone, we are part of a community. So there are a lot of things going on, and we need to connect with all these things. They are doing a new electricity network. They are doing whatever they are doing in the neighborhood. So we are part of we need to connect to these new things. So one of our neighbor, just door with door, is Wikio, is part of the family. So they are also aiming to launch Wikio 2.0. So we are taking this opportunity to improve all the interfaces that we have to them. We have improving. They will be able to run and deploy fully Earthkit, and we are also putting in place these elements, this Arco service that will allow us to visualize all our products in the Wikio viewer. So yeah, probably you remember your feelings when you had to go through this process. And probably will not be the last house you will live in, so probably we will be moving to another house in some years, or we'll be doing some extension. So thank you.
Thank you very much. The next talk will be about the visual interactive content on CADS 2.0, Introduction to the Earthkit. The speaker is James Varndell.
And maybe I'll get there. Is it worse for me, or is it? It is the big arrow, right? The big. There's no like light appearing on it or anything. I don't know if that's supposed to. Okay. I'll try pointing it all around. Oh, now we've gone really far. Now we're on the bad. That's not a good start. Okay, let's see if we can go back. Oh. I can see a mouse. Thank you. Thank you very much. Okay, thanks. So I'm James Varndell. I work in the CDS team and also in the web services team in the development section at ECMWF. So I'm going to talk a bit about the evolution of the CDS toolbox in CDS 2.0 and introduce you to Earthkit, which is an open source Python software project being led by ECMWF. If I can change the slide. Next slide, please. Is that going to work? Yeah, we go. So for those of you who aren't familiar, the CDS Toolbox is a feature of the current CDS, where we provide an online Python editor and environment in which you can access the entire catalog of CDS data, and we also provide a bunch of tools for processing and visualization of that data, all through this interface here. So we have down the left-hand side, that's all of the tools we provide, and they're all fully documented. In the middle is the sort of Python code that you write, which is what we call the toolbox workflow. And then on the right-hand side, when you click that green run button at the top, you get a nice result, in this case, some climate stripes. So the Python code you write here can also generate interactive web applications, so including things like user interfaces, drop-downs, interactive maps, all those sorts of things. So there are lots of really good things about the toolbox. So the online processing component meant that users were able to process large volumes of data entirely within the CDS cloud. You didn't need to download data to your machine or worry about the resources you had locally. You could do it all through the toolbox. And with that came powerful tools, which supported a wide range of statistical analysis functions, with also visualizations, and as I said, web application interfaces. And developing web applications in the CDS toolbox required no front-end knowledge whatsoever. So you're able to entirely use Python to develop web applications. There were also some downsides to the CDS toolbox. So the online-only approach, while it was good for preventing you from having to download lots of data, the technology we used to do that meant it wasn't possible to use the CDS toolbox offline. So if you wanted to incorporate CDS toolbox code in your other Python code, that wasn't very easy or even particularly possible to do. There was also quite a steep learning curve. So we while the application production features of the toolbox are very powerful, it was sort of designed around those features, which meant that doing simple things like just accessing some data, doing a basic visualization, weren't necessarily as simple as they could have been. And then also compatibility. It is possible to use non-CDS data with the CDS toolbox, but it's not very easy and not something we really recommend doing at the moment. And then also there's some slightly more complex things. So the performance of the CDS toolbox was sort of hit and miss. There were some really good things about the performance. We had a caching system, which meant that if you made a really big CDS request, say you took a big chunk of Era 5, it might take an hour to download that the first time. If you try and access that data again with the same CDS toolbox request, you should get the same result instantly. The trouble is, as Irina was pointing out, we've got more and more users, and the more users we have one shared cache for all of our users, and that sort of refreshes itself as it fills up. So the more users we have, the less scalable the cache becomes. And I'm sure some of you in this room who've used the toolbox probably had that frustrating experience of running something you haven't run for a few days, and then it's completely uncached, and you've got to wait again for everything to download. Transparency was another problem. So the technical implementation of the toolbox meant that it wasn't always completely obvious to the users exactly what was happening. So it looks very much like normal Python, but it's kind of not. I won't go into any detail about that, but that created a few problems that were difficult for users to debug on their own. And then also in terms of maintenance and development, all of our service-based code was very tied to our infrastructure, which meant it was sort of closed source. It was hard to share it with collaborators, and we had to sort of explain the entire CDS system to them first before they could collaborate with us on tools. With the development of the new CDS 2.0, we've been thinking hard about what we actually want the climate data store tools to provide. So we really want to lower the barrier to entry for users to access and analyze CDS data and visualize it as well. We want to make the common tasks that lots and lots of our users do all the time as fast, efficient, and easy to use as possible. We want to be as interoperable as we can be with non-CDS data and tools. So this is one of the biggest requests we get from Toolbox users is how do I use this data with my other data that doesn't come from the CDS? So we want to make sure that we maximize interoperability with other data. And also embrace open source. So that means building our tools on top of well-established open source projects, but also embracing open development, which means encouraging the community to contribute to our tools and making everything fully open and available through GitHub. Ooh. I think we're both trying to do it at the same time now. Sorry. Next slide, please. So with that in mind, I'd like to introduce Earthkit. So Earthkit is an open source Python package that can be installed and imported wherever you like. So that can be on your own computer. It can be on the CDS Lab, which I'll come back to in a sec. It can be on somewhere like Wikio or AWS. Anywhere at all that you have Python, you can download and install and use Earthkit. And what does it do? So it basically provides all of the features that the CDS toolbox used to provide. So you've got data access, you can access the CDS, but you can also access local files, any data that you happen to have, data from URLs, and much more sources. It provides some analysis, so we have some meteorological processing, some statistical analysis functions, spatiotemporal analysis, things like aggregation over shapes, and much more. Plus polymorphism, which just means transformations to well-established, well-known data structures like NumPy, Xarray, Pandas, and also visualization, so geospatial visualization plus two-dimensional graph plotting as well. So I didn't mention in any of those things the cloud stuff that we had in the original toolbox. So that's where CDS Lab and Wikio come in. So these are platforms on which you can run this code, still using cloud resources. But the fundamental difference is now using Earthkit, you can then run that locally or anywhere else. You can go between Wikio and CDS Lab, AWS, wherever you want, and it should all still work the same. And here's just a bunch of images that have been generated using some of the Earthkit components. So we've got some geospatial maps in there, also some statistical plots. And if you come to the training session, which I'll talk about again at the end tomorrow, we'll show you some examples on how to produce these kinds of images from CDS data. So why use Earthkit? So obviously there are other open source projects out there like Xarray, but the whole point of Earthkit is that it's trying to lower the barrier to entry. So it's accessible and simple. You don't need to be a software developer to use it. We really want to encourage people who aren't necessarily even that familiar with Python to engage with Earthkit because it's all designed to be very human readable and very high level. It's making common tasks very fast and efficient, so we're providing ready-made tools for doing lots of common analysis tasks, the sort of tools that we had in the original CDS toolbox, but now made open source and accessible to everyone on any platform. And yeah, as I say, we're embracing open source interoperability with popular libraries like NumPy, Xarray, Matplotlib, Plotly, just to let people in at a level where they might already be familiar with those sorts of tools. So sorry to do this at 5 o'clock, but I'm going to show a little bit of code. Just to show you how straightforward Earthkit actually is in practice. So we tend to import Earthkit as EK in Python. If any of you are familiar with CDS API requests, then this data request probably looks very familiar to you. So Earthkit has a data component, earthkit.data, and you can get data from multiple sources, and one of those is the CDS. And essentially all you need to do is say you want data from the CDS, and then you pass a classic CDS API payload. You've got the dataset name and then the parameters that you're interested in. But of course, you can also get data from other sources like files. So I've got from source mydata.nc. It doesn't need to be a netcdf file. It could be grib, it could be CSV, it could be a GeoJSON file. The idea is Earthkit will understand what that file is and produce a data structure that's representative of that kind of data. And then there's even a from source URL, so you don't need to download this data before using it with Earthkit. You can just directly point it to that URL, and it will equally go and get it in the same way as other data sources. And of course, all of these data sources are fully interoperable, so that means you can use all three of these data sources together with Earthkit's processing tools and visualization tools. It also provides local caching, which means on your local machine, for example, if you run this code, say a CDS request on your local machine, it will cache the result locally in a fully configurable way, so you can turn it off altogether if you want to, or you can specify how long to cache for. But the great thing about that is you can make CDS data requests without having to worry about whether that data is going to fill up your disk, because you can specify, I only want 10 gigabytes worth of data ever taken up by these requests, and it will automatically housekeep anything that's pushing you beyond those limits. So it helps you not have to worry too much about data management. And as I've already mentioned, polymorphism, but I just wanted to show you how straightforward that actually is. You just have to do data to Xarray or to Pandas or to NumPy, and it will automatically transform your data into that data structure. Another component of Earthkit, we have some analysis tools. So for example, we have Earthkit Aggregate. So that has some functions for doing things like climatology means. I just wanted to emphasize how it's very human readable. So you have like earthkit.aggregate.climatology.mean. You just pass your data and a frequency, in this case month. So that could be hourly data or monthly data. Either way, it would still produce a monthly climatology. And other simple tools for doing things like climate anomalies, or even things like spatial aggregations. So that bottom one is to calculate the average over the NUTS European statistical shapes on some data. And hopefully you can see this is all very high level, very easy to use, and also crucially fully documented as well. And finally, I just wanted to show some visualizations as well. So we have, Earthkit has two visualization components at the moment. We have earthkit.maps and earthkit.plot. So maps does geospatial visualizations, and plot does the 2D statistical visualizations. As you can see, we have very, very simple functions like this Earthkit maps quick plot. If you just throw some arbitrary data, it could be from a netcdf file, a grib file, from the CDS, from somewhere else, it will just try and visualize that the best it can based on the metadata that it finds in that file. And you can even specify a domain, which could be like a continent or a country. In this case, I put Europe. This is actually ERA 5 global data on a regular latitude-longitude grid, but because I've asked for Europe, it's explicitly tried to find a good projection for Europe. So we've got a really nice, quick graphic to produce. And again, with things like climate stripes or climatology plots, we've got very simple, very human-readable, easy-to-use functions for doing those kinds of things. And of course, even though these examples here are very, very simple, these things are also very customizable and flexible, with lots more options if you want to do something more complicated or more personalized. So finally, just to talk about the project status of Earthkit. So Earthkit is under active development, but it is currently still in the alpha phase of development, although we are making rapid progress. You've probably noticed Earthkit is not Copernicus branded or ECMWF branded. So the idea here is we really want to embrace open development. It's a fully open source project, and we want to try and get the community involved as early as we can. We already have contributions from all over ECMWF, but also from other organizations like Meteor Swiss. It's already available to install through Conda and pip, and you can also go to our GitHub repository for Earthkit, where you can fork the repository, raise issues, contribute if you'd like to. It'd be great. And tomorrow afternoon, we have 2 Earthkit training sessions at 2 o'clock and 4 o'clock in room Salonik 2. So this QR code here will take you to the repository of Jupyter notebooks that we've developed for that training. I strongly encourage you to scan that now if you want to come to the training session, because the Wi-Fi is a little bit slow, and if we all try and do this at the same time tomorrow, I've got a funny feeling it might take a while. So if you want to come to that session, I would scan that QR code. Maybe this evening in your hotel room, using that Wi-Fi, try to download all of the Earthkit stuff. It's all in the README at that URL. If you have any problems, come and talk to me or my colleague Eddie, who's at the back, he's waving, and we're happy to help you. So if you have any trouble tomorrow morning, come and chat to one of us. We can help you before that session. Thank you very much.
Thank you very much, James. We'll go slightly over time to accommodate the next 20-minute workshop, which has the following very promising title: Towards the Fairest Climate Data Store. And the speaker is Markus Zanacki.
Thank you for the introduction, Ali. And since I'm going to be the last one between you and the drinks, I'm going to try and be as fast as possible. So the title of the talk today is Towards the Fairest Climate Data Store. And in the talk, I will be describing what we mean by fair, and also try and show you how we think that the Climate Data Store has already made good progress towards being a fair data store. So the Copernicus Climate Data Store is a free and open one-stop shop to explore climate data. As we've already heard many times today, we have over 240,000 registered users and counting. We provide a wide range of climate data sets and applications via an online searchable catalog. And the CDS is prepared to be a key player in the global ecosystems of data and services, for example, the green data spaces, and as we heard from Angel earlier also, for example, Wikio, the Wikio DIAS platform. But we are continuously improving the service, and in order to do so, we'd like to promote the uptake of new users across many different sectors, and also facilitate the access to more climate data, and also promote sharing of data across the European data platforms. Now, in order to do this efficiently, we want to be more fair. Now, fair stands for being findable, accessible, interoperable, and reusable. And FAIR is a set of guiding principles to support the discoverability and reusability of digital assets. And it emphasizes the ability for machines to programmatically find and reuse digital assets for both the data and also its metadata, in addition to supporting its reuse by individuals. The FAIR principles, the concept is aligned with the European Commission's aim to promote access and reuse of research data. In fact, this is a quote I found in an upcoming Horizon call. Open and fair data is the new norm for research, contributing to adaptation to climate change. And so it's very important. And not only that, but it's also relevant to two key European initiatives, which is Europe Fit for the Digital Age and the European Green Deal. Now, one thing about the FAIR concepts that we need to understand, and also for the rest of my talk, in context the rest of my talk, is that the FAIR concepts may be applied to the individual data record level, but also to the catalog level, but then also to the larger ecosystem of services, the service level. For the rest of this talk, I'll mainly be focusing FAIR on the catalog level, but of course that goes hand in hand with the data, the individual data records. So just a quick question for you, just a thought a thought question that you may just have a quick think about. How should you aim to use the FAIR principles? So four options here is to judge the fairness of your data set, or to communicate your digital assets, whether it's a tool to enhance the usability of digital assets, or is it to win grants from public funding. So if you just have a quick think about it, and the one that I think is the correct answer, and certainly within the CDS, what we'd like to promote, is to use it as a tool to enhance the usability of digital assets. Now, I know we have many contractors and third parties here who will and have already supplied data sets and new data sets to the CDS. And just to reassure you that we don't want to use FAIR as any level of test or judgment to the data sets that you supply, but more so we'd like to use it with you as a tool to enhance the usability. And I think this is great because then this will maximize its reach and add more users to each of the data sets. Now, FAIR can be broken down into individual components for each of the four findable, accessible, interoperable, and reusable. Now, I haven't listed them here, but instead I've posed a few questions that one can ask oneself when you want to determine whether your data set can be classed as FAIR. So with regards to findable, one can ask oneself whether the data resources can be easily discovered using relevant keywords and metadata. For accessible, can the data resources be accessed, read, and understood by machines and humans? Is it available in widely used open format? Interoperable, can the data be easily integrated with other data sources using common standards and formats? And for reusable, you can ask, can the data be used and reused for multiple purposes without significant effort or additional licensing restrictions? So, like I said, there's many resources online. I haven't laid out all the components to each of those, but if you'd like to find out more information, please visit these links online, or also please visit our poster that we have in tomorrow's poster session. Now I'll go on to talk about the CDS and how we consider it to be to have already gone a long way to being fair, and what we think it's one of the reasons why it's such a successful catalog entry. So I've picked out a few of the components that I haven't shown, but is described as part of the FAIR principles. Under findable, there is the global unique and persistent identifier. In the case of the CDS, we provide each of the catalog entries with a DOI, which is linked, in this case, to the DataScience Commons catalog, a certain database. And in this way, the catalog entry in the CDS is linked with a persistent identifier, but also accessible online through multiple indexes. We also have the catalogs. Each catalog is described with rich metadata. So at a catalog level, we have on the overview page of each data set, we have a data description table, and also each of the main variables are described. And not only that, but it's also in machine-readable format. And also, the metadata and data is indexed and searchable. And so here I show you a selection of the CDS catalogs which are available through the Google Datasets page. Try again. Okay, so we have another question for you. Again, it's just for you to have a think about. Of these three dataset titles, I'd like you to just think which of them is most findable. Now, the first, I'll let you just have a quick look at it, and then I'll go on to explain what we think. So, in the CDS, we aim for the dataset titles to help the users find the appropriate data that they want to use. And as such, the second of those three titles was a title taken from the CDS, and we like to maintain all of the dataset titles with some structure where we name the main variable or the theme that is involved in the dataset, then maybe a spatial component to the dataset, then a temporal component, and then the source for which the data is derived from. I've also listed a few of some of the things that we also expect from a dataset title. And it's mainly to make so that it doesn't include many acronyms. It's not obliged to contain all these items. That the derive from should refer only to the main categories in the catalog, and also that detailed information regarding the data set is provided in the overview text. Now, this means that the CDS catalog has all the data sets that look consistent amongst each other, but also it helps with the findability of each individual data sets and makes it easier and lowers the barrier to entry for the users. Moving on to the next of the FAIR principles, so the accessibility. The CDS uses open data and also has an open and free license. So in this case, I show here that we use a Copernicus license, which is very open. We use a standardized open and free communications protocol. So in this case, the data is available just via our website through a download form where users can click through on the download form and download their data. Now there is an authorization where you need to log in or create an account to log in, but this is just so that we can prevent people from misusing the climate data store. We also allow access through the CDS API, and this is an open source CDS API here in Python. And lastly, the metadata is accessible even when the data is deprecated. And here I show one of the data sets that we have taken down, but the catalog entry remains with the associated metadata. Okay, so I have another question for you, just to look. So of these three, so these are CDS dataset overview images, and I'd like to ask you which of you think that is most fair, and I'll just give you a couple of seconds to think about it. Now, indeed, all three of them are overview images from within the catalog. Now, as you can see, there's a broad range of images that come, but what we'd like to see moving forwards is that overview images also contain the metadata related to that picture, and also potentially even the code that was used to create it. Now, this is particularly important as we have our data sets appearing in other catalogs where we don't control how the overview images can be shown. And so it's really important that users who come across these understand the context in which these pictures are shown, but also would be able to replicate them if need be. So moving on to the third, which is interoperability. So the CDS uses the metadata uses formal accessible languages for the knowledge representation, and also the metadata uses the vocabularies that follow FAIR principles. And lastly, the reusability. The data and metadata are richly described with attributes released with clear and accessible data usage license. Here I just show you an example of the rich metadata, both in terms of human readability in the data description table of main variables, but also at the individual data record. So in this case, a netcdf file where we also include metadata in the global attributes. The data and the metadata is also associated with detailed provenance, and in this case, each data set, each catalog entry contains a whole load of documentation that goes and explains how the data set was created, etc. And also that the data means the domain-relevant community standards. So in summary, the FAIR data principles ensure that the data are findable, accessible, interoperable, and reusable, and this is both for machines and human users. The CDS is committed to working towards being fairer, with richer metadata at catalog and data level, and also improving the machine accessibility and interoperability. This is particularly important as we go towards sharing data out across the different data spaces around Europe and global. And of course, this is said in FAIR maximizes the added value of the CDS by allowing the interoperability with other European and global data services. So with that, I thank you very much for your attention.
Marcus, many thanks also for your excellent time management. We're only 1 minute over time. That's excellent. So, a quick practical remarks before we have dinner and some drinks. As said, in a bit we'll be serving some mocktails, and at 7 o'clock we'll have our dinner and some entertainment. Who was there at last year's GA? Raise your hand, please. That's a great number of people. So the city of Den Haag reported unexpectedly and unexplainably, I should say, high noise levels at that fateful night that I'm sure you remember. And so to save the citizens of the wonderful city of Brno the same trouble and turbulations, the entertainment of tonight will not involve singing, but there will be music. And there will be a game that involves probability, and I'm sure that at least some of you consider that to be home turf. So the speakers who will be opening tomorrow, could you please meet me at the back of the room at 9:15 sharp tomorrow? Thank you very much, so we can have a quick chat and you know what to do. Other than that, let me see if I have anything else to say. The dinner is a standing dinner, I should say, and it is at the restaurant here. And please, if you want, fill in the survey where you can evaluate the event, and the survey will be available at the reception. If you are online and you decide to leave today, you should look for the link at the bottom of the YouTube that you are following for our streaming. And you are promised a nice gift once you complete the evaluation. On that note, give yourself and the organizers of the event a huge applause, and see you later.